group of people what organization is most responsible for revolutionary advances in space technology, and there is little doubt their answer would be NASA. Clearly, over its long history, NASA has been one of the most innovative and exciting change agents the world has ever seen, proving that we can accomplish great things if only given a goal and the opportunity. That feeling has been firmly imprinted on the NASA DNA and continues to motivate all those who push the envelope of technology. But rather than just rest on its laurels, NASA is moving to expand its role as a change agent in new and exciting ways. In order to do this, the NASA culture will need some minor tweaking first. Today's generation of NASA researchers are working to alter some outmoded practices of how technologies are developed and implemented at NASA. If these ideas take root, they have the potential to revolutionize NASA from inside out. Coming up on this episode of NASA X, we will follow members of Space Technology's Game-Changing Development Program Office as they work to revolutionize and mature new technologies within NASA. We will feature a few of the many technologies managed by the GCDP to see how these innovative ideas are advancing the missions of today and missions of the future as well. NASA has a long and storied past. In its short history, the agency has accomplished truly breathtaking achievements, forever changing how humans view themselves in the universe. The NASA of today is no different than the one of the past, of course. It is still the world leader in space technology and is still accomplishing truly unbelievable feats. But many in the NASA community have seen the pace of technological breakthroughs slow in recent years. That was not always the case. In NASA's early years, it seemed like many of its projects were stuck in fast forward, none more so than the Apollo program. President Kennedy made his famous Man on the Moon speech at Rice University in 1962, and by July of 1969, Neil Armstrong was stepping out of the lander onto the surface of the moon. One reason we got there so quickly was because NASA made the decision early on to let the engineers lead the charge toward the moon, rather than the norm, which was to have a more bureaucratic structure. That is not to say there was not structure. There was just an understanding that more risk must be taken in order to complete the mission in the given timeline. But as the Apollo program retired and the shuttle came online, a shift began. The culture within NASA became much more risk-averse and, rightly, more focused on safety and successful missions. But with this new posture, less focus went into the development of transformative technologies. This mindset permeated throughout NASA, and eventually, in the words of one NASA official, NASA became more evolutionary and less revolutionary. NASA never stopped innovating, but researchers developing new technologies often found substantial hurdles in their way. To better understand this, let's look at what NASA calls TRLs, or Technology Readiness Levels. The 9 TRLs measure the maturity of evolving technologies and order them from 1, which is the lowest, to 9, which is a technology that is fully developed. An example from history of how the TRL system works can be seen in the late 1950s, when the famed NASA engineer Max Faget came up with an idea for the Mercury spacecraft. Dr. Faget was sitting in the cafeteria at NASA Langley drawing on a napkin when he came up with the idea for the basic shape of the Mercury capsule. He fleshed out the details with his team, and soon they had the beginnings of the craft, which put them at Technology Readiness Level 1 for the Mercury project. He and his team then began moving through the other levels, testing and building models, and after a few years, arrived at TRL 9, which culminated with the first manned flight of the vehicle on May 5, 1961. The same basic concept is still used today. Researchers come up with concepts and ideas and hope to move them through the early TRL stages all the way to full maturity. This system is the framework from which NASA engineers develop technologies, so it goes without saying that the TRLs are very important within NASA. But in the last few decades, many researchers have come up with great ideas only to find themselves stuck in the lower TRL stages. But in the early 2000s, pushback began happening within the NASA research community. It was widely agreed that there needed to be a way to push important concepts to the front of the line and move them more quickly through the technology readiness level stages. To do this, a sea change needed to happen within NASA, which would completely alter the current culture and get us back to our leaner, engineer leads the way mentality. That sea change happened when NASA's Space Technology Mission Directorate created the GCDP, or the Game-Changing Development Program Office. Space Technology developed the GCDP with the idea that new, exciting, disruptive technologies would be rapidly infused and given the chance to prove themselves more quickly.
If you look at the Space Technology Program, especially if you look at the Game-Changing Program within, our projects are about 2 years long with an option to extend them for a third year. So basically we are carrying on executing our existing portfolio, and by the end of the year we will develop dozens of new technologies that we can make available to other programs within space technology, other stakeholders such as human explorations under the AES project, or maybe we can pass on technologies to Science Mission Directorate as well.
The idea here is to take some more risks and to do some things instead of incrementally, but in a transformative or disruptive way. Let's look outside of the box. Let's look for completely different ways of doing technology. And so the idea is that we can afford to take risks and target technologies that will hopefully have orders of magnitude improvement that can do things that we've never been able to do before.
With this idea firmly established, the team needed to begin looking throughout NASA to determine which projects would be first on the list.
Somebody might have a great idea, a new way of doing navigation or communication, and they'll come and they'll pitch that idea to a PI. If the PI believes it's a good fit within our portfolio, that it meets game-changing metrics, that it's aligned well with agency priorities, then they'll develop what we call a New Start proposal, and they'll bring that to our program board. So they have to be a TRL3, and that's, they've gone through the proof of concept. It's not basic research, it's not a scientist in the lab, but it's someone who's taken it and said, look, I've checked it out in a small way, a small scale, and it's proven itself. I need to get it from TRL3 to TRL5, through the Valley of Death, we call it.
This term, Valley of Death, is apropos because this is where so many promising technology ideas falter. Generally, an idea in the TRL range of 1 to 3 are proof of concept ideas. But once they get into the TRL3 range, more often than not, excess funding and time needs to be spent on them to move them forward. This level is where so many technologies of the past fizzled out. But one of Game-Changing's central goals is to grab the hand of some of these ideas and lead them through this valley of death and on to actual missions.
What we are doing here in Game-Changing is we're taking a bunch of technologies in this 3 to 6 range, and we're rapidly advancing them. We can take selective ones, the best ones that we can find, we can advance them for a 2 to 3 year period, we can mature them from this lower TRL to where they can be used by projects and missions, and then we can go on to the next one and do it again and again and again.
With the goal set, the team began the process of looking at some of the best ideas within NASA, choosing a wide-ranging set of technologies to help rapidly mature and begin this new approach for the agency. The GCDP manages over 30 projects that focus on everything from nanotechnology and lightweight materials to nuclear systems and solar electric propulsion. The hope is that with enough support, the GCDP-managed technologies will eventually be used to help create innovative new space technologies for our nation's exploration, science, and economic future. One of the first technologies they chose is from NASA's Robotics and Autonomous Systems and is located in this lab at the NASA Johnson Space Center. Here, a small team of highly motivated young robotics engineers are working on an idea that has the potential to help astronauts on long-duration missions and may end up changing the lives of millions as well. One of the first Space Technologies GCDP projects we will explore is located in this lab at the NASA Johnson Space Center. Here, a group of NASA researchers have come up with an exoskeleton that they call the X1. It has the potential to solve some major problems for astronauts on long-duration missions. This 60-pound assisted mobility device is worn on the legs of the wearer and is used to assist them in various ways. To understand why NASA is interested in a device like this, you have to understand a little about physics in space. A major problem faced by astronauts in space is bone loss and muscle atrophy due to a lack of use. Generally, on shorter trips, the bone and muscle density problem can be easily managed, but longer duration missions pose a much greater threat to crew health and performance. Here on Earth, we use our legs every day to walk around. But on orbit, the astronauts are in microgravity, so muscles and bones, especially those in the legs, aren't being used as they would be normally. Because of this, muscles weaken and bones begin to lose their density. As a result, some astronauts come back to Earth with up to 30% less bone structure in their legs and with significantly weakened muscles. To combat this, NASA doctors prescribe a strict regimen of exercise on orbit, but there is only so much that can be done. Generally, there is a treadmill and other bulky devices used to keep in shape, but these only provide limited success. The X1 may be able to change that.
I guess one of the biggest things for NASA and their astronauts is keeping their astronauts safe and keeping them fit and keeping them in good shape. We're looking at in the next few years, we're going to start sending astronauts to the space station for year-long missions instead of just 6 months, right? And so how do we keep them fit? How do we look at muscle density loss and bone density loss and muscle atrophy and things like that? If we look at a device like this, look how much, you can see how much smaller and compact it is. And this is really going to hopefully pave the way towards smaller technologies for countermeasures that we can use when we're in a smaller capsule and we want to go back to the moon and out to Mars. So the goal on space station, we're looking at two different things right now. We're looking at it for dynamometry applications, which is basically measuring muscle strength. And so we've been working with the Human Health and Performance Group and saying, wouldn't it be great if we had a device on space station that we could use to measure muscle strength while they're up there? Because they don't do that right now. So now what we're looking at this to do is say, you go use ARED, you go use the treadmill or the stationary bike, and then maybe once a month or once every 2 weeks, you use the X1 as a dynamometry application so we can measure your muscle strength. And we can really start to close the loop with the physicians on the ground and the prescriptions of exercise that they're giving the astronauts to see how effective they are. At its core, it's a mobility assistance device. So you can imagine that when we go to Mars, no matter how much you exercise along the way, you're going to be very tired when you get there. And so now maybe we can use this not only for exercise, but you can use it for mobility assistance when you get there, because you're going to be weak. All your joints that are actuated, you can use them to resist you, or you can use them to assist you.
NASA is very interested in the X1 for use in space, and this same device could also be a game changer for anyone who needs rehabilitation, like stroke victims. X1 could be even more life-changing for paraplegics. Early on in its development, the team partnered with the Florida Institute for Human and Machine Cognition. This group has been working on a mobility device that could serve as the legs for wheelchair-bound patients.
At that time, they had their own exoskeleton that they had developed called Mina V0, and they were really focused on mobility assistance, helping persons with paraplegia get up out of the wheelchair, walking again. And at that same time, we had, Robonaut, which we had just flown to space station. We worked on all this hardware. We developed all the actuators and all the mechanical and electrical assemblies for that. We developed all the safety systems in order to be able to send it to space station. And so we said, well, why don't we come together? We take that knowledge that we have about building these structures, and we'll take the knowledge that you guys have with assisted mobility and your high-level software, and we'll come together and build X1. And so X1 is really about improving life for people here on Earth and in space.
The X1 has the potential to change the lives of anyone suffering from limited mobility. When asked, many paraplegics say just being able to stand, reach the top of a shelf, or have a conversation with another person at eye level can improve their quality of life significantly. Much work is going into the X1 to make it accessible to as many people as possible. It is relatively lightweight and has been designed in a way where it can be adjusted to fit many different body types. And for persons who have lost their ability to walk, there's also a pre-recorded walking gait that can be adjusted to help them learn to walk again. In this iteration of the X1, paraplegics must still use crutches to help them balance and walk. But the hope is that the technology will develop to where the device can be utilized without crutches.
You know, my mom has multiple sclerosis, and she is 80% kind of confined. And for a device like this to help her, that's something that she looks at saying, I wish I could have that. But in 10 years from now, people won't be saying that. I think people will be saying, oh, let me go get that out of my closet because I'm ready to go out and walk around.
Sometimes technologies develop slowly and incrementally, and sometimes things happen all at once. To term the tipping point. I think with this type of technology, we've actually found a tipping point where the actuation technology is there, the computation technology, the applications for spaceflight, and the willingness and people's interest in this type of technology. And all these things converging at once, I think that's what makes something, that's how the game has changed. All these technologies happen at the same time, and people are grasping that opportunity to really to make a difference. And so it's not only changing the lives of astronauts, improving their health, but it's also improving lives here on Earth. We feel that it's not just game-changing, it's actually life-changing.
Spaceflight has many obstacles, one of which is weight. Any mission off this planet has a weight restriction. NASA has estimated roughly $10,000 per pound to get something into orbit, so weight reduction is a huge factor. If manufacturing costs could be brought down as well, millions of dollars could be saved on each launch. The challenge of creating low weight and less costly launch components is very attractive. The Game-Changing Office is taking this challenge very seriously and has created a composite cryo-tank to offset additional weight and possibly save money. Current propellant tanks are made from metals like aluminum. As the name suggests, the composite cryo-tank is being made from a strong, lightweight composite material that have a huge upside when talking about saving weight and money.
We start out the project looking at 30% weight savings over traditional state-of-the-art aluminum or aluminum lithium tanks. And we did a phase 1 activity with 4 contractors before we down selected to Boeing for phase 2. And out of that studies that we had, we were getting anywhere from like 35 to 40% weight savings. Every pound that you save in mass on a launch vehicle, you get that savings in payload. And it's depending on whether you're, at the core stage or an upper stage, that ratios vary. But you do get significant savings. So you get more performance, you get more capability, or you get increased payload.
The process of building the cryo tank is not only cost effective, the weight reductions could ultimately save millions during a mission. Current composite materials are cured in large ovens called autoclaves. This process can be very expensive, but NASA's composite cryo tank is being developed out of autoclave, making it much less expensive.
Saving the out of autoclave or the autoclave expense, meaning that normally you have this huge tank and it's a composite and it's got all these materials that are in it, and you have to cure it in a huge oven. you got to maintain the oven, you got to buy the oven, you got to procure the oven. So if you can find a way to manufacture with the same technical integrity as a tank that's gone through the autoclave, outside the autoclave, you can cut development costs significantly. 30%, I think, is the number that they're saying. And not only development costs, but recurring costs. You make these tanks, it doesn't have to go into an oven.
The way it works is a fiber placement head on a robot is programmed to lay down the material exactly where it is needed. This new process reduces costs, time, and most importantly, produces a better product. Because all of this technology is relatively new, the NASA team is using a process called the building block approach. First, they test small coupons or pieces of the material to make sure that it can measure up to expectations. It is then made into larger pieces and tested again. The project is currently at the point where a scale model 2.4 meter tank is being tested, with the eventual goal to build a full-scale tank to fit on a launch vehicle. The current 2.4 meter section is located here in this silo in the west test area at the Marshall Space Flight Center, under the shadow of test stands for the Apollo engines. Engineers have placed a foam coating over the tank and will then test it in a way that would be expected on a launch vehicle.
We put the tank through the exact conditions that it would see in the launch vehicle. So we fill it with the cryogenic material, in this case it's liquid hydrogen, and then in the case of a launch vehicle, we may have to empty that. So we would fill and drain, pressurize, unpressurize, all to determine how the tank reacts to those conditions and loads.
With this test completed, engineers can look for problem areas, fix them, and then move on to building the larger tanks. And if successful, this game-changing process can be adapted to other parts of a launch vehicle, making it more lightweight and less expensive. These are just a few of the ideas that are being worked on by the Game-Changing Development Program Office. But many more innovative ideas and technologies are being moved through the game-changing lane each day. And with each new development, change is coming to NASA that is allowing the agency to rapidly infuse technology and make smarter decisions about how to move forward and create different approaches while changing the culture. Much of the credit for this positive change can be placed directly at the feet of Space Technology's Game-Changing Development Program Office.
Personally, I would love if 5 years from now somebody said they really changed the game. They made a difference for NASA. That's all I'd need to hear.
Okay, 3, 2, 1. Well, I've been lucky enough to spend exactly 1 leap year on the space station, 366 days. So you can imagine that in 366 days, you get to see the Earth quite a bit. Even though we are so busy on the space station, we do try to look outside and glimpse what's flying below us any chance we get. was a part of me, the dreamer, the little kid that started dreaming about this whole experience now basically 40 years ago. That part of me was still there, unchanged for 30 or 40 years, and just marveling incredulously at the beauty of it all. And I would see clouds and green and rivers, and it would just completely fill my eyes. The difference in observing the world or the universe from inside the space station, looking through the windows, or being outside, is what I describe as the same level of interaction that you can have looking at a beautiful aquarium from the safety of a room. When you're outside and all you have is a helmet and maybe 1.5 inch of plexiglass in front of your eyes, you can see details and colors and shades, the level of detail that you can capture and the way you experience that universe is going to be very, very different. You want and you feel that you have become part of it, and you can develop that sense of belonging. I think that the first impact of the first flight was that I did see and I did sense how fragile, how small the Earth is. We are used to think of the Earth as something so vast and big, and we don't think that what we do, our daily life, can affect such a vast system. But from space, you get a sense that every individual, every living organism is somehow connected. Seeing the city lights at night, where a place like Europe or the United States or Asia, densely populated, everything is so interconnected, and all those lights and all those lives are apparent. They are right in front of you all together, and you think that all we are doing somehow as an effect on everybody else. You come back from an experience like that thinking that that's what's happening, and then you can see the effects, both the positive ones but mostly the negative ones, in a second flight. And I think you have to acknowledge and grow an awareness, and with that awareness comes the desire to share the experience and share that awareness. It's understanding that the science that's telling us how we are changing and influencing the world has solid mathematical and solid mathematical base. And then you see the effects of it and you just interiorize it. You make it your own experience. And I think that that's what happened. That's why astronauts develop that awareness of and the desire to help the environment somehow, in any way they can.
Wherever, however, whenever. We're here, there. We're everywhere. NASA Space Communications and Navigation. Exploration enabled.
We are going to the moon to stay, and this is how.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
Alright, good morning everybody. Roll call, got the pilot, got the co-pilot, GEOC operator, mission director. Alright, flight mission crew, FCIFs are complete and flight currencies are all checked. Crew schedule has been published. We're NASA 872. Engine start expecting 0600. Estimated landing of 07 tomorrow morning. Subdivision durations approximately 24.
All right, thanks everybody.
I didn't ignore your email.
First number.
Hawks are strong, powerful birds capable of flying thousands of miles each year. Some species undertake long migrational journeys, a testimony to their strength and stamina. Our bird will fly over 10,000 nautical miles and will reach an altitude of 65,000 feet.
Preparation for an HRX flight starts a couple of days before the flight, where we get together and look at the meteorological forecasts and decide where to send the aircraft.
Those targets are determined by the circulation of the atmosphere, which varies from day to day.
And so we design a flight based on meteorological data to go down and sample in near the tropical tropopause, so what altitude to sample, also what latitude and longitude to sample.
We're looking at all the areas where the scientists want to fly, and we coordinate those areas with the Federal Aviation Administration.
We work with the scientists beginning at that time to come up with options and a plan to get them what they need. We try and maximize the time that we spend in the air.
For this experiment, we're focused on regions where temperatures are cold because we're interested in high altitude clouds. These clouds are about 10 miles or 16 kilometers above the surface.
When all the instruments are ready for flight and everything's been checked out and the aircraft's been checked out, and we button up all the hatches and we're ready for flight.
24 wind calms, altimeter 2984.
Once everything is ready in the control room, we give the OK for engine start.
Got control panel, secure the aircraft to shores.
So we're ready for aircraft taxi prep.
Copy and work.
Center line, 22 left.
Roger.
And Trapper, can I get a take-up report?
Yes, sir. Runway's clear. You go for takeoff.
Roger that.
40 knots. 80 knots.
Take off. Ready now.
And payload admission, this is data, KUSI.
We fly it with a mouse and keyboard, and it's more like flying an airline that's always on autopilot.
Well, with the Global Hawk, we have these same controls, only we're just on the ground, and the aircraft could be, several thousand miles away.
Rather than pointing the nose in any given direction or setting a throttle for a particular power setting, we just tell the aircraft, go to this heading, go to this altitude, go to this airspeed. The system itself decides on the best way to get there.
And one of our challenges is to kind of understand the contingency state that the aircraft is in and make sure we understand what the aircraft is doing, and that's what we truly want the aircraft to do.
Most of the time the aircraft is flying in what we call a cruise climb mode. It's actually full throttle in a climb. It gets up to a maximum altitude and then it has to wait to burn fuel off, and as the aircraft gets lighter, it goes a little bit higher and a little bit higher, up to a maximum ceiling of about 65,000 feet.
Come easy left. Roger, release and then turn.
One of the things we do during these flights is we have a meteorological team, a team of forecasters down the hall who are watching the satellite products and telling us where thunderstorms are, for example.
There might be colder temperatures south of Hawaii versus just off the coast of South America or Central America. So we have to know where to direct the plane. So we look very carefully at the meteorological situation first. Then when they're in the air and you're flying along, oftentimes these forecasts are wrong.
So when the atmospheric conditions change during the flight, when we're out over the ocean, a lot of times there's a request for us to change our flight track. Maybe the area that they're interested in is in a different area. So one of the things that we will do is coordinate that flight change.
We will use the information we're collecting as we fly along to redirect the plane.
If you'll notice up on that forward deck of the airplane, there's a big white 48-inch dish. That's a KU, a commercial KU SATCOM dish, and that is constantly pointing at the satellite that we have subscribed to for the missions.
We actually get extensive data transmission from what the instruments are measuring in flight.
We decide, based on what we see, to send the aircraft somewhere else or to have it go down to different altitudes.
The classic case, as I said, is you look down, you see a cloud on the LiDAR, and you say, we're going to turn around, descend into that cloud, and sample it.
So we'll profile down through these thin clouds, making measurements of not only water vapor, but the temperature and the pressure, and a range of other gases, including ozone, chlorofluorocarbons, and so forth, so that we can understand the movement of air and the behavior of the air in that layer as we dive down.
One of the great things about this is being that our ground station is building based and we have all of the scientists in the back room. We always fly with 2 pilots. This gives us the opportunity for one pilot, the mission commander, to get up, go to the back room, leave the other guy to monitor the airplane, and we can talk with any one of the particular scientists, whoever has the most important data that they want to get at that particular time, and we can work directly with that scientist, sit right down at the table with him or her, and decide what's the best way to get them what they want and still meet everybody else's needs.
Obviously, the pilots fly the plane. They're the ones who are talking to ground control, but the pilot has to know where to go, and that's where the scientist's role comes in. The scientist will pick the targets and direct the plane towards the appropriate targets, both before we fly and while we're flying.
It's quite a process because sometimes it can mean a major shift in the flight track. So we will look at what they have proposed and provide some feedback, and then we have to talk to air traffic control to make sure that what we're proposing is okay with them. So we'll change the flight track sometimes many times during a flight.
And so that's how we coordinate between the flight operations team and the payload operations team. So it's a very close collaboration during a flight between both groups.
Very interesting for me too, because coming from a platform where we would just have instruments loaded on the plane and we just go fly a mission, we get real-time interaction with the scientists, and I've learned a whole lot just in the few years I've been doing this on what's going on in the back end of the airplane. Very exciting and very interesting.
872 is coming right, hot pass. 30 seconds.
Well, what next and what's important to do?
We hope that HREX will improve our understanding of this part of the atmosphere, but ultimately HREX will raise some additional questions as well.
We have a lot of work to go, and we hope that doing HREX with multiple missions, different times of year, in different parts of, mostly over the Pacific, but into the Indian Ocean, to fully understand the range of conditions that we'll see, that models have to consider all of those ranges of conditions in order to understand the climate system properly.
We need to develop some more instruments and fly them on Global Hawk and other high altitude aircraft to make measurements there as well.
Emily Dickinson once wrote, "The brain is wider than the sky." Many questions have been addressed along the way, and new ones have surfaced. We'll keep searching, for the answer is in the air. Carl Sagan once defined the Earth as the pale blue dot. "70% of its surface is covered by water. Life on our planet began in the oceans some 3.5 billion years ago. Since then, water has been an essential component for us. In fact, 2/3 of our bodies are made out of water. We can't imagine life without it. As far as we know, without the presence of liquid water, life is not possible at all. Water is all around us. It's not only in our oceans, but we also find it in rivers, lakes, ice, rain, clouds, even in the air we breathe in, as it's continuously evaporating into the atmosphere.
Water is important for all life. We wouldn't have life on this planet if there wasn't water. When astronomers try to think about other planets and whether they have life on it, the first question to ask is there liquid water?
We have liquid water covering nearly the entire planet, 70% of the planet covered by water. There's water in our atmosphere, in the air, all around us. You don't find any place, any chunk of air in the atmosphere that doesn't have some water molecules or some ice particles or some water droplets in it.
Without water as part of the climate system, we would have wild temperature swings in our atmosphere that would probably make any planet uninhabitable. So water is a key driver.
So water is everywhere. Now, the way water begins, of course, it's a liquid out here, and the sun beats down on the surface and it warms the water. It evaporates it. Just like on your stove, you put your pot of water and your heating element below it heats it up and it boils off. You get steam or you get water vapor. Same way that the sun's energy will warm and evaporate water. That water rises in our atmosphere, and as it rises, temperatures are cooler aloft, and so you form clouds. Clouds are water particles. They're little liquid water particles. Some are very tiny, and they float around as clouds. They can also freeze and form ice particles, and those ice particles float around. Those are also clouds. As the atmosphere moves that water vapor around and those cloud droplets, they fall out of the sky and they come down on the surface and they feed our lakes and our streams. They make the soil wet so that crops can grow. Water is really a fundamental part of our planet. It goes back to the oceans and then it goes through this cycle again. So you get this constant heating up of liquid water, becomes a gas. It precipitates out onto the land, and it drives this, what we call the hydrological cycle.
So as water comes into the atmosphere, it has a number of effects. So it helps to make clouds, it helps to make rain, but water is actually a very important greenhouse gas.
Also, water carries energy with it. It takes a lot of energy to evaporate water. And then when water forms cloud droplets, it releases energy. So water is a big component of not only the hydrological cycle, the movement of water, but the energy cycle of the planet also, because it's a greenhouse gas and because when you evaporate water, it carries a lot of energy.
So the way it works is when we change the atmosphere, put more carbon dioxide in it, it gets warmer, and that allows the atmosphere to hold more water. The water is also a greenhouse gas, so that increases the temperature further, so it's a feedback effect.
Water, being a strong greenhouse gas, will actually amplify the greenhouse gas effect from these other longer-lived species like carbon dioxide and methane. So that's a very strong positive feedback loop which would keep driving the temperature up.
Or you could create more clouds and reflect more energy back to space, which is what we call a negative feedback.
So we have this complicated interaction between the positive feedbacks from the water vapor itself versus the clouds that it forms, giving you a negative feedback. And finding that right balance, that's part of what we're trying to understand with the entire hydrological cycle in the tropical part of the atmosphere.
And it turns out about half of the change in temperature of the atmosphere right now and the change predicted in the future associated with the increasing carbon dioxide is caused by this water vapor feedback.
Water comes and goes, and that's driven purely by the physics of how water works. It's a reactionary greenhouse gas as opposed to a longer-lived stable greenhouse gas. But water's the big player in the entire feedback loops of how the atmosphere works.
So it's very warm here in the tropics, and it's very moist. And so the air down near the surface has a lot of energy in it.
So deep convection in the form of thunderstorms and typhoons actually are more energetic. They go to higher altitudes.
And so it can go quite high. We see these big thunderstorms that develop, and that's this air being funneled up, just like a boiling pot of water. The air gets funneled up into the upper troposphere here and actually go very high.
And so that extends the troposphere upward to higher altitudes, and the temperature keeps decreasing as you go up, and so it's colder.
And so eventually, most of the water gets frozen out as you get up to these altitudes of 50, 60,000 feet. So it's incredibly dry, even though down at the surface in the tropics, it's very wet and moist. It's very high humidity, it's damp. When you get to 55,000 feet, about 16 kilometers up, it's incredibly dry.
You still get some water making it up to the tropical tropopause, and there the atmospheric motions transport air into the stratosphere. So air is transported into the stratosphere with a small amount of water that's left behind, and that's controlled by the temperatures at the tropical tropopause. So if the tropopause is colder, less water will make it into the stratosphere. If it's somewhat warmer, more water will make it into the stratosphere.
Above us, up at 40, 50,000 feet in the tropics, the atmosphere is going to warm up through this century. And because of that, there will be less freeze drying of this air going up. And so the thinking is that water might go up. Now, water is a powerful greenhouse gas, so if water increases at those higher altitudes, it will act to trap more energy at the surface. So it could cause the temperature to actually go up higher.
Climate change will have huge impacts on food supply, on ocean levels and flooding of coastal regions.
So it's important to understand, put all of this together to understand how water will change through the next century.
The more we understand the processes, the better off society will be because of it.
ATREX, when studying the tropical tropopause, is addressing a key uncertainty in our ability to predict future changes in climate in response to human influences.
It is believed that Guam was first discovered by seafaring people who migrated from Southeast Asia around 2000 BC. When Portuguese explorer Ferdinand Magellan arrived at the island in the 16th century, he found a highly stratified society, experts in the art of sailing and skilled craftspeople, the Chamorro. Since then, numerous expeditions have investigated this region of the Pacific, yet there are still many discoveries to be made and places to be explored. Although this time we'll be looking up, way up into the sky.
Attention on that, engine start on my mark.
That's number 7324. NASA 872.
My land cover career really started in 2002 with biggest wildfire in Oregon's history, and that was the Biscuit wildfire. I, at the time, was doing botany surveys and looking for rare plants or rare mushrooms, and so I was spending a lot of time out on the forest looking at and taking photos and doing the documentation that a scientist or a land manager does. When that fire happened, it changed everything, because we all had to react to this fire that was burning up some of the places that I'd literally been the day before. And it was mapping what was there and what was under threat, but it was also mapping the effects of the fire. We needed to find a way to look across 500,000 acres. And the only way that we could really do that was satellite data. If we can't get out and actually measure every single thing, what are we missing? And that's where citizen scientists can actually come in and really help traditional scientists to better understand what is happening around them, but also fill in these gaps.
The Global Learning and Observations to Benefit the Environment program is an international science and education program. It provides students and the public with the opportunity to participate in data collection and the scientific process. The Globe Observer app is one of these opportunities, allowing citizen scientists and students to take land cover observations around the world and submit them to a larger database. But what exactly is land cover? Dr. Eric Brown de Colston of NASA's Goddard Space Flight Center explains.
Land cover is really the basic form of the landscape that we have around us. So whether it's a forest or a desert, but it's really one of the components of the landscape that we can study from space.
Dr. Peter Nelson is a scientist who uses land cover imagery in his research.
I am a remote sensing scientist who studies land cover across the globe. I use satellite imagery to make maps of land cover and try to quantify what covers the Earth. Sometimes a satellite can't see what's happening underneath a tree canopy or what's happening underneath cloud cover. And so we really need people to go out there and to take these photos, to do these observations, to help fill in where a satellite can't actually make some observations.
Just like any digital photograph, land cover images are made up of a series of pixels to show what covers the Earth. A pixel, or picture elements, is the smallest unit of a digital image. When combined with thousands of other pixels, a picture is formed. Each pixel color shown represents a land cover type. It's from these pixels where ground verification or ground truthing come into play. You see, depending on what satellite is taking images, a pixel can cover roughly an area of 30 to 500 meters squared. For imagery captured by Landsat, a pixel is 30 meters squared, or about the size of a baseball diamond. However, part of that pixel showing forest might actually be water, or shrubs. By taking land cover observations, citizen scientists can help answer these questions when it comes to land cover maps. So, why are these land cover observations so important? Why are they taken in the first place?
We also are looking at how these components are changing over time. So deforestation in the Amazon or across the world, how are cities expanding? A lot of different things to study, and really the view from space is the way that we do it here at NASA. We have big supercomputers that simulate the physics of the atmosphere and the land, the interaction between the Earth systems. It's important to have that, that land cover map. It sets certain parameters. Those models can actually be used to look at current day conditions and weather. So based on these current conditions, what might the Earth look like 50 or 100 years from now? There's an element of understanding, but then also being able to predict into the future, what that might be like, what these changes may mean for us.
Each point shown here represents a real-world measurement of environmental conditions. Scientists use computer models to fill in information where measurements may not exist. By verifying the satellite imagery and using the data for these models, scientists can predict changes in our environment more accurately. One of these scientists using land cover maps to track urbanization as part of her work is Dr. Amita Mehta of NASA's Goddard Space Flight Center.
So urbanization changes terrain as well as characteristics of the surface itself. And so impervious surface is what we look at when we are monitoring flooding. When there are, say, parking lots or cement and concrete surfaces, they increase. So previously, if it was a farmland or something which was not built, and if that is built now, that water previously that could go or percolate in the soil and in the ground now cannot go in, and it stays there. Monitoring helps you to plan for it. So if you see land cover changing, even then you know that how water is going to flow in that region might change. If you have to send rescue out or you have to plan for relief activities, then if you know land cover, then you know where there might be help needed.
By using land cover maps and models that reflect changes over time, scientists can predict where flooding and other events may occur. With a changing climate, these predictions from models and land cover maps can help scientists better understand these changes and help communities prepare for them. But perhaps a more important reason as to why take land cover observations is you get to participate in a community of scientists, citizen scientists, and students.
So it's a very important component that the citizen science and students of the GLOBE program and GLOBE Observer can contribute to, is by really giving us the information on the ground of what they're seeing around them and in front of them. And we hope over time as well how maybe some of these things are changing, because those would be very valuable for science.
I saw the value of having information before a hazard happens, because once that fire went through an area, we can never recreate that data. This is all important for us to share and put together, because that's how we understand Earth as a system. All of these things end up affecting where we live, why we live where we do, and why we make some of the choices that we do.
To learn more about Globe Observer, check out the website at observer.globe.gov and download the app to start taking your own observations today.
report range status. Range green.
T-minus 5, 4, 3, 2, 1. Go for main engine start. 0 and lift off.
These are not the best of conditions, but for these knights of the highway, hauling a multi-million-dollar spacecraft more than 800 miles is all in a day's work. They're carrying NASA's next planet hunter, TESS. TESS stands for Transiting Exoplanet Survey Satellite. Its job is to search for habitable planets outside our solar system, but close enough to study. That's because we're not just looking for planets, we're looking for life. And the first leg of this spacecraft's journey to orbit is the ride to NASA's Kennedy Space Center.
So we left yesterday at Dulles. We left at 10:15 in the morning. We ran into an accident on 95, horrible weather, rain, down through Richmond.
The 16-hour road trip from Virginia to Florida wasn't easy, and protecting this one-of-a-kind spacecraft during its move was vital. Its shipping container is designed to keep TESS safe on the road.
The case gets used for a number of missions. It's mounted on some shock-absorbing bumpers so that we don't see a lot of the road noise getting into the spacecraft while we transit. We don't want any humidity inside. We don't want the temperature to change, so we have an air conditioning system as well. So we're just trying to keep it environmentally stable on the trip. And then we have very sensitive science instruments. So we actually provide a nitrogen purge. We spray nitrogen gas in to make sure that no air gets in contact with some of the sensitive components.
TESS has safely made it to Kennedy, where it is immediately taken to the Payload Hazardous Servicing Facility. But the job of keeping it clean is far from over.
TESS has really strict contamination control requirements. So what we've done is created a clean enclosure inside the high bay that acts like a clean room within a clean room, basically.
This is a unique mission full of first-time events that are sure to be a challenge.
TESS isn't like another mission. We haven't done another TESS. This is the first of its kind.
The time has come for this diverse team to put years of planning into practice as they begin the countdown to T0.
We've had a period of hard work that lasted for years, and when we finally get to the point of launch, it's very exciting. This is where the fun begins after we've gotten through all the early legwork and the planning, that we are actually going to now prepare a spacecraft for launch.
Building on the groundbreaking discoveries of the Kepler mission, TESS has scientists across the world excited about its possibilities.
TESS is probably one of the most interesting spacecrafts that I've ever worked on in my career, because of the science it's bringing back down to Earth. It's taking science fiction to science fact.
TESS will use the transit method to hunt for the telltale signs of planets orbiting other stars. In the transit method, the spacecraft watches the sky, and when a planet passes in front of a star, the star's light briefly dims. But Kepler only looked at one portion of the sky. TESS is taking this search to a whole new level.
What TESS is going to do is look around the entire sky around us to find stars nearby, much closer, 10 times closer than Kepler.
The really exciting part about this is it's the first all-sky survey of this type, using the transiting method to look for Earth-sized and super-Earth planets.
I think the real interest by the public in exoplanets is that everyone has a dream that there's an Earth analog out there, another planet that has the ability to have an atmosphere and water and sustain life on it. That, of course, is the ultimate sort of goal of exoplanet science.
When all the pre-launch tests, inspections, cleaning, and checkouts are done, it's time for TESS to join up with its launch vehicle, the SpaceX Falcon 9 rocket. This is a critical process, and it begins with encapsulation. This is the Falcon 9 payload fairing. Its smooth aerodynamic profile will give TESS a safe ride through the extreme heat and pressure of the climb to space. The vehicle systems engineer in NASA's Launch Services Program plays a critical role in bringing the spacecraft and rocket together.
We have our hands in just about everything. We have to know enough about each system to know how they all interact together, and we have to know how the vehicle operates as a whole. So that's how critical the vehicle system engineer is in this whole process. We've been working very closely with SpaceX from the start. Even when during their design phase and going through the whole certification process, the vehicle system engineer was integral in that role to understand what's going on with the SpaceX launch vehicle and how the NASA team can supplement a lot of what's going on.
The fairing is in one piece as it arrives at the door to the high bay. Inside, the test spacecraft is ready and waiting for encapsulation.
What's exciting about encapsulation is it's one of the last few things we do to prepare the spacecraft to get ready to go on the launch vehicle. It's exciting because you know we're going to be launching in a few days, which is the most exciting part of working this mission for the past couple of years.
TESS has to be ready for prime time when it gets into orbit, which means the last of its covers used during processing have to come off. Once TESS is inside the fairing, it won't be seen again on Earth. The payload fairing has been opened into two halves, and they're positioned on either side of TESS. The spacecraft is surrounded. Slowly and carefully, the fairings are moved into position until TESS is locked inside.
The encapsulated decision has just been completed. Right now they're getting ready to lift the spacecraft, the encapsulated spacecraft, onto the trailer, which they'll then transport to the launch site. And from there, they'll make the encapsulated spacecraft to the launch vehicle, and at that point, that's the last major thing before we get ready to launch. And that is exciting.
A specialized transporter rolls into the processing facility's high bay. It's here to take the payload fairing and its precious cargo to be attached to the Falcon 9 rocket. Getting TESS to this point was no small feat. It took several teams working closely together to ensure every system and every piece of hardware are ready for this mission. With the crane doing the heavy lifting, the fairing rises off the floor. It's guided toward the transporter, with team members helping every inch of the way. The fairing must be attached securely to the transporter for the final miles of its journey on Earth. There is no margin for error. The Falcon 9 rocket is waiting.
The Falcon 9 for the test mission is a new launch vehicle. We are planning to recover the first stage from the test mission on the drone ship, Of Course I Still Love You. If successful, this will be the 24th successful booster landing for SpaceX. By recovering first stages, not only do we understand more about our launch vehicle, it also enables us to reuse and refly that hardware, which is a key part of the SpaceX mission.
The fully assembled Falcon 9 rocket, with TESS on board, rolls out of the hangar at Space Launch Complex 40 at Cape Canaveral Air Force Station. Its final stop, the launch pad.
The SpaceX team is really proud to be part of such a cool mission, the TESS mission. The TESS satellite is looking for planets outside of our solar system in our galaxy, which aligns very well with the SpaceX vision to make life multiplanetary. To prepare for the rocket to be vertical on the pad today, the engineering team in the hangar did those final last checks. We mated the fairing to the rocket, and once the launch vehicle was finally checked out, the rocket rolled out of the hangar late last night and went vertical early this morning.
TESS is healthy. The Falcon 9 rocket stands ready. It's time for the final countdown.
So launch day is a pretty incredible day. Those last few minutes, you're just holding your breath. You find yourself holding your breath until, you get that T0 count. I lead a team of LSP engineers to successfully launch our spacecraft into orbit.
The SpaceX team has partnered with the NASA Launch Services Program, NASA Goddard, Orbital ATK, and MIT to enable that planet-finding mission.
We go on console about maybe 3.5 to 4 hours prior to launch. We do our voice checks to make sure we can activate and we have all the voice channels that we need to listen. We're listening to, at any one point in time, maybe 6, 7 voice channels at the same time, so you're kind of training your ears to listen for your call sign. The team has a great responsibility to be able to look at all this data and say, yes, we are go for launch.
LD, go for launch. Falcon 9 is in startup. Falcon 9 is configured for flight.
3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS.
Status check to proceed with terminal count.
There is a moment at the start of every mission when everything comes together. A moment when years of preparation and planning are put to the test.
Clear to proceed.
There are no second chances.
You have permission to launch.
Success or failure is just a heartbeat away.
Rock report range status. Range green.
A spacecraft and its rocket on the pad, fully fueled and ready to launch.
Status check. Go Atlas. Go Centaur.
In that moment, a controlled explosion is released with such intense power it can propel a spacecraft off the Earth and into space for the benefit of all. We call this moment T0. This is its story. NASA is about to do something we've never done before. Nestled along the mountains on California's central coast is a little talked about space launch center known as Vandenberg Air Force Base. From here, history is about to be made.
This is the first time we've had an interplanetary launch from Vandenberg Air Force Base in California. The cool thing about this launch is that we've got such a capable rocket, the Atlas V, we don't have to launch from Florida.
InSight is going to be the first time that we've had a spacecraft leave Earth's orbit launching from California. We've actually done studies for it, even up to decades ago, but it just comes down to whether or not the mission had extra propellant left over and whether there was an operational reason to switch from an East Coast launch to a West Coast. This is just the first time all of it came together.
What we're going to do is we're going to unload the spacecraft really carefully, and then we're going to drive it a couple of miles to the Astrotech facility where they have a clean room all set up for us. We've got about 2 months here. All we got to do is clean it up, test it out, put the fuel in the tanks and bolt it on the rocket, and off we go to Mars.
InSight is NASA's next groundbreaking mission, literally designed to break ground on Mars. Using probes and seismometers, InSight will listen for Mars quakes and measure how much heat the planet's interior gives off. If we're going to truly understand how rocky planets like Mars and Earth were created, we need to look inside.
It's unlike other missions that we've done to Mars. We have a number of orbiters, a number of landers that we've successfully explored this amazing planet. But this actually is the first mission where we're really looking on the inside, the inner space of Mars.
Sending a science mission to the Red Planet is never easy. Landing a probe on the surface is even harder. To accomplish this, InSight will have to shed its many components in a matter of minutes, bit by bit, like peeling an orange, until only the lander is left.
So the cruise stage itself is the critical component that actually gets us to Mars. There's an aeroshell that absorbs the heat as we re-enter the atmosphere. That aeroshell enables us to go through the atmosphere of Mars successfusly without getting the inside, the lander itself, too hot. We deploy a parachute. That parachute does two things. It really ensures the stability of the aeroshell as it's starting to get closer to the surface. It also slows down the spacecraft further until finally we drop out of the combination backshell and parachute, and then we do a propulsive descent down to the surface.
We know water exists on Mars, and where there's water, there could be signs of life. But we must ensure any organisms we discover weren't simply stowaways from Earth. This is where the Planetary Protection Team comes into play.
Planetary protection is what we do to responsibly explore other planets and moons in our solar system. In order to do that, we need to make sure that we send a clean spacecraft there. We would hate to get to another planet or moon and think we discovered life, but it was actually something that we brought with us. So we collect our samples on InSight, any part of InSight that's going to land on the surface of Mars. We bring it back to our lab and we process it using a NASA procedure. If we run into a situation where we take a sample and it comes back as having a higher number of bacteria than what we want, then we make sure that the engineers go back and clean those surfaces with the whole idea that we don't want to cloud our ability to potentially find life on another planet or moon.
Lockheed Martin Space of Denver, Colorado, built InSight with an extremely efficient design, streamlining what needs to be done at the launch site. They shipped the spacecraft to Vandenberg with no assembly required. Simply check it out, fuel it, test it, encapsulate it, and it's ready for launch.
The processing for our spacecraft has been very smooth. A lot of the processing had to do with fueling the spacecraft, removing some remove before flight items. Everything else was pretty much already installed on the spacecraft in Denver, Colorado before it was shipped here. And that's called a ship and shoot, which means there's not too much to do except for to fuel the vehicle and do some last minute power on checkouts of the onboard computers and subsystems.
These preparations are crucial. Everything must be working perfectly before InSight leaves Earth. This effort is designed to ensure a safe arrival and landing following the 6-month trip from Earth to Mars. In the meantime, United Launch Alliance, or ULA, is busy at their launch pad, Slick 3, assembling the world's most successful rocket, the Atlas V.
Well, I mean, we're building a rocket. What's not exciting about that? And really excited to be able to launch the first planetary mission from the West Coast.
First, ULA stacks their Atlas V booster onto the launch platform. Atlas V is powered by the mighty RD-180 rocket engine. The RD-180 is a powerhouse, burning highly refined kerosene known as RP-1 and liquid oxygen for thrust. For this mission, the RD-180 has more than enough power to get InSight off of Earth and heading towards Mars. When the booster's fuel is spent, the Centaur second stage kicks in and finishes the job. Centaur won't actually hit Mars. It will fly just past it. Final course corrections will be done by InSight itself to enter the Martian atmosphere and land on the surface. Once fueling and testing is complete, the team from United Launch Alliance will encapsulate InSight inside its payload fairing, the shell that keeps InSight clean and safe during its dangerous ascent through Earth's atmosphere.
We're at the phase of the mission where we're encapsulating with the launch vehicle, and the ULA team with their fairings now come in and they take the two halves of the fairings and they make a clamshell around the spacecraft to help protect it for the environments that we see during launch. And we do that because as we leave the Earth's atmosphere, the air and the molecules in the atmosphere would tear up our spacecraft otherwise, and the fairing is there to protect us.
With InSight encapsulated in its fairing, it's time to move the payload out to Slick 3. But this California coastline comes with its own set of challenges. The surrounding marine layer can swallow up a launch pad, reducing visibility to under a couple hundred feet.
So right now, it's on the transport vehicle and it's ready to roll. And we'll be rolling out around 2 a.m. At that point, we'll have a convoy that drives very slowly from the payload processing facility out to the Slick 3 Atlas V facility. And once it arrives, we'll hoist the encapsulated spacecraft up to the top of the mobile service tower and place it on the launch vehicle.
This morning when it was sitting on the truck and they put the crane on it, they started lifting it up. That's the last time this spacecraft's ever going to feel the ground of Earth. I'm just kind of jumping out of my skin. This is so exciting. We're getting so close to launch, and it's been a long, long road for me. This has been a challenging program. I mean, we've had a lot of technical issues to overcome. We actually had to stand down back in 2015, but since then we've gotten it all together, and things have been going so smoothly the last year. We really feel really confident about this launch now. We got it on top of the rocket. We're going to blast it off in just a few days, and when it gets to Mars and lands, finally it will have solid ground under its feet again and get to work on probing the depths of Mars.
But InSight won't be traveling alone. Hitching a ride to the Red Planet are a pair of CubeSats, twin satellites called Marco A and Marco B.
So Marco is a dual payload riding as a secondary mission on its way to Mars.
So Marco is a pair of CubeSats, and CubeSats are really small spacecraft. They're essentially the size of a large cereal box, so about this big.
It's going to be relaying telemetry from the entry, descent, and landing of InSight back to Earth in near real time. After InSight is deployed on orbit and is heading to Mars, Centaur, which is behind me, ejects Marco A into orbit, and it'll slowly rotate itself so that Marco B ejects 180 degrees on the other side of the vehicle.
But Mako is a technology demonstration mission. It's actually one of the smallest spacecraft we've ever launched to interplanetary space. It's the first interplanetary CubeSat. So in of itself, it has all of these technology that we've never tested in deep space before. So if Mako works this time, one of the cool things that we could do is actually replicate that system and fly it with other missions in the future. And whether you're going to Mars or Venus or maybe even further away to an asteroid, you could think of it as bring your own telecom relay.
So everything went well today with the lift of the spacecraft and mate onto the rocket. It started off very foggy and windy, and right now it's a beautiful day, just typical California weather. And now we're ready to go to Mars.
But just as twilight falls across the base, the fog returns, cloaking the coast with a bone-chilling mist that will last until daybreak.
As we get closer to T0 liftoff time, a number of activities have to happen. There's a mobile service tower around the Atlas V rocket, and the InSight spacecraft is on top of the rocket, enclosed in the payload fairing. So we're going to back that mobile service tower away from the rocket to leave it exposed just beside the umbilical tower.
Stand engineer, proceed with MST roll to park position. Roger. MST boards shall be closed in park position. Roger.
The final launch pad preparation is underway. Once the mobile service tower is rolled back, InSight and Atlas V are just hours away from T0. Basking in the searchlights of the West Coast facility, they are presented with the glamour of a Hollywood premiere, fitting treatment for such an historical mission.
So there's a lot of excitement within the NASA launch team about the InSight mission. First time we're going to launch from the California coast, going to Mars. And what is really exciting to the team is this is the culmination of a lot of work. The teams have been working on this mission for over 5 years, and today is the day that they will see all of their hard work rewarded.
Status check to proceed with terminal count. Atlas systems. Propulsion. Go. Hydraulics. Go. Pneumatics. Go. LO2. Go. Water. Go. Centaur systems. Propulsion. Go. Pneumatics. Go. LH2. Go. Facility. Go. Range coordinator. Clear to proceed. Launch director.
LC, you have permission to launch.
Go Atlas. Go Centaur. Go InSight. Proceeding with the count.
We're at T-minus 8, 7, 6, 5, 4, 3, 2, 0. Liftoff of the Atlas V, launching the first interplanetary mission from the West Coast. And NASA's InSight, the first outer space robotic explorer to study the interior of Mars.
Seconds after liftoff, the rocket punches through the marine layer, lighting the night sky for miles, visible all the way down to Los Angeles. An infrared camera showing the long tail of the exhaust plume captures some of the ascent, as well as an onboard ascent camera.
And we're nearing booster engine cutoff, or BECO.
Back to 4.6 Gs in preparation for BECO. Boost phase cooldown has completed. And we have BECO. Shutdown looks good. Stage separation. We have box and fuel pre-start. GN2 purge firing. The RCS is underway. We have ignition and full thrust. And we have indication of payload fairing jettison. Looks like a good step.
And the payload fairing that was encapsulating the InSight spacecraft has been jettisoned. The RL-10C engine, the second stage of the Centaur, continues to burn.
An hour and 28 minutes into the mission, the InSight spacecraft and the Marco twins are deployed from the Centaur upper stage, beginning the long voyage to Mars, where InSight will go to work shedding light on secrets hidden in the depths of the Red Planet.
Hey there,
I'm NASA astronaut Ricky Arnold. Welcome aboard the International Space Station. Today we're going to talk about the Space Station truss. The truss segment is just about 100 meters from side to side. A truss is a segment or part of the whole integrated truss structure. The trusses are used to support the 16 solar array panels, which provide energy for us, and radiators which get rid of excess heat that builds up inside the space station. The design of the truss involves triangles and beams, which can be seen on Earth in structures like bridges. Why triangles? Well, this is because of their unique geometric properties, their methods of transferring loads, and their spatial openness. Triangles are more rigid than rectangular shapes because they have fewer joints. The larger number of joints in a shape, the more prone that shape is to being impacted by shear forces. What I'd like to talk a little bit about today is some of the forces that can act upon the truss. Well, the first force I want to talk about is compression force. And compression force is just like it sounds, two things coming together. So if we apply a compression force to the truss, what do you think is going to happen? Well, let me go ahead and do it. And you can see right here where the truss would bend. What do you think the opposite force of compression is? Yeah, it's going to be right. It's going to be pulling apart. We call that a tension force. And a tension force is what's going to help maybe even rigidize the truss segment, but it also could potentially pull it apart. I'm not going to pull apart this tape measure because we probably need it later for some work we have to do. Now, if you look carefully, this next force I want to talk about is basically kind of like a twisting force, and we call it torsion. And even when I just let go of the tape measure, you can see it will actually start to happen a little bit. You can start to see, because the center of mass is actually right here, where most of the tape measure is located, and when I let it go, the tape measure itself starts to twist just a little bit. Finally, the fourth force that can act along a truss segment is that can occur at a single point where two opposing forces work on a single point along the truss, just like they can upon the Earth's surface. Think about some earthquakes. You can have a plate that is, or along a fault line where one side of the fault line is moving upward or being forced upward, while the other side is moving downward. And that force in one point in opposite directions is called a shear force. And we can also have that happen on the truss segment. Something like this. One thing to think about, where do these forces come from? One force, even though we're up here largely out of the Earth's atmosphere, we do still have drag with the Earth's atmosphere, which can impart loads on or impart a force on the truss segment. Another, I already hinted at earlier, is crew working inside. We're up here, we're exercising, we're moving really heavy pieces of equipment around. So we have an amazing engineering team on the ground, and we have specific disciplines that their job is to monitor all the forces imparted upon the International Space Station. They keep track of all those various forces I talked about and where they could be coming from, the atmosphere, visiting vehicles, or even things that the crew are doing inside the space station, and to make sure that those forces aren't significant enough to cause any damage to this wonderful laboratory and living space we have up here in low Earth orbit. Thanks so much for joining me today. We'll see you next time. So long.
Wherever, however, whenever. We're here, there. We're everywhere. NASA Space Communications and Navigation. Exploration enabled.
You don't remember this miracle, but it happened to you. You were born into chaos. Those first days were a blur. But then, by the power of your mind, you resolved that chaos into a universe. A small universe at first, but a supreme act of learning. From then on, you became a learning machine, acquiring knowledge at a rate that you would never match again. I'm Jim Franciscus. No one of us has been untouched by our advances in space. And I don't mean only the spectaculars, impressive as they've been. Join me as we look into some of the space explorations that so excite us and have such promise for improving man's environment that we dare not ignore them. For it is in the quest for such knowledge that science is bringing us closer to an understanding of who and where we are. And like that baby in the crib, helps us resolve our world, our universe. We who make our way in more mundane pursuits enjoy the results, applaud the discoveries, and then take the benefits of science for granted. But seldom do we think about the discipline each scientist faces. What we believe to be true today will be adequate for most of us. Not, however, for the scientist. He is driven, quite simply, because he knows there is more to know. And this knowledge, when tested and proved, will, as it always has, be used to improve the quality of our lives. "400 years ago, the lords and ladies, their jesters, the knights, and the peasants believed the solar system looked like this. The Earth in the center, the sun out there, going around us. One of the men thinking about this was a Polish doctor, Nicholas Copernicus. He found an answer that his mind couldn't resist. The sun is really at the center. The Earth goes around the sun. But the establishment wasn't easily moved. It was easier for them to move Copernicus and his Earth with him. But then came Johann Kepler, a German. He believed Copernicus, but thought he'd satisfy the powers that be as long as the new universe moved in perfect circles. But then Kepler saw the truth. His mathematics insisted the circles needed stretching. The orbits were elliptical. From Italy came Galileo. Hitting upon Kepler's notes, he came up with a telescope. And he saw the stars, myriads where others before him had seen only thousands. And he saw that the planet Venus has phases, like the moon, which proved it must be orbiting the sun. And the moons of Jupiter? If a planet could have satellites, why not the sun? Finally, an Englishman, Isaac Newton, discovered why the Earth and the planets move about the sun. It is the gravitational pull of the sun which keeps them from flying off into space. Newton told them,
"The solar system is a great clockworks. If you understand the laws of nature, you can make or do most anything." Really?
The human race saw, became a great learning machine, and made progress never before possible. not sure you can credit Newton for everything you've just seen. However, the practical results from what appear to be a purely scientific discovery are often unpredictable. A good example that looks contemporary despite its origin in the 1800s is Michael Faraday's statement defending his research before an English parliamentary group.
Gentlemen, I do not know what this electricity can be used for, but I predict that one day you will tax it.
Give a man knowledge, then step back and see what happens to him. It seems to free him. And that's what's put us in space today. Until recently, almost everything we knew about space was learned through this tiny window, the visible light window. All the rest of the secrets of the universe were hidden behind windows of invisible radiations, low-frequency radio waves, infrared, ultraviolets, and others. Signals from the universe, energy that would unlock so many secrets, were blocked out by our own atmosphere. And a pretty good thing, too, since part of the radiation generated by this invisible energy is harmful to us. But as for seeing behind these windows, the Earth's atmosphere makes it impossible, even with the largest, most sensitive telescopes. There is one solution. Go higher and higher, taking our telescopes with us, beyond the atmosphere to outer space. Out here, what was invisible down below is still invisible to our eyes. But here we can measure it. And by measuring the radiation, infrared, ultraviolet, X-ray, gamma ray, cosmic ray, we can tell the distance of the stars, the energy they are pumping into space, how the atmosphere of other planets is different from our own, the temperature of gases in interstellar space, the strength of magnetic fields, the speed of particles in galaxies. The measurements become numbers, and the numbers are rained down on Earth. And out of the numbers grow pictures. The Earth and its sister planets, the ultraviolet sun, the X-ray sun, radio sounds from space, and the word that there are more than 100 billion stars out there besides the sun. And with each spacecraft, each measurement, we are bringing the universe into sharper and sharper focus, resolving it, seeing it grow brighter and ever clearer in our minds. In a universe of billions of stars, there are billions of mysteries. What is the origin, age, and evolution of the universe, the destiny of the stars and galaxies? We have reached a unique moment in history where man has developed the tools to take scientific measurements that may unlock some of these mysteries. Our satellites will help us crack the secrets of our solar system, unlock the doors in the universe, and enable us to learn more about our own planet Earth. With this knowledge, we may be able to improve life and avoid disaster. Without this knowledge, we may be able to do neither. In the few years we have jumped into space, our image of the Earth's environment has utterly changed. We have found, for example, that instead of simply being surrounded by a magnetic field that faded out endlessly in space, we are actually encased in a magnetosphere. And that this magnetosphere ends at about 40,000 miles. Ends because there's a great wind out there. A wind, mind you, where there is no air, no molecules that you feel pushing against your face when you stand in a breeze. This airless jet stream is the solar wind. And to stand in it unprotected would be like holding radioactive material in your bare hands. You saw our astronauts on the moon unfurl a window shade of metal foil, which they later brought home with them. Man was catching, literally, bits and pieces of the sun, fallout from the sun's nuclear hell. And that is what the solar wind is, fallout from the thermonuclear reaction in the sun. We wanted that sample because we live in a cavity in that wind, and we want to know how it is affecting us when there is a storm on the sun, changing our weather and blacking out our international radio communications completely. And we'll want to know what effect that solar wind has on life. How dependent are we on that magnetosphere? If another planet didn't have this protection, could it still have life as we know it? something else we cannot even imagine. There may be only one way to know. Go to the other planets. The inner planets, Mercury, Venus, Earth, and Mars, are relatively small, solid bodies like the Earth. Investigating them is our immediate goal. In 1973, the Earth, Venus, and Mercury will be lined up so that we can try a new way to go further in space. We'll launch our Mariner to Venus and then use the gravity of that planet like a roller coaster to give more speed and fling it into space toward Mercury. The first time we have ever been able to explore that planet. Venus is a paradox. It rotates the wrong way, for example, the opposite of all the other planets. Or perhaps we are all out of step, except for our lady in space, Venus. Why? Well, we really don't know, but if we find out, it may tell us more about how the solar system was put in motion than all the other planets moving counterclockwise. Venus is the brightest planet, but no one has ever seen it. We have seen the thick reflecting clouds that hide it, but not the planet itself. These clouds heat the planet. Any water on the surface of Venus would immediately boil off into the heavy atmosphere, more like superheated steam than water. Why bother? To satisfy scientists' curiosity? No. No, to know our own atmosphere better, we have to know all atmospheres. We have to ask, how did the Venus atmosphere get that way? Is it possible we are headed that way? Are we mass-producing enough pollution, enough smog, that might trigger the change, upset the balance, change the beneficial effects of our atmosphere? Only to mire ourselves in a malignant envelope that alters our climate drastically, that in the end might extinguish human life entirely. On the other hand, might it be possible for us to reverse conditions on Venus, perhaps with vegetation or chemicals, so that the oxygen locked in the carbon dioxide of the clouds is released, so that the planet cools, rain falls, and it becomes more like Earth? Is it possible that we might seed this bit of matter in space, so that some future generation from Earth can become pioneers in a distant new world? Why not? On Mercury, the nearest planet to the sun, there's probably no hope like that. If this planet ever had an atmosphere, it was blown into space long ago by the pressure of radiation from the sun. Here we may be seeing for the first time a completely desolate planet with no protection from the solar wind. Looking at Mercury, we can ask, is this the way the Earth would be without a magnetosphere or an atmosphere? Lashed by the full force of the solar wind without hope of life. And what about Mars? Well, this is the planet where we hope to find life, or which will help us understand the life process. In 1965, Mariner 4 got our first close-up photographs of Mars. 4 years later, Mariner 6 and 7 returned for a more detailed look. They sent back fascinating pictures of the rugged surface and the polar ice caps. When you watched this on TV, did you really feel that the spacecraft sending back the pictures was actually 60 million miles away? Can you imagine 60 million miles? The next step will be to orbit Mars. This unmanned flight is scheduled for March in 1971. Then we'll colonize it with machines. Our Mayflowers and our Pilgrim Fathers on Mars will be Viking, orbiters and landers. On the way down, the landers will measure the thin atmosphere. While overhead, the orbiters make related measurements. Then, for at least 90 days, our mechanical astronauts will take pictures, analyze the soil, sniff the strange air of Mars, feel for moisture. Thus, we will obtain information about Mars from the ground up to the limits of its atmosphere. Perhaps the greatest interest will be in the lander's search for signs of life. We're pretty certain now that there is no man-like life there, but we were not always men. We were once just cells. Before that, we were perhaps just molecules of protein. And we still want to know if there's that kind of life, or if sometime in the past, life did exist on Mars, and what could have happened to it. All of this will lead up to the ultimate exploration by man himself on Mars. The outer planets, on the other hand, are entirely different from the inner planets. On Jupiter, Saturn, Uranus, and Neptune, there may be no place to land, stand, or walk. They're all several times the size of Earth, but they may not have a solid surface to land on. About the fifth one, Pluto, we don't know enough to call it either solid or gaseous. Our spacecraft will leave the Earth for Jupiter in 1972. It will be a 400 million mile journey, and it will take almost 2 years. Jupiter is the largest of all planets, 11 times the diameter of Earth and over 300 times as massive, but a quarter of the density. We will want to know what causes the color changes in the bands of clouds. What causes the mysterious red spot that drifts around the planet. And we'll want to know if before the Earth became what it is, it was perhaps first like this. A mass of gas and dust and vapor. A condensing part of a nebula, out of which the sun was also forming. The protoplanet, caught by the mother star's gravity, turning eternally in orbit, condensing into stone, into rock, destined to develop life, and then perhaps to become, in the end, like Mercury, an airless rock baking in the sun. To go to the planets beyond Jupiter will be a journey, an odyssey of years. To do so, our spacecraft will have to have an operating life far surpassing any we have planned before. Moreover, these planets are so far away, we shall have to take advantage of special conditions to reach them. In the period 1976 to 1980, they will be in an unusual alignment that will enable us to go to all of them. And this alignment won't happen again for over 179 years. The last time the planets approached anything like this grouping was when Thomas Jefferson was President of the United States. And you'll remember it was he who sent Lewis and Clark to explore the West to resolve the image of our country. On our first grand tour, we'll launch a spacecraft toward Jupiter. Then, using the roller coaster maneuver we tried out on the Venus-Mercury flight, we'll send the spacecraft to Saturn, use the roller coaster again, and the spacecraft will go on to find Pluto. It will be a 7-year voyage. In the second grand tour, the spacecraft will go to Jupiter as before. Then Uranus, on to Neptune, nearly 3 billion miles from Earth. After nearly 8 years, this spacecraft, which will be sending back its rain of data, will then escape the solar system and become the first object created by man to adventure into the galactic space of the Milky Way. A message to 100 billion stars that we are here, somewhere in the universe. How can we use the knowledge we will gain of the solar system for the betterment of our life on Earth? Our spacecraft are already being used to observe the Earth, to count the Earth's resources, provide better communications, better navigation, and to study the Earth's atmosphere. We live in this atmosphere. We breathe atmosphere. We see atmosphere. The sky is blue only because the atmosphere scatters the sun's light. It is here that the interaction between the sun and its solar wind and Earth, between oceans and land, between the Earth and its own atmosphere, is acted out. This is where the hurricanes, the typhoons, tornadoes, tidal waves move across the stage. It is in that thin layer that the very fabric of life is both nurtured and attacked by nature. Can we do something about weather? Has our study of other planetary atmospheres given us any clues to the weather here on Earth? We think so. And in the next few years, the world is going to see the largest, most widespread scientific experiments ever attempted. It will be known as the Global Atmospheric Research Program, GARP. This will be a cooperative effort of the scientific societies and academies of almost the entire world. Everything that we know, everything that we can learn, will eventually be drawn together to create a model, a mathematical description of the atmosphere. When this is done, and with continuing observations, we hope to have the ability to forecast the weather accurately up to 2 weeks in advance. Think of the vacations saved, the picnic sandwiches, the rain check you wished you never got, the hairdo that was so special and had to look just right. More important, perhaps, than all the things you've just seen, we may be able to tell food producers everywhere in the world how much moisture they can expect, when to plant, how big their harvest is going to be, and where to distribute the food, where it is apt to be most needed. Today, we look to spacecraft to help solve these problems. In ancient times, man looked to the stars, and isn't that how astronomy began in the first place? We live under the influence of a star, our sun. Yet for 2 centuries after the invention of the telescope, we almost ignored the sun. It was perhaps too close to be interesting. Today, our orbiting solar observatories are making up the lost time. Soon we plan to put a telescope into orbit around the Earth with its instruments pointed at the sun, and an astronaut to adjust it, recover the photographs from time to time. We will call this the Apollo Telescope Mount. The sun, as we now appreciate, is a most unique laboratory. By measurements and logic, we are deducing its life history, and the life history of countless other stars. We believe that it was once a much larger, far cooler ball of glowing red gas. Cooler because the nuclear reactions that make stars hot were just beginning. Its own gravity pulled it inward, decreasing its size, increasing its heat, moving it into the main sequence of a star's life. It became the yellow-orange sun that rises in the morning over the life it has nurtured. As it grows older, it will probably grow hotter, larger again. Then, a great flash of light in the sky, a nova, it may collapse, and pass its old age as a cool white dwarf, its story all but ended, perhaps. But from what we learn on the sun, we can instruct our other satellites what to measure among the other stars. Our orbiting astronomical observatories turning their eyes to see what is invisible from Earth. Or our radio astronomy explorers, spinning out arms longer than the Empire State Building is tall, reaching out for radio waves that come from stars, the planets, the Earth itself. They will find mysteries, some that we shall solve, some that will lead to other mysteries. For example, the Crab Nebula. Until a century ago, astronomers with simple telescopes saw this as a blur, then resolved its image further with modern telescopes, and now see in greater detail by space observations. In its center is a small blue star, a faint hot star, one whose history we believe is all but ended. Yet, from that point of light comes energy at a rate 50,000 times greater than the sun's. It is a pulsar, and it pumps an unbelievable burst of energy into the heavens 30 times every second. What does it mean to us? Well, if we can measure it, describe it mathematically, understand its laws, then perhaps someday we might be able to duplicate this newly discovered energy source, as we did with the nuclear reaction astronomers found on the sun, and perhaps even tax it. Who will we meet as we travel in and out of the byways and boulevards of space billions and trillions of miles in length and breadth? Is there a chance that we will find planets where there are beings like us or unlike us, but perhaps alike in their deep curiosity about where they are, where they came from, and who shares the universe with them? Many of us think so, because even in our own galaxy, with its billions of stars, there should be millions of planets on which life could have evolved. For we are like the child in the crib, its eyes open, resolving its first mystery. Well, there it is, the great adventure of the universe, which it took man more than 6,000 years simply to define. And at last we are ready to go there, ready for the next great leap in learning that the human race makes to meet the challenges of the moment.
The human exploration of space is still in its infancy. The Apollo missions were just the first step in our goal to have astronauts working on the surface of worlds beyond our own. And as NASA plans its return of humans to the moon and eventually onto Mars, a team of scientists have come together to test and build some of the tools our future explorers may use on these journeys. Based out of NASA's Goddard Space Flight Center in Greenbelt, Maryland, this group is called the Goddard Instrument Field Team, otherwise known as GIFT. The scientists in GIFT collect data on some of the most unique terrains on Earth, such as glaciers in Iceland, lava tubes in Hawaii, Mar craters in New Mexico, and the desert regions of Chile. The goal is to conduct field research in geologic settings that share similarities to locations on other planets, moons, and even asteroids. Scientists call these sites planetary analogs, as they help us learn how to interpret data from across the solar system, while also getting a better understanding of Earth. In these environments, GIFT researchers test both commercial and newly developed scientific equipment. These are portable devices that could be used by astronauts, or used aboard future rovers or other types of spacecraft. These field instruments are capable of multiple types of analysis, with some providing instantaneous feedback. The team uses devices that can observe and characterize the landscape around a user, as well as ones that analyze the chemical composition and physical properties of materials found at and below the surface. The team also works with instruments that measure aerosols in the atmosphere, magnetic fields, and solar radiation. No matter which field campaign they are on, the scientists in GIFT are selecting and using their instruments to answer high-priority science questions. And to more fully capture the essence of how humans would explore the surface of the Moon or Mars, GIFT members also simulate astronaut EVAs, or extravehicular activities, at the planetary analogs they study. Both former and current astronauts have accompanied GIFT on these simulations. Overall, the Goddard Instrument Field Team provides a unique resource to NASA and the external science community by combining the studies of planetary science, earth science, and hardware technology. All of the tests, experiments, and data collected provide a blueprint for the human exploration of other worlds. And that's a great gift for those taking the next giant leap.
Today, we're going to talk about robotics on the International Space Station. Right now, there are several types of robots in orbit. There's a robotic arm that was used to construct the space station. There's a dexterous robotic space handyman. There's even robots that school children control by writing programs. We'll learn about those and some pretty special robots here on Earth. Join me as we go on board the ISS to learn more about robotics. Hi, I'm NASA astronaut Tracy Dyson. Welcome to Station Life.
Houston on 2 for velocity calculation, assembly, steps 4, 5, and 4, 6. We're moving on to
Tracy,
step
you
5.
want to go right now for that activity?
Thank you.
Okay, Tracy, we copy, and that's good information. We'll pass it along.
In this episode of Station Life, we're going to talk about robotics on the International Space Station. We'll hear from astronaut Mike Hopkins and what it takes to control the Canadarm2 robotic arm. We'll take a look at how robotic technologies from the International Space Station are helping lives right here on Earth. We'll have an interview with astronaut Kara Nyberg, one of our most experienced robotic arm operators, and the role robotics plays on the ISS, and hear stories of using Canadarm2 to catch dragons, among other things. So don't go anywhere. We've got a lot of robotic action coming right up.
One of the things that's really interesting about the Canadarm2 on the space station is that it has the ability to inchworm around the space station. It has 7 joints, and that makes it analogous to the human arm, but it also has a symmetric design, which means the base and the tip of the arm are symmetric, and there's an elbow joint in the middle. This means that what starts off as the base can be then maneuvered and released once the tip has grabbed onto another location, and then that base becomes the tip. So imagine my arm as I go from here, as I'm moving the arm here, I can grab on this end and release this end, and I can move around now. This allows me to inchworm around the space station and allow me to increase my range in order to service things and also to do surveys and get the arm around this ISS. Like many people in the world that have a space passion, we all want to become astronauts and go into space. What I realized as I was growing up was that there are other areas that one can perform in the space program, and that was to become a flight controller. Once I became an active flight controller, I remember being in the Mission Control Center and sitting down and about to do an operation which I had written a procedure for. As the operation was beginning, I was looking at the numbers on my console, I was looking at the details of the operation, and I suddenly looked up at the monitor and I saw this beautiful view of the Earth going by. And I saw the Canadarm2 moving across this view, and it just sunk in that this is me. I'm in space. I didn't have to be an astronaut to get into space. I'm a flight controller and part of this beautiful program. And I could see my nation's arm moving, and it just gave me this wave of energy, and I just fell in love with my work. But of course, when that happened, I had to re-lock onto my numbers and focus on the job at hand, but it was a really fantastic moment, and I'll never forget that. My name is Cam Bahrami. I'm a robotics flight controller for the Canadian Space Agency. I'm stationed here at NASA's Johnson Space Center in the Robotics Flight Control Group. My responsibilities here are to support and execute the robotic operations on the space station using Canada's robotic system.
Did you know that we call operating the Canadarm flying the robotic arm? That's because it's a lot like flying an airplane. I mean, it's got hand controls, you can pitch, you can yaw, you can roll, and you have to be pretty precise. Watch astronaut Mike Hopkins describe how we use the Canadarm to catch cargo vehicles arriving at the space station.
Okay, hey everyone. Yesterday we had the opportunity to catch the Orbital 1 Cygnus vehicle, also known as C. Gordon Fullerton. And I'm going to take the opportunity today to talk about the controls that we use for the robotic arm. And so we're actually down in the cupola right now, and this is where we control the robotic arm when we go out and we grapple one of these vehicles like the Cygnus vehicle that we did yesterday. And so this is the control station, and what you see over here on my left, this controls the translation of the robotic arm. And then over here we have rotational control. And then this middle computer is where we actually take the robotic arm into the different modes that we do have. And then on our left over here we have a control panel for the various monitors. So what we're doing when we're grappling is I'm watching on this monitor basically a target on the vehicle, and I've got an overlay on it that allows me to line up the robotic arm with that vehicle, and I just drive right in. Now I wanted to take advantage today though, because we have a pretty special opportunity here to show you a unique view of the robotic arm. And so if we look out one of the cupola windows here, you can actually see the end effector of the robotic arm. And we don't get a chance to look at this view very often. In fact, today we were doing an inspection on the end effector. And so if you look in the middle, you can see those cables. Those are what we call the snares. And when we go over the pin that's on the vehicle and I pull a trigger, it causes those cables, those snares, to close around that pin. And that's how we grapple onto a vehicle. And actually you can see up above as well, that's the camera that is giving us that view, and that's a pretty unique view for us, and so just wanted to share that with you.
Clearly, the Canadian Space Agency's robotic arms are technological marvels in space. You'll be happy to know that the same technologies are saving lives here on Earth.
1981 marked the debut in space of one of Canada's most iconic symbols, Canadarm. Developed for Canada by McDonald, Detweiler & Associates, formerly Spar Aerospace, The first Canadarm and its descendants, Canadarm2 and Dexter, are in great part responsible for the successful assembly and operating of the International Space Station. Now the technology behind these robots is finding its way back to Earth. By the end of 2014, an estimated 24,400 Canadian women will have been diagnosed with breast cancer. Early detection and treatment make a difference and help save lives. Researchers at the Center for Surgical Invention and Innovation turned to Canadarm technology to develop IGAR. It is a promising platform offering one-stop diagnosis and treatment for patients with a high risk of breast cancer. Currently undergoing clinical trials, IGAR is one of the first robots of its kind designed to work inside an MRI scanner that can show the size and location of tumors more accurately than a mammogram or ultrasound scan. Thanks to its delicate and precise touch, the robot will be able to perform biopsies with pinpoint accuracy, analyze them, and treat early tumors without open surgeries. The platform will also help in detection and treatment of lung, liver, kidney, and prostate cancers, and might also be used for delicate spinal surgeries. Thanks to Canadian Space Robotics, this technology is a step towards a future where surgeons can rely on robots to perform intricate medical procedures that will be less invasive, less painful, and will allow patients to recover faster. Canadian Space Agency, thinking outside of the globe.
My name is Terry Fong. I run the Human Exploration Telerobotics project at NASA, and what we're doing is developing robots to improve the way that humans live and work in space. As humans go further and further into space, as they go to Mars, one of the big things that we're going to need are robots to help humans live and work when they're very, very far away from Earth. You know, if you think about being on Mars, one of the big challenges is how do you carry out work on a surface? How do you work outside of a habitat? And so one of the things we're trying to do is create robots that can work ahead of humans, robots that can work in support of humans, and robots to follow up, doing those things that humans need robots to do to finish up work. I'm just really excited about the idea of humans and robots working together. Well, frankly, that's the future.
Well, guess who we have with us today? We have with us none other than one of our most experienced robotic operators and leaders in the astronaut corps in that category, Dr. Astronaut Kara Nyberg. Welcome to Station Life.
Thank you very much.
I don't get enough of Karen. We actually sit right next to each other. Our office desks are right next to each other. But she is someone that I greatly admire for all of the experience that she brings to the International Space Station. She has been part of the construction work on STS-124.
That's correct.
She helped to bring a module, I'll let her talk about that in a second, and attached it to the space station. And then she lived on board the space station during Expedition 36 and 37 and did a number of tasks with the robotic arm at that point. And so there has been rarely anyone else that has touched that robotic arm control than Kara Nyberg. So please, Kara, tell us a little bit more about the experience that you've had operating robotic arms on board the space station.
I've been very lucky. I've gotten to do pretty much everything that it was designed to do with it. As you mentioned, STS-124, we brought up the Japanese laboratory in the payload bay of Space Shuttle Discovery, and we used the Canadarm to take it out of the payload bay, move it around, attach it to space station. So that is one of the big tasks that the arm was designed to do originally, is carry heavy or big masses. And
Kibo was one of the, or we call Kibo's the whole complex, but
Right.
the pressurized module is the largest, is it not?
It is. It is.
And talk about, because didn't you also on your shuttle flight operate the PDRS, the shuttle arm?
I did.
Okay.
I did.
Talk a little bit about, because this is exciting, the difference between that arm and the station arm in terms of the joints.
Right. Well, the shuttle arm was pretty much fixed at the shoulder where you could have some pitch and yaw. The station arm also has roll at the shoulder, which adds another degree of freedom, so you have a lot more motion with the arm. And also you can move the location of the station arm.
Yes.
On station. So you could go along the truss and move it to different places and move it to the lab. And they do this little inchworm maneuver, they call it, where they attach one side, release the other, and inch it along the station to different spots.
That's creepy, but also kind of exciting at the same time. And so you did this motion, which, what do we call this one? The pitch plane?
Pitch plane, yeah.
We can only do that with the station arm.
Right.
And that's also what kind of makes it exciting, versatile, and dangerous at the same time, right? Because you can be moving, like this part of the arm can stay still, and this part can be moving around.
Right.
And there's just a ton of stuff you got to be looking out for when you, I mean, your mind is going constantly as you're operating that robotic arm. So talk a little bit about your space station experience. I know we had a number of cargo ships come up, and they all require at this point a grappling of the arm and an operator at the other end. Which vehicles did you grapple?
We had HTV-4 arrive.
Again, Japanese do big things big. That's our biggest cargo ship.
Yeah. So I was at the controls to capture that, and we also had orbital demo arrive. So it was the first orbital sciences vehicle. Luca captured that, and I was working with him during that. And I have to say, of all the things I've done in my spaceflight career, when I was at the controls of the arm, and it was just the realization that that vehicle's coming in. There are thousands of people around the world who are counting on nobody but you at that time to successfully capture that vehicle. And I didn't think about it much as I was doing the flying, but as soon as I finished and we confirmed that we had it captured, I could tell my heart was about to come out of my chest. And it just really shows, I mean, a lot of the things you do, you're working more as a team, and you're always working as a team, but for that moment when you're at the controls of that robotic arm, it was me or nobody.
It's all
at
you.
that point.
And that's pretty cool. I mean, you can focus through that heart pounding, and you're probably like pushing that aside. I have no idea what that is, but when it's over, the flush of wow, I just did that is pretty rewarding.
Yes, absolutely.
So I would say, so you've operated 4 different arms. We include the OPSS. You have grappled 2 cargo ships. You have grappled a robotic arm, the largest element, pressurized element on the space station. Karen, with all of this experience, and you've worked with so many different other individuals, other astronauts coordinating these tasks. What would you say was the most rewarding part about your robotics experience, both in space and in training for it?
I think it's the most rewarding thing in all of these robotics activities is similar to the most rewarding thing in everything we're doing when we're traveling in space, is getting the job done and getting a job done well, and working as the team to do that. You know, during the spacewalks, we wouldn't have been able to do the spacewalk activity without the robotic arm help, so I was an important part of the team. Capturing a vehicle, we could not capture the vehicle without the robotic arm, so a very important part of the team.
Well, I'd say that there's very little of the space station that would exist today if it were not for robotic arms, and especially that big Canadarm2 that we have used to move so many elements of the space station. So I just want to thank you so much for coming on the show today, Karen, because this whole episode is about robotics, and when I heard that that's what our topic was, the first person I thought of was Karen Nyberg. So thank you for being here, and it's been a real pleasure, and we hope to have you back.
Thanks for having me, Trace.
Welcome. The Canadarm and Japanese robotic arms aren't the only robots we have on the space station. Meet Robonaut. It not only looks like a human, but it's also designed to work like one too. With hands and arms, Robonaut is able to use the same tools that astronauts use. In the future, Robonaut may be used to perform hazardous maintenance tasks or even spacewalks.
Robonaut, a robot meant to work with humans and use human tools. R2's head houses not its brain, but its vision equipment. Behind R2's visor are 4 visible light cameras, 2 to provide stereo vision for the robot and its operators, and 2 auxiliary cameras. A 5th infrared camera is housed in the mouth area for depth perception. Each arm boasts 7 degrees of freedom and the strength to hold 20 pounds in any pose in Earth's gravity. Each arm is approximately 2 feet, 8 inches long, giving R2 a total wingspan of 8 feet. Instead of feet, the robot has clamps that allow it to latch onto and climb up on objects. The legs are also longer than human legs, a span of 9 feet, 2.7 meters, and are more flexible, giving the robot more ways to cling to things inside or outside the station. The advantage of a humanoid design is that Robonaut can take over simple, repetitive, or especially dangerous tasks on places such as the International Space Station. Our experience with R2 on the station will help them understand its capabilities for possible deep space missions.
Welcome back, and thanks for watching this episode of Station Life. Today, we learned about robots. We wouldn't have been able to build our International Space Station without the Canadarm. Good thing for us, spin-offs developed from the technology are helping patients with neurosurgery, and is now being developed to help those with breast cancer. We're also developing new technologies for robotics in space and on Earth. If we're to succeed with future missions to Mars, we need humans and robots working together. And that's a wrap for this episode of Station Life. So be sure to stay in touch and follow us on Facebook and Twitter for the latest research news. And don't forget to download our Kick a New app for your mobile device. Until next time, stay with us. Off the Earth, for the Earth.
What's up for January? New year, new moon, midnight meteors, and Mars rises. January begins with a new moon on the 2nd, and that means the first week of the month is ideal for stargazing because the few days before and after the new moon are the darkest. Head outside around 8 or 9 p.m. all week and look southward to be dazzled by all the bright stars of the winter circle, along with the Pleiades and Orion. The quadranted meteor shower peaks on the night of January 2nd and the morning of the 3rd. This tends to be one of the better meteor showers of the year and often produces a number of bright meteors called fireballs. This year, the peak coincides with the new moon, making for great viewing conditions provided the skies are clear. You should be able to see a few meteors on the couple of nights before and after as well. For the best quadranted meteor viewing, find a dark location away from bright city lights, point your feet roughly toward the northeast, and look up. The meteors appear to radiate from the constellation Boötes, which includes the bright star Arcturus, but they can appear anywhere in the sky. Generally, the best viewing will be after midnight, once Boötes rises above your local horizon. The source of the quadrantids is thought to be the asteroid 2003 EH1, which might actually be an extinct comet. So start off your new year by catching a few shooting stars after midnight on January 3rd. Finally, a couple of highlights at dusk and dawn. On January 5th, look to the southwest after sunset to find the crescent moon in a close pairing with brilliant Jupiter. The two will be only about 4 degrees apart, which should make them appear together through most binoculars. Then at the end of the month, on January 29th, if you happen to be up early, you can catch sight of the moon near the red planet. Joining the pair in the southeastern sky will be Venus. Having left the evening skies last month, Venus is now rising before the sun as the morning star. Now, Mars is slowly returning to view after passing behind the sun over the past few months. In fact, NASA stops communicating with our spacecraft at Mars for about 2 weeks every 2 years when the planet is directly opposite the sun. That event, called solar conjunction, took place back in October. Mars will continue to brighten and climb higher over the next few months, where it'll have super close conjunctions with Saturn and Jupiter, which we'll tell you about in future videos, so stay tuned. Here are the phases of the moon for January. Stay up to date with all of NASA's missions to explore the solar system and beyond at nasa.gov. I'm Preston Dykes from NASA's Jet Propulsion Laboratory, and that's what's up for this month.
We are SCAN. We are advancing today's space communication and navigation services and technologies to meet tomorrow's challenges. SCAN is committed to ensuring vital space communications through a network of complex ground stations and tracking data relay satellites. Together, these systems enable continuous communications and global coverage for space programs. Every space mission delivers terabytes of vital information for the process of scientific discovery. Our extensible and expandable communication and navigation infrastructure provides a resilient space framework that can meet the growing requirements of our users. We develop, operate, manage, and engineer pioneering solutions. Transformational technologies in satellite communications are underway. Cognitive systems will enable autonomous satellite networks, and optical communications will increase our ability to send and receive data to the vastness of space. We are developing these and other technologies to advance explorations of Earth, the lunar region, and beyond. Spectrum, the medium that enables communications and navigation. Through coordination, we ensure efficient use of this limited resource. We work with P&T partners to provide space missions accurate position and timing information. The most exciting part of this journey lies ahead, collaborating with commercial industry on major advancements in space communications. Our next generation of visionaries are creating a bright future, enabling Artemis lunar communications and a pathway to Mars. NASA Space Communications and Navigation. SCAN. Exploration enabled.
Wherever, however, whenever. We're here, there. We're everywhere. NASA Space Communications and Navigation. Exploration enabled.
You just watched the trailer to the inaugural season of NASA Explorer's Cryosphere. The 9-episode series first launched in October 2018, taking a hard look at the great lengths NASA goes to study a part of the Earth that's often called the canary in the coal mine, a serious indicator of present, past, and future climate change. The show was filmed right here at our studios at Goddard Space Flight Center, as well as on location in California, Alaska, Greenland, Iceland, Antarctica, and the Arctic. Our crew followed many of the people you're about to meet into the harsh elements to capture their stories and were rewarded with breathtaking icescapes. When you think of a NASA explorer, you might imagine an astronaut or even a scientist studying the outer reaches of deep space. In reality, while NASA is unlocking the mysteries of our solar system, it's also looking for answers on Earth, the only planet we know of so far with life. So sit back and enjoy this 9-part adventure story filled with awe, triumph, loss, and courage. Be sure to stick around afterward for even more exciting bonus material from the 2018 Cryosphere Field Season.
Here at the end of the Earth, it still feels like a place for raw exploration and adventure. It's vast in all directions and ground zero for some of the biggest questions we have about the climate. But when we decided to make a series about the frozen places on Earth, we knew there would be one hurdle we would need to jump over first. What is the cryosphere?
The what?
Ooh.
I have no idea.
While I'm aware of the cryosphere, I don't actually know what it is.
It has something to do with ice. All right, that's all I got.
How do you get people acquainted with the cryosphere when most of us don't even know what it is?
Hey, so here we are in Washington, D.C., standing on the roof of NASA headquarters. That's the Capitol building right behind me. And what headquarters does is kind of serve as the focal point to connect the dots.
That's Dr. Tom Wagner, NASA's cryospheric program scientist at headquarters. In short, Tom is responsible for making sure NASA knows what the current status of the cryosphere is.
The cryosphere is everything from the snow that falls by your house to the icy reaches of the Himalayas, to the big ice sheets of Antarctica all the way at the South Pole, and also the frozen ground of the Arctic, and even some of that frozen ground that's currently under the ocean.
If you had to break it down, you'd have a mix of sea ice, snow cover, permafrost, ice sheets, and glaciers.
Right now, our best predictions are that sea levels will rise anywhere from 1 to 3 feet within the next 100 years. 3 feet of sea level rise has the potential to displace about 100 million people, which is a lot of people that need to find new homes.
Our current reality places us at a near tipping point, and the cryosphere is playing a huge part in that delicate balance.
So one of the things people don't know about NASA is that we study the Earth, and we've been doing that since NASA's inception back in the 1950s. And we study the frozen part of the Earth in a variety of ways.
Missions like SNOW-X, Airborne Snow Observatory, Oceans Melting Greenland, Operation Icebridge, Arctic Boreal Vulnerability Experiment, and countless other labs and individual researchers stand at the forefront of monitoring the cryosphere. But this year was a particularly big year.
3, 2, 1, and liftoff of Grace Follow-On, continuing the legacy of the Grace mission of tracking the movement of water across our planet.
2 state-of-the-art satellite missions are being launched in a single year as part of a major attempt to understand Earth's frozen places. Our scientists are answering hard questions, sharing stories from the field, and giving their best predictions for what we can expect of a warming world.
We're taking you with us as we follow NASA explorers on their journey to the frozen ends of the Earth as they study our rapidly changing world from satellites, planes, and boots on the ground. What we think of snow depends a lot on where it falls. If you live in the eastern US, maybe it's fun. Or maybe it's just a pain.
But if you live in parts of the world where they depend on the water that's in the snow for a large fraction of their total water that they use for drinking, for agriculture, for industry, or for hydropower, the snow is a very important natural resource. For example, in the western part of the United States, 80 to 90% of their renewable water comes from snow.
Snow is one part of the cryosphere that many of us have actually encountered before, but it also plays a critical role in regulating the Earth's climate. Through decades of remote sensing, NASA has kept a close eye on the ebb and flow of snow cover.
We now have a 52-year record of snow cover in the Northern Hemisphere, and we can see changes in the extent of snow cover over the time period, particularly in the last few decades, where we can see that the snow cover has been retreating. It's been melting a lot earlier in the springtime.
The extent is relatively easy to do, and it has been done over the years. What's tricky is, though, how thick is that snow? And it's even trickier how much water is in that snow.
That tricky part is known as the snow-water equivalent, or how much water would actually be in a layer of snow if it melted. NASA and its partners have taken to the air to help solve this elusive mystery. First, there's the Airborne Snow Observatory, or ASO, a small plane outfitted with a couple of instruments, one of which measures snow depth using LiDAR. LiDAR measures distance using light from lasers. Since 2014, ASO has flown over basins in California and Colorado, taking before and after looks at snow depth. Scientists subtract the snow-free summer data from the snow-on winter data to get an idea of the snow depth. There's no single way to measure all types of snow across the globe, and so NASA's other airborne campaign, SnowX, is testing different combinations of sensors. This winter, SnowX will test a new instrument, the Snow-Water Equivalent Synthetic Aperture Radar and Radiometer, or SWISAR.
SWISAR consists of two main components, one of them being the radar and the second one being the radiometer.
So with the radar providing the depth of the snow and the radiometer providing the density of the snow, we could put those two things together and get the snow water equivalent. Here in the chamber, we're going to measure different radiation patterns at our different frequencies and do some full system testing in this chamber. This chamber kind of enables us to isolate various types of radiation and interference. And in about a month, we're going to take the instrument, mount it on a Twin Otter in the Grand Mesa in Colorado, and we're going to fly it over the Grand Mesa and take various different measurements. This is what we call our engineering flight.
Making sure the sensors are calibrated is key in order to face the challenges nature will throw at them.
Half of the area that gets covered by snow every winter contains trees and forest. And the trees make it difficult for the sensors to see the snow that's underneath the trees, so it makes it difficult for us to measure how much snow there is. After the snow's had a chance to sit on the ground for a while, it gets denser and denser and denser over time, and it changes, which is another reason why snow is very challenging to remotely sense. It doesn't stay the same. It's constantly changing. One of the things that we often do in the field is go dig what we call a snow pit. You literally dig a pit in the snow so we can see all the different layers. The layering is very important.
All this digging is part of ground truthing SnowX, a way of matching up what the airborne instruments see and what is actually sitting on the surface. The ultimate goal of SnowX is to figure out what the best combination of instruments would be for a future satellite mission in order to get a global picture of snow.
We need to know how much snow is in a snowpack, because if we have too much snow and the snow melts too fast, then you can get flooding. And if you don't have enough snow, or if the snow melts too early, that can lead to a longer wildfire season, a more intense drought, and we need to know these things for water resource planning.
I can't really name anyone that has so much integrity as she does to the things that she's accomplishing. It's pretty amazing. Having Claire as a role model, just a strong woman in science and just so smart and so kind. It's just a huge confidence booster. It's that, hey, I could do that too, you know? That's possible, that's successful, that's what I want to do.
I would characterize her as a pioneer in the field.
The amount and quality of the work she's put out is second to none.
I know people who have a lot of tenacity. I know people that have integrity, but it's rare that people have both together in that, you know, that combination that Claire does.
Every morning, Dr. Claire Parkinson gets up before sunrise and runs 2 miles to work. She hasn't missed a day in nearly 40 years. To know the evolution of sea ice and how we observe it from space is to know Claire. This year, she's celebrating 40 years at NASA.
When I arrived at Goddard, which was in July of 1978, it was an incredibly exciting period here. Satellites were pretty new, but a lot of data had been collected.
NASA scientists were inundated with information, and Claire was in a cohort looking at sea ice, trying to make sense of a jumble of very raw, very new data. It was around that time that Claire and her team, at the time led by Dr. Jay Zwally, created the principal sea ice record that we use today.
How does something like that record help you do your job?
Oh, that record is fundamental to understanding sea ice. So without it, we wouldn't know how rapidly it's changing.
You may not realize it, but Claire's work studying the changing extent of the ice caps deeply affected our understanding of climate change, and relatedly, our understanding of how climate change affects life on Earth.
One of the clearest signals for climate change that resonates with people has been this shrinking of the polar ice cap in the summer that we're able to see because of Claire's work.
After we had a record that was about 15-20 years long, we started noticing that the extent of the ice in the Arctic was getting smaller over time.
Sea ice is formed on the surface of the ocean and therefore is made from seawater. The biggest concentration is in the Arctic, and it's also where the biggest loss in sea ice is occurring. Every year, NASA reports on the sea ice minimum and maximum extents. As expected, the data is concerning.
By now, not only has this trend toward lesser ice continued, but it's even accelerated, so that now the decreases are greater than what they had been.
These trends are deeply troubling. But one thing's for sure. Our awareness of shrinking sea ice extent due to climate change was propelled faster and further after Claire Parkinson arrived at NASA.
I mean, she takes her job seriously, and the health and welfare of those instruments in space, yeah, she's on it. You know, it's one of the things you don't worry about because Claire's in the loop on these things. It's going to be fine.
In science, We stand on the shoulders of giants, on the shoulders of those who explored before us. But then, some among us are giants.
Tuesday was cold, I almost froze my toes. Oh, what's it gonna be next week? Who knows? That's climate. Oh, that's the climate you got. You take a bunch of weather and you average it together and you're doing the climate rock.
At a glacial pace, it means something's happening so slowly you can barely tell it's happening at all. That used to describe the very incremental movement glaciers and ice sheets experienced each year. But now that's changing. We're tagging along with 3 NASA scientists to understand the different lengths they go to not only investigate ice sheets and glaciers, but also communicate their often complicated science to the public. First, let's get oriented. Ice sheets, in pink, pretty much occur in only 2 places, Antarctica and Greenland. Glaciers, in yellow, play a key role draining melt off the ice sheet. Glaciers are also found in the high mountains, but we'll get to those in another episode.
So we know that something's happening in Greenland right now that's unprecedented in the last several thousand years.
That's Dr. Josh Willis, oceanographer at the Jet Propulsion Laboratory. Josh and his team are tackling one of the major environmental challenges of the 21st century, trying to answer fundamental questions about how melting glaciers impact sea level rise.
With my mission, Oceans Melting Greenland, or OMG for short, we're trying to understand just how much of Greenland's melt is caused by the oceans.
Along with being one of NASA's top scientists working on the cryosphere, Josh is passionate about demystifying climate change in typically unconventional ways.
I think by reaching out to people with a little bit of humor, a little bit of fun, maybe a song, you really have the opportunity to help people understand and come to terms with what we're doing to our planet. Because it's definitely happening and it's definitely a big deal, and we need to start preparing for it.
Down at the opposite pole, Dr. Kelly Brunt is getting ready for a major expedition.
In December and January this coming year, I'll actually be in Antarctica down near the South Pole collecting ground-based GPS data.
This is actually Kelly's second expedition to the South Pole. The first occurred in December and January of last year. Both surveys are critical and will help validate data collected by NASA's airborne campaign, Operation Icebridge, and the recently launched satellite mission ISAT-2.
All 3 of these layers, that ground-based, that airborne, and the satellite, are all tied together. The ground-based helps validate both the satellite and the the airborne helps give us more validation data for the satellites, but also a bigger story with respect to the depth of the ice sheet and what's going on underneath the surface.
While some scientists are taking measurements in the field, others are looking for answers in physics and lines of code.
For me, those projections that we are doing, they do have a very personal meaning.
Dr. Sophie Nowicki is an ice sheet modeler. That means she and her team have the important job of forecasting how ice will change in the future, which also predicts changes in sea level rise. It's a job she doesn't take lightly, especially since urban planning and infrastructure use her team's models to make decisions about the future and safety of their communities.
When we make those projections that are 100 years in the future, 100 years can seem so far away, like I don't have to worry about it, it's just too far. But actually they are not. It's really like the future that we are looking at that our children or grandchildren will see to experience.
Whether it's learning to communicate in new ways, traversing a swath of Antarctica in a massive piston bully, or taking responsibility for an impactful climate forecast, our NASA explorers are pushing the limits of discovery every day. But on a very human level, they're people with families and friends who have a stake in finding out why and how the planet is changing as rapidly as it is.
some places on the surface, you might have these steep cracks and giant fissures that you would have to be careful not to fall into. In other places, you might see towers of ice right next to places that were relatively smooth. You might see places that were dark. Ice there takes the form of rock. It's frozen solid until you dig down into that ocean. So you may see some things that look similar to Earth, but you may see some things that are very different.
That voice you just heard?
I am Morgan Cable, NASA scientist.
I love it. That's Morgan. She's probably one of NASA's best spokespeople for exploring our solar system's icy moons.
Europa is a fascinating place. It has this liquid water ocean that's about 3 times the volume of all of Earth's oceans combined. That's a lot of water.
To understand what makes Earth so special, sometimes you need to back up and take in the big picture. Remember, the cryosphere is every place on Earth with frozen water. And water is one of the biggest indicators for life.
Every place, at least so far, that we have found life, we found water along with it.
And so far, Earth is the only planet we know of with life. Although Europa isn't the only icy moon in our solar system, NASA has identified it as one of those places with key astrobiological potential. Morgan is a collaborator on the Mapping Imaging Spectrometer for Europa, an instrument selected for NASA's next mission to Jupiter's icy moon Europa. But she's also more than just a scientist working in a laboratory. She's preparing future NASA missions for success on the surface of alien worlds. This year, Morgan and her colleagues were in the field studying how life colonizes in fresh lava.
Earth, it turns out, has a lot of excellent, what we call analog environments, places that are similar enough to some of these other worlds that we can conduct some tests and we can do some analyses here. Now, they're not perfect, of course. They're not going to be exactly like Europa, but we can still learn a lot by testing in these environments. Some of these places include Antarctica and the Arctic Circle, but there are other places too, Alaska, Greenland, even Iceland. Any place where you have a lot of ice, because guess what the surface of Europa is made of? A lot of ice.
Studying the cryosphere doesn't just have big implications for Earth. It also matters for the frozen worlds in our own cosmic backyard.
If we're able to find life or evidence of past life on a place like Europa, that tells us that not only can life happen in other places, but it's common enough that it happened at least twice in the same tiny solar system. That means that the universe is wide open in terms of how much life we might find, the types of life we might find. It would revolutionize how we see ourselves and the possibilities for contact in the universe. It would be amazing. Oh, it's so exciting.
My interest in glaciers comes from the sheer size of these things and how much they're able to change on human timescales. And so the amount of mass and energy being transferred by glaciers around the globe is tremendous. It's an absolutely fascinating thing to study from space.
Mountain glaciers are some of the most charismatic parts of the cryosphere. Some might cling to the edges of cliffs at higher elevations, then lay bare and flat in a broad plain, looking cracked and weathered like elephant skin, before tumbling thousands of feet toward the sea and terminating in a dramatic calving front. They're like motion frozen in time, until they aren't. They tell a story about the distant past and yet are incredibly responsive to the present. You can understand why they'd be captivating to all of us, and especially cryospheric scientists. Meet Alex Gardner, a cryospheric scientist at NASA's Jet Propulsion Laboratory, who is going to help break down what a classic West Coast North American glacier might look like, where high amounts of snow dump onto the mountains.
And at higher elevations, there's melt in summer, but not enough melt to get rid of all of that snow. And so that snow accumulates, it compacts, it turns into ice, and it starts to flow under its own weight, and it flows down the valleys. And as it flows down the valleys, it actually carves those valleys out and it makes them deeper. And so it creates these beautiful fjords where the ice flows down, snakes out and down to the ocean or to the lakes or further inland. And so that ice is flowing, it's moving.
Alex uses satellite data to study large-scale changes in glacial ice. But 2,000 miles to the north, Chris Larson from the University of Alaska Fairbanks spends a lot of time studying glaciers from the air. He's been flying over Alaskan mountain glaciers for many years, most recently on a NASA-funded mission called Operation Icebridge Alaska. He's absolutely enamored with his local rivers of ice.
And what do you love about mountain glaciers?
Well, they're in mountains, so they're really pretty.
You couldn't ask for a better way to experience Alaska on a large scale than to go flying around for campaign after campaign and look at all of the mountains in Alaska. Truly infinite. You just feel like you'll never see the end of them and don't want to either.
But Chris doesn't spend weeks away from home and family for the views. Chris and his colleagues at NASA want to answer some pretty big questions by learning more about Alaskan glaciers and how they tick.
You know, why does NASA care about these? Well, they actually disproportionately contribute a large amount to sea level rise.
In the long run, as the Earth warms due to climate change, the big ice sheets and mighty outlet glaciers of Greenland and Antarctica stand to contribute the most to sea level rise, simply because the vast majority of the planet's ice is stored there. But currently, it's the world's smaller mountain glaciers in comparatively warmer places, like Alaska and Patagonia, that are contributing about a third of all inputs to sea level rise, even though they account for only 1% of the world's ice.
Mostly due to them being dynamic. They have water at the bed, which allows them to slide fast, and they react quickly to climate change and have higher velocities than their polar counterparts.
Back at JPL, Alex uses satellite measurements of global ice and computer models to predict ultimately how much sea level rise we might see due to climate change. But in the case of mountain glaciers, we also care about the local impacts of disappearing ice.
When we think of changes in ice sheets, we typically think of just what is the consequence for sea level rise and the future evolution of the ice sheets. But glaciers in other regions, like high mountain Asia, Alaska, the European Alps, these are places where changes in runoff matters to stream flows. In places like high mountain Asia, you have a lot of glaciers that feed the streams that flow down to populated regions. And that runoff becomes significant for water resources, irrigation, and agriculture.
Both Alex and Chris are passionate about understanding how glaciers are changing and what it means for our planet's future. They'll continue to use tools like elevation maps from the ICESat-2 satellite and detailed airborne measurements to monitor changing ice.
What we're looking at is a legacy of the Ice Age. Permafrost and methane is a time machine. So what we're going to do is walk back in time. We're going to see old carbon, old bones, old environments, and none of those are in equilibrium with today's climate, so that's the problem. That world doesn't exist anymore, and it hasn't for 10,000 years. It was nicely and very delicately separated from this modern warmer climate by about this much moss. And when that moss goes away, whether for fire or for human disturbance or for warming, then all hell breaks loose.
permafrost. It's maybe the part of the cryosphere that's most out of sight and mind. It's fascinating how it formed in the first place and how it got loaded with so much carbon. In a minute, we'll go back underground with Matthew Sturm from the University of Alaska Fairbanks. But first, let's meet Peter Griffith, NASA's project manager for the Above campaign, which supports more than 70 science projects studying forest and tundra vegetation, wildfires, animals like birds, caribou, and Dall sheep, methane emissions from expanding northern lakes, and the impacts of climate change on people in Alaska, Canada, and around the world. Many of those projects have some direct connection to permafrost.
Permafrost is the hidden cryosphere. It's the permanently frozen soil that surrounds the Arctic, all across Alaska, northern Canada, and then across Eurasia. The ground has been frozen during the ice ages.
During the ice ages, there was not enough snowfall in the drier regions of Alaska and Canada to form glaciers there, so the land was suitable for vegetation.
What happened is that over thousands and thousands of years, all of that plant material got compacted and frozen every winter and buried and pushed down, so that today there's 300 feet deep of frozen water and dead plants and some pieces of dead animals too. Sometimes you find woolly mammoths in the permafrost. But most of it, of the organic matter as we call it in the permafrost, is frozen plant material.
Some of that plant material is now thawing and decaying, releasing its ancient carbon into the atmosphere, sometimes in the form of methane gas bubbling out of expanding northern lakes.
We started this fuel campaign because the Arctic is the part of the planet that is warming first and fastest. And there are consequences to this for permafrost. So during the Arctic Boreal Vulnerability Experiment, we're studying permafrost with people on the ground, from aircraft flying over the region, and also from satellites in space.
Another way to understand the permafrost is to take a walk below ground with Matthew Sturm and into the U.S. Army Corps of Engineers permafrost tunnel.
And they've dug this tunnel back into the side of a hill about 200 feet, and it goes sort of sloping down so that by the end of the tunnel you're about 100 feet underground, and you're surrounded by bones sticking out of the wall from the steppe bison and the mastodons that are frozen in it. There's sticks that are 40,000 years old, that you can touch with your hand. There's grass that's still green, that's tens of thousands of years old because it got frozen, right away, and it's never lost the green color.
But as fascinating as it is to see these relics of an ancient era, or to see a tree split in half by thawing soil, or even to light a ball of methane on fire from under winter ice, at the end of the day, Peter and his colleagues want to know just how much organic matter is frozen in that permafrost, and how fast it might be released.
Currently, we think that there is something on the order of 2 to 3 times as much carbon locked up as frozen organic matter in permafrost as there is carbon dioxide in the atmosphere. So releasing all of that organic carbon from permafrost into the atmosphere would be a real game changer. That would be a tremendous transformation of the planet's atmosphere. Now, the good news is that it would take a very, very long time for that to happen. However, we are warming the planet at a rate now that calls into question how quickly is that changing and what the consequences in the near future and in the far future are going to be.
We're at Vandenberg Air Force Base for about 20 minutes before the launch of ICESat 2. You might see the white light off in the distance, that's the Delta II rocket.
It kind of feels like an idea that was always going to just stay an idea. But no, it's real. It's sitting on top of the rocket.
You know, and for me, it's kind of surreal. Like you say, it's been 10 years, and it's hard to believe. It's like, we're really here? This is really about to happen? It's totally cool.
This is Dr. Tom Newman. Over the years, his work has taken him to some pretty remote areas to study changes in the ice regions of our planet. And his research, among many others, has defined the goals of the new NASA satellite, the Ice, Cloud, and Land Elevation Satellite 2, or ISAT-2.
And we have ignition and...
The story of ISAT-2 really begins with ISAT-1. ISAT told us all kinds of cool things about the ice sheet and about sea ice that we didn't really know to ask. That data allowed us to measure elevation change of ice sheets in a way that we hadn't been able to before, and showed that all the action on the ice sheets, the places that were really changing quickly, were around the edges. So when we were thinking about what could we do better next time, we knew that was one key component.
In addition to the edges of the ice sheets, ISAT-2 needed to measure a dimension of sea ice that remained elusive: its thickness. To figure out how thick sea ice is, you can measure the height of ice sticking out of the ocean, or freeboard, and compare it to the height of water between the sea ice flows, called leads.
The problem is, sea ice is really dynamic, and those cracks open and close various places in the ice pack throughout the day, throughout the year, and what we need to do is have measurements of the ocean whenever it's available, wherever it occurs in the sea ice pack.
To solve that problem, ISAT-2 was designed with a fast pulsing laser instrument to take precise, near-continuous measurements across its 3 pairs of beams. For 10 years, everything about the mission was designed to measure rapid changes in the most rapidly changing part of the cryosphere. But it has to get into space first.
But it's a huge transition going from the ground to in space. We've spent the better part of 10 years, thousands of people have been involved, and actually seeing the rocket there on the pad with all of that work kind of all put together in one place, it's pretty amazing. And then getting up in the middle of the night to go watch the actual launch, it's sort of surreal in a way, because you've put so much time into it for so long, and actually seeing it over there is like, whoa, you know, it's a big deal.
4, 3, engine start. 2, 1, 0. Lift off. 1, 2.
That was awesome. Totally cool. There it went. That was Atlas. The last Delta II, heading on up. So Atlas has been turned on over the course of the first few weeks of the mission, really culminating for us with the laser. So this is our first look at sea ice data from ISAT-2, and it looks fantastic. The signal level is fantastic. Capturing ridges, we can clearly see the ocean, all sorts of cool stuff in there, and this is just our first data. It's only going to get better from here on out.
The data from ISAT-2 is well on its way into digging deeper into the unknown dimensions of sea ice sheets, and glaciers. It will shed light on changes in sea level and global weather patterns, and once again find new things about ice we didn't know to ask.
So my heart is definitely racing. I don't know about anyone else's. This is the stuff nerds dream of.
10 seconds. 9, 8, 7, 6, it's gonna 5, 4, 3, 2.
That countdown you just heard? We'll get back to that in a minute. Last episode, we saw the epic launch of ICESat-2, NASA's newest state-of-the-art ice-observing satellite. But now that that's in orbit, the pressure to deliver results is on.
Between launch and, the first ground returns, took 17, 18 days or something like this. It's a time when you're quite nervous.
9 years ago, Dr. Torsten Marcus took over as the lead project scientist for ICESat-2 during a time when the mission needed a champion.
You start fighting for a mission over, for 9 years now.
So when ICESat-2 was turned on for the first time 18 days after it was launched, only then would the science team know if the whole thing had worked. And it did.
First of all, it's kind of emotional, right? Being here, ICESat-2 was developing for 9-10 years. As a project scientist, you live the mission, right?
If it sounds like there's a lot of noise in the background, that's because Torsten is being interviewed from a plane 1,500 feet in the air. IceBridge was tasked with the job of bridging the data between the end of ICESat's mission and the beginning of ICESat-2, about a 9-year difference.
The goal is that it would run until ICESat-2 launched and then would have overlap with ICESat-2 as well, so we can get a really long, well-calibrated time series from IceBridge.
As the deputy project scientist for Operation IceBridge, Brooke works closely with Torsten to make sure the two missions are syncing up.
The timing was everything during that mission, which was a real challenge because not only do we need to...
Basically what you need to take away is getting an airplane and a satellite in space to fly over the same flight path at the same time and collect matching data is really, really hard. IceBridge was tasked with two objectives: check the accuracy of ICESat-2's data over land ice and over sea ice. They were able to lock in the land ice data fairly quickly in the mission, but the sea ice data...
It was really tricky. We waited day after day. Do we fly the sea ice? It's still on our list.
7, 6, it's gonna 5, 4, 3, 2, 1. Mark on the overpass 0435, 350.
Here's what just happened. A plane 1,500 feet up and a satellite 308 miles up measured the same sea ice at the same time. This moment finally linked veteran mission Operation IceBridge's data to that of its new sister mission, ICESat-2. Two projects that, until now, were separate for nearly 10 years.
It's a very satisfying feeling because you do something that is meaningful and in the bigger picture. And yeah, it's very satisfying.
Our search for knowledge doesn't end here. Grace Follow-On and ICESat-2, the two satellite missions that launched this year, will continue to bring in incredible data for the foreseeable future. The steady drumbeat of campaigns in the field goes on, but most of all, the people who look for answers will never stop searching. And from our perspective, it's pretty clear why. What is your favorite planet in the solar system?
My favorite planet is the planet Earth.
What? Earth? Really?
The Earth, obviously.
Favorite planet in the solar system? Earth, right? We live on it. It's a really important one.
Favorite planet is Earth.
Right.
Yeah.
Yeah.
Yeah, so
Why?
When you look out at the other planets, they're absolutely fascinating. They've got all sorts of interesting systems going on. They've got dust storms. But then when you're on another planet, looking back at Earth, I mean, it's just incredible.
Whenever you go in different places, it looks so different, so amazing. It's just, I love planet Earth. It's just a very special planet. This is our home.
We've seen things far beyond the solar system. But even with all that, even the amazing things we've seen, one of the most amazing is the Earth itself.
It's got to be Earth. It's got to be Earth.
It's got to be here. I like the polar regions of here, of Earth. Yeah, sorry. It's very boring.
Earth is good.
Earth is good.
We live here, it sustains our life.
I'm not going to turn my back on it.
It's got water, it's got ice, it's got vegetation. I mean, it's rich with life. And so Studying Earth is a very, very rewarding career. And I think if we were on any other planet, we would be trying to get to Earth as quickly as we could.
"14 days, 2 piston bullies, 4 people." So yeah, 750 kilometers, door to door. Recently, we just got back from Antarctica, where we completed about a 2-week ground traverse near the South Pole. We're basically driving piston bullies, tracked vehicles similar to the ones that groom your ski areas. Behind those piston bullies were 60-foot long plastic sled trains, and ultimately those trains carried things like our sleeping tents, fully erected and left standing during the day when we were driving. Kitchen tent, fuel, generators, all sorts of cargo.
But everything we needed for the trip.
And from a both science and survival standpoint. So this entire traverse was in support of ICESat-2, which will launch later in the year.
ICESat-2 is all about measuring elevation, and a natural question is, how do you know you're getting the right answer? This is how we will know. We'll go out and collect a reference data set. We'll be ready to compare and evaluate, see how we're doing.
319 is feeling kind of ready. How you guys doing over there?
So the big measurement we were making was to measure the elevation of the ice sheet surface around our traverse, and we had the 2 GPS running, one on each vehicle, measuring that elevation. One of the other experiments we were doing is leaving out what we call corner cube reflectors to get an assessment of the pointing of ICESat-2. When we make an elevation measurement, how are we sure it's in the right place? So in this picture, you can see a bamboo pole with a little white cap on the end of it, and embedded in that cap, a little piece of glass about as big as your pinky nail, and calibrated to return green laser light from the satellite. It bounces off of this thing and goes right back up to the satellite again, super reflective. So these things, as Kelly has demonstrated, show up in data with altimeters like ICESat-2. When you first get to South Pole, and you're coming from McMurdo, which is a nice seaside town right at sea level, and South Pole is what, about 10,000 feet. And yeah, you notice it pretty quickly. The temperature is a lot colder than in McMurdo. It's probably 30 degrees, 40 degrees colder, and 10,000 feet higher. Walking from the camp to where we're putting in an array, for example, would be a 10-minute walk, maybe 5 minutes. A couple breaks on the way. It's still pretty high.
The plan is to repeat this traverse for the next 3 years, so 4 years of data total, and that would last the mission lifetime, the mission requirement lifetime for ICESat-2.
ICESat-2 has 1,387 orbits, and so it's cruising around the world, and it's got these unique tracks that repeat every 91 days, and all of those tracks converge right here at 88 South. And so our route crossed, what, 20% of them? So we can calibrate data from 20% of our tracks with this stretch that we drove, and by repeating it every year about the same time of year, we'll have overlap at exactly the same time, but we'll also be able to figure out what's been going on in between, because we'll measure it in 2017 and then again in 2018, and you can see how it changes from year to year. So that'll be pretty cool too. It'll quickly become the best surveyed piece of either of the ice sheets.
This video is from the 16 October 2018 Northern Peninsula Ice Bridge mission. We're about 1/3 of the way into the flight right now in this video, and we have just finished our first transect across the Larsen C ice shelf from west to east. And we are making a right turn to get lined up for our second transect across the ice shelf. You can see here we're crossing some fairly large tabular icebergs. These are remnants of the breakup of the A68 iceberg off of the shelf last year. The big square-looking iceberg at left is the one that became somewhat famous in the media over the last few days. Now we're crossing some combination of open water and sea ice. This big, huge tabular berg ahead of us is the A68 iceberg. It's about 100 miles long, about 30 miles wide. And you can see the video here has been sped up by a factor of 20, and even at that, it still takes us quite a while to get across this thing. And you have to remember there as well that we were only crossing the northern corner of it, and even so, it took us a while. So now we're back off A68 iceberg, heading westbound. You can see the sun there, it's the afternoon, crossing a mixture of sea ice and icebergs, and this big white mass ahead of us is the Larsen C ice shelf, which we're just about to head back on.
There's enough ice here in Greenland to raise sea levels by 25 feet all the way around the world. It's an incredible amount of ice, and it's melting and adding to sea level rise. For oceans melting Greenland, what we really want to do is measure the oceans, measure the ice, and watch them change together year on year, and try and answer the question, how much are the oceans melting away the ice, as opposed to the air, which is what most people have studied so far. It's really a breathtaking landscape. These giant mountains and canyons are all along the coast. When you look out the window, you really get a sense of just how huge these glaciers are, these gigantic rivers of ice that are draining the ice out of Greenland into the ocean. And then they reach the ocean and it gets all broken and craggy and big chunks fall off. It's incredibly dramatic. Kulasuk is just a tiny little town in southeast Greenland, and we've been launching probes out of here for the past 4 or 5 days. It's already been a fantastic year for OMG measuring the oceans. We launch them right out of this tube right over here. Open up the tube, you can look right down it and see the water passing by, or sometimes the icebergs or clouds or whatever it is we're flying over. 6, 5. We slow down a little bit and we just push these big gray cylinders out of the bottom of the plane, and they fall to the ocean and measure the temperature and salinity when they get there and radio it back to the plane. We're really trying to look at the ice and ocean all the way around Greenland. So we're dropping 250 profilers. We're going to cover the coastline all the way around. And in the spring, we map out the glaciers with a radar, also all the way around. So we're really looking at mapping all of the ocean ice interactions in Greenland as best we can with one mission. What we care about with OMG really is the breaking off at the edges. As the water eats away at the ice, then it can actually speed up that breaking off part. And when you dump more ice in the oceans, then it causes sea level rise. So OMG is really here to try and figure out how much are the oceans doing, how much is this kind of breaking off of the ice, it's called calving. How important is that relative to the melting at the surface? And more importantly, is the ocean causing some of this speed up of the calving? We think it is, but how widespread is it and how big an impact? Even the smallest iceberg looks gigantic when you're right next to it. We saw an iceberg that was grounded in the bay. Remember, 90% of the iceberg is below sea level. So if there's about 10 meters or about 30 feet of ice above sea level, then 300 feet are below. It's a reminder that a lot of the stuff we're trying to measure is hidden below the surface of the ocean, hidden below the surface of the ice, and peering down into both of those is really at the core of what OMG is trying to do. Every time a ton of ice comes off of Greenland, sea level goes up a tiny little bit, and it's coming off Greenland at billions of tons per year. It's interesting to meet some of the Greenlandic folks who have been here their whole lives. They've all watched the glaciers literally vanish before their eyes. They didn't need satellites and airplanes and scientists to tell them that Greenland was melting. They look out and see the glacier used to be here and now it's way up there. Sea level rise is really a global problem. It's something we can't just ignore. 2/3 of the planet are covered by the oceans, and it's really the same ocean. I mean, if ice is lost here, sea level rises back home in Los Angeles, rises in Southeast Asia, in Australia, all across the planet. Being here and seeing the ice disappearing and literally watching it fall into the ocean is really profound, and I think it's something that I hope that we help people understand with OMG, that we all live on the same planet and it's changing and we need to know how.
From space, we see deep into the heart and veins of our ever-changing planet. Pictures of Earth are worth more than 1,000 words. They are the blueprint for our future. To unlock the full potential of space's unique vantage point, we've created powerful tools. Tools that gather valuable data. Data that enables farmers to efficiently manage water and fertilizer for stronger food yields. Data that scientists use to monitor ticks and mosquitoes that carry harmful diseases. Data that first responders use to find the fastest routes to save lives. That's only a glimpse of what we can do today. In the future, when combined with AI and powerful computing, a broader range of space data would generate infinite solutions for Canadians. Imagine a future where we can use space data to better understand and predict the impacts of climate change, like rising sea levels, extreme weather, wildfire risk, and flooding. Measure the health of our forests and create predictive maps of pest damage and burn extent. Produce real-time dynamic navigation routes to protect whales and other endangered species. Ensure security and sovereignty in Canada's vast Arctic. Tomorrow's challenges require investing in innovative solutions today. Earth observation is key to securing economic opportunities and improving the lives of Canadians. Together, we can define Canada's future.
Ignition sequence starts.
Good morning, and welcome to this view of the activity in the International Space Station Flight Control Room at NASA's Johnson Space Center. These specialists are keeping an eye on the operation of all of the space station systems and helping the Expedition 66 crew members through the last few hours of their work week in space. The American and German crew members have focused this week on science experiments and cargo operations, while Commander Anton Shkaplerov and Flight Engineer Pyotr Dubrov completed a spacewalk of more than 7 hours to outfit the station's newest module.
Houston Station on Space to Ground. Welcome to Space to Ground. I'm Nilofer Ramji. A spacewalk, cargo dragon's departure, and science investigations. It continues to be a busy week aboard the space station. On Wednesday, January 19th, Russian cosmonauts Anton Shkaplerov and Pyotr Dubrov completed a spacewalk to outfit and configure the Prichel and Noka modules. The duo installed new handrails, rendezvous antennas, a television camera, and docking targets on Prichel. A Soyuz spacecraft carrying 3 Russian cosmonauts who will be part of the Expedition 67 crew is the first scheduled docking to Prichel planned for March. Cargo Dragon is set to return to Earth carrying more than 4,900 pounds of supplies and scientific samples. The SpaceX Cargo Dragon has been packed with samples from experiments conducted aboard the orbiting laboratory and is ready to depart the space station. You can catch all the action on NASA television, the agency's website, and the NASA app. After re-entering the Earth's atmosphere, the spacecraft is scheduled to splash down off the coast of Florida. One of the payloads returning aboard Cargo Dragon is the In-Space 4 physics study. Results from In-Space 4 could share insight into harnessing neoparticles to fabricate and manufacture new materials, including medical diagnostics and thermal shields for Earth and space applications. The combustion experiment Acme Flame Design had some progress this week. The Advanced Combustion via Microgravity Experiments, or ACME, is a suite of 6 combustion investigations aimed at reducing pollutant emissions in practical terrestrial combustion and strengthening fire prevention in spacecraft. One of the experiments, Flame Design, aims to improve our understanding of soot inception and control to enable optimization of oxygen-enriched combustion and design of non-premixed flames that are both robust and soot-free. That's Space to Ground for this week. Thanks so much for watching. Don't forget to follow @ISS_research on Twitter to keep track of all of the science aboard the space station. We'll see you next week.
One more note on the subject of extravehicular activities. NASA's working to return astronauts to the moon in just a few years to explore it and learn to live there long term. It's part of the plan to get humans ready to explore out into the solar system. It's called the Artemis program, and Artemis teams here in Houston have used the Neutral Buoyancy Laboratory to work on developing the tools and training plans for the astronauts who will conduct the moonwalks of the future. Take a look. Long-duration missions on the International Space Station are helping prepare astronauts to live on the moon. And flight engineer Mark Vande Hei is now in the last couple of months of what's expected to become the longest single spaceflight ever by an American astronaut. Before he launched last year, knowing that there was a chance he'd be making an extended trip, the retired U.S. Army colonel was looking forward to another shot at some of the things he knew he was going to get to experience once again.
So I always, as a kid, I never would have told anybody that I wanted to be an astronaut. My attitude about that was like saying, I want to be Spider-Man or I want to be a superhero. I always thought that working at NASA would be amazing because my physics background, the photography you see from space, and the knowledge that we're kind of pushing the limits with our space program. All those things made NASA seem very appealing to me. The fact that I got to be an astronaut is gravy. And now my attitude about actually being an astronaut, actually getting to go to space, that's all just, I keep getting these bonus deals that are even better and better. So I'm pretty excited about it. The thing about physics that I really like is it takes what we know, figures out a mathematical model for it, and then you can use that to try to get to what we don't know and theorize about things. It helps us imagine things that we can't even sometimes use instruments yet to detect, and then science follows up with that to try to do experiments and try to test theories we come up with. So certainly being able to contribute to science, the space station's all about science, and it's helping NASA further our exploration goals. I really think we have to keep exploring. Most of our nation's background involves people leaving what they were comfortable with and coming to a place that was new and different and very risky. So I think it's part of our national character to want to explore. Dedicating those resources to this peaceful endeavor that can actually help out all of humanity. My name is Mark Vandehei, and I'm a NASA astronaut.
Those who see the Earth from the International Space Station often say it provides them with a new appreciation for the planet. Well, many of the pictures that they take of that planet are also providing the raw materials for science experiments. The Avian Migration Aerial Surface Space Project takes advantage of thousands of images captured by astronauts to give people an understanding of the migrations that birds undertake across the Earth.
I flew as a Canadian astronaut on the mission STS-42, Space Shuttle Discovery, back in January of 1992. Currently, my role as president of the foundation that bears my name is to conduct some research into the migratory corridor, habitats, and behaviors of certain species of migratory birds. We've been trying to utilize photography to put together a compelling reason why people need to pay attention to these very fragile organisms and their fragile environments. We think that doing it at 3 different levels, the aerial, surface, and space, will provide the different perspective. So it's as if we were down at carpet level with a magnifying glass on the surface, and then we get up and we see the patterns a little bit differently. And then we get into space and see this whole corridor, but we see different patterns that we didn't even know existed. So the space station can provide us these images so we can actually construct part of that flight, a part of that corridor of one of these species.
Growing up as a Canadian, Dr. Bundar was one of my heroes. She was the first female astronaut that we had in Canada, and I always kind of looked up to her because she was also a scientist and a physician. And there she was offering me the chance to participate in this beautiful project. And I loved because it fit with my hopes of sharing from space station my love of the environment. One of the challenges of taking photos of the Earth from space station is that we're going pretty fast. You know, we're going around the world in about an hour and a half, flying at 5 miles a second. And as you get to the cupola, get your camera ready, you're looking at previous images, satellite imagery, trying to wrap your mind around what you're trying to see, and then you look forward towards, the limb of the Earth as the Earth the scene is coming towards you. It's coming pretty fast, and you gotta identify it on the horizon as it approaches, because you have maybe just a few seconds as you're flying over that location, and then you look back, and maybe you have a few more chances as you're flying away from it. But that's it. The whole thing lasts, way less than a minute. But kind of chasing the right frame is a bit of an art because you only have one chance.
To date, we have at least, I'd say, somewhere between 24,000 to 25,000 images provided to us from NASA.
This was one of the larger imagery projects that we've worked on. Typically, we work with researchers or scientists that are looking at a few different locations on Earth, maybe no more than 10. And this ended up being about 50 different locations on Earth that we wanted both nadir looking shots, which is a straight down looking shot, as well as Earth limb shots. We worked with various crew members over the years to take a lot of these photos, but we also reached back into our database of over 4 million astronaut photos just to see what already existed. We get excited when external groups seek out these types of imagery projects with us, especially scientific and research groups.
Space exploration really offers us an amazing perspective on our home. And I think this project is a beautiful example of how we can kind of scratch our heads, take a few steps back, look at the big picture.
It's about taking that creativity that were offered in space, combining that with the aerial shots of getting closer and closer to when they put their feet on the ground, to me is an extraordinary way of trying to bring together this emotional story of the importance of habitat protection so that these beautiful, magnificent creatures that fly the way we do in space can survive on our planet for future generations.
Astronauts and cosmonauts on the International Space Station spend some of their time keeping the station operating smoothly, some of their time supporting science operations, and sometimes they help students on Earth learning about science, technology, engineering, and math. In this demonstrations video, astronauts Megan MacArthur and Shane Kimbrough use the weightless environment on the station to demonstrate the concept of moment of inertia in a way that even I can understand it.
Hello, my name is Megan MacArthur.
My name is Shane Kimbrough. We are living and working aboard the International Space Station orbiting 250 miles above your head. Here on station, we live in a microgravity environment which allows us to experiment with weightlessness and push the boundaries of science.
Today, we will demonstrate moment of inertia by first using a large flashlight, then demonstrating it with the human body. Are you ready? Let's go check it out. Inertia is the tendency of an object to resist change in its current state of motion. That might sound familiar since Newton's first law of motion is also referred to as the law of inertia. Moment of inertia, on the other hand, describes an object's tendency to resist rotational acceleration. An object's moment of inertia is a property that depends on how mass is distributed around its axis of rotation. There is a relationship between an object's mass distribution and how easily it spins or resists spinning. In general, objects have a lower moment of inertia and are easier to spin if the mass is closer to the axis of rotation. As you can see, the flashlight rotating about its longer axis is spinning at a faster rate than the flashlight rotating about its shorter axis. This is because its mass is closer to the axis of rotation. The spinning flashlight in this position has a lower moment of inertia, which means there is less resistance to rotation. When the flashlight is spun about its shorter axis, its mass is spread further away from the axis of rotation. In this position, the flashlight has a higher moment of inertia. Now let's see if this applies to humans as well.
Notice how fast Megan is spinning in relation to her body's position. When her arms are tucked in tightly next to her body, her moment of inertia decreases, which causes her to spin faster. When her arms are extended out, more mass is pulled further away from the axis of rotation, which increases her moment of inertia and causes her to spin slower. This happens because redistributing our mass changes our moment of inertia, which in turn changes how fast we spin. Thanks for coming aboard and watching our demonstration today. To explore more on moment of inertia, check out the Classroom Connection lesson that goes along with this video and discover many other lessons and activities at the STEM on Station website. See you next time.
The mission of the International Space Station includes serving as a platform for scientific research and for learning how to support human crew members during long-duration missions away from the safety of Earth, and promoting international cooperation, and being a test bed for future technologies that we'll need to support our plans to explore farther than ever before in the years to come.
Making space for technology development. Presented by Science at NASA. The International Space Station, or ISS, is Earth's only orbiting laboratory. That's important because it not only allows us to conduct research that benefits all of us on Earth, it also provides the only microgravity environment in which we can test technologies critical to our deep space exploration in the near and far-term future. Here, engineering models can be validated, and new technologies and systems for future missions can be demonstrated, without risk to crew members. Historically, the Mercury program enabled the Gemini program, which in turn enabled the Apollo program through technology and systems advancements. Today, the space station is giving us a similar experience in long-duration spacecraft operations, and serving as a testbed for new technologies and upgraded vehicle systems, which are enabling future missions. Dave Horniak is NASA's ISS Technology Demonstration Research Portfolio Manager. He notes the ISS lets us demonstrate that a technology works as intended in a spacecraft environment. Demonstrations on the space station inform operators and flight crews how the system operates, proves interoperability with other systems, and demonstrates system safety and reliability. There are many technologies and capabilities that need to be developed as we move forward to the Moon and onto Mars. For example, researchers have recently tested a new design of solar array that will be used on the first module for the Deep Space Gateway, our future space station that will serve as a home base for astronaut expeditions to the Moon. Solar arrays in operation right now need to unfold before becoming active. But new designs allow future solar arrays to roll out and also retract. They were tested for strength and durability on the ISS and were designed to be more compact than current rigid panels. NASA's Orion Multipurpose Crew Vehicle is a 4-person exploration craft designed to take astronauts farther in space than anyone has gone before. Its backup navigation system uses a new technology that is optically based. It captures images of the Moon or Earth, and based on their size and angle, an algorithm determines Orion's location. These optics can't be tested on Earth because our atmosphere would distort the images enough to make the algorithm inaccurate. Aboard the ISS, however, the algorithm was confirmed to work properly. A secondary benefit is the system was tested at spacecraft speed, making for a realistic navigation scenario. As people travel deeper into space, they'll need solutions to a variety of safety challenges. For instance, if a fire breaks out, how fast can it grow and spread in a microgravity environment? NASA's Spacecraft Fire Safety, or SAFFIRE program, has already conducted a series of experiments on 3 ISS cargo vehicles to measure flame growth, oxygen use, and combustion products. Results are helping to improve spacecraft fire detection, response and extinguishment, and crew protection. Ultimately, says Horniak, technology and operations demonstrations occurring on the ISS today are guiding our planning, reducing risk, and providing capabilities to enable future exploration missions. For more inside information about the tech being tested aboard the station, visit www.nasa.gov/ISS-science. For more on the science of space exploration, visit science.nasa.gov.
One goal of the International Space Station is to develop the technologies we'll need for future explorations, for when we go back to the Moon and then on to Mars. NASA's Exploration and In-Space Services Projects Division at the Goddard Space Flight Center has sent many such projects to orbit. In this episode of Tech on Deck, we learn about their first one, the Robotic Refueling Mission.
Outside of the International Space Station, space can be a lonely place. Most satellites are designed to live their lives alone, and we've yet to find life outside of Earth. This means that when we launch a spacecraft or satellite, for the most part it's on its own, and has a limited lifespan based on when critical items like fuel run out, or something breaks. You wouldn't throw away your car if it ran out of gas, and thanks to the advent of modern-day robotics, software, and computing power, we will soon be able to apply that logic to satellites. We are on the cusp of breaking the one-and-done paradigm that exists for most satellites. An important step in that direction is NASA's Robotic Refueling Mission, or RRM, demonstration on the International Space Station. Because refueling a satellite that was not designed to be refueled has never been done before, practice is key. With that in mind, the first two phases of RRM took place on station from 2011 to 2017 and tested the tools, technologies, and techniques to refuel and repair satellites in orbit.
RRM and RRM Phase 2 were designed to demonstrate end-to-end refueling of a spacecraft, as well as the first steps of cryogenic refueling or replenishment. We wanted to use the robot on the International Space Station to be able to demonstrate the technologies and techniques to do this refueling, so we built innovative tools to bridge the gap between the robot and the payload interfaces.
Consisting of a module or box affixed to the outside of station and robotic tools, the demonstrations use station's Dexter robot to operate tools and test servicing tasks such as cutting and peeling back protective thermal blankets, unscrewing caps, turning valves, transferring fluid, inspection, and intermediary steps leading up to refueling.
Once we were all done, we were able to transfer fuel end-to-end through a spacecraft fill and drain valve that wasn't designed to be robotically refueled.
The RRM demonstration helped test and prove technologies that will make refueling satellites not designed to be refueled possible, something that will be further demonstrated by NASA's On-Orbit Servicing, Assembly, and Manufacturing 1 mission. But it also helped to lay the groundwork for designing future satellites in a way to make them more easily serviceable.
These missions were important because we needed to demonstrate in orbit that this technology was ready. There were a lot of people that felt that at the time of RRM that the technology was so far in the future that they didn't feel what we were talking about was possible. So we needed to demonstrate in orbit this technology so that we could start changing the paradigm and incorporate these technologies into the future spacecraft designs and missions.
RRM Phase 1 and 2 were all about preparing an interface for refueling, which in many ways is half the battle. To robotically refuel a satellite, you need to perform a series of highly dexterous tasks to even access the valve. The next step is to actually perform refueling tasks, which is what the next phase, RRM3, has been demonstrating on station over a series of operations since 2018. RRM is a critical piece of the sustainable spaceflight puzzle that helps us with the ability to robotically refuel, repair, and maintain satellites in both near and distant orbits, well beyond the reach of where humans can go today.
As we travel farther into space, from low Earth orbit to the Moon, to Mars, maybe someday beyond that, clever solutions to supply problems, like stocking spare parts, will be a vital part of NASA's preparations. 3D printing is an emerging technology that may be used to create custom mission-critical parts. But in order for it to be practical, we first have to understand how particle shape, size, and distribution affect the manufacturing process when in the conditions found in deep space. One particular study is helping to explore those factors.
One of the things they're going to have to do for space exploration is do additive manufacturing, because we may have an engine part that fails, and you're certainly not going to take up spare engine parts. You're going to have to manufacture them there. And a lot of what we want to do with that means looking at microscopic particles, because they're building blocks. And now I think a big part of the future in this field, and for lots of different reasons, is active materials. So now we have ways that instead of just the particles being just particles, we can activate them, we can functionalize them, we can get them to associate with one another specifically. So one of the things we're aiming for is active self-replication, evolution in microgravity, to put lots of things together and to optimize properties using evolutionary processes from not living things, but mimicking what living things have done so successfully. We'll learn how to do that on Earth eventually. But before we do that, it's much better, because they have different densities, to do it in microgravity. It's always really important to do something at the forefront of science that will then become a forefront in engineering and production.
If you want another look at any of the stories we showed you today, go over to YouTube or Facebook at those addresses right there. You'll find them all, along with lots of other great features on a wide variety of NASA topics. If you're looking for good conversation about human spaceflight, check out Houston We Have a Podcast, our weekly show about all aspects of human spaceflight and NASA's missions of exploration. Today, Gary Jordan gets into the details of the one biological experiment that will fly on the Artemis 1 mission this year, which will focus on the effects of radiation on a biological sample in deep space, the first experiment like it since the Apollo years. Go to nasa.gov/podcast for this week's episode and all the previous episodes. In fact, the full library of all the NASA podcasts are there and on Apple Podcasts, Google Podcasts, and SoundCloud. You can get the latest from all over NASA delivered to you every week. Go to nasa.gov/subscribe to sign up for the NASA newsletter.
Wherever, however, whenever. We're here, there. We're everywhere. NASA Space Communications and Navigation. Exploration enabled.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather.
Rock, report range status.
Range green.
T-minus 5, 4, 3, 2, 1. Go for main engine start. 0 and lift off.
These are not the best of conditions, but for these knights of the highway, hauling a multi-million-dollar spacecraft more than 800 miles is all in a day's work. They're carrying NASA's next planet hunter, TESS. TESS stands for Transiting Exoplanet Survey Satellite. Its job is to search for habitable planets outside our solar system, but close enough to study. That's because we're not just looking for planets, we're looking for life. And the first leg of this spacecraft's journey to orbit is the ride to NASA's Kennedy Space Center.
So we left yesterday at Dulles. We left at 10:15 in the morning. We ran into an accident on 95, horrible weather, rain, down through Richmond.
The 16-hour road trip from Virginia to Florida wasn't easy, and protecting this one-of-a-kind spacecraft during its move was vital. Its shipping container is designed to keep TESS safe on the road.
The case gets used for a number of missions. It's mounted on some shock-absorbing bumpers so that we don't see a lot of the road noise getting into the spacecraft while we transit. We don't want any humidity inside. We don't want the temperature to change, so we have an air conditioning system as well. So we're just trying to keep it environmentally stable on the trip. And then we have very sensitive science instruments. So we actually provide a nitrogen purge. We spray nitrogen gas in to make sure that no air gets in contact with some of the sensitive components.
TESS has safely made it to Kennedy, where it is immediately taken to the Payload Hazardous Servicing Facility. But the job of keeping it clean is far from over.
TESS has really strict contamination control requirements. So what we've done is created a clean enclosure inside the high bay that acts like a clean room within a clean room, basically.
This is a unique mission full of first-time events that are sure to be a challenge.
TESS isn't like another mission. We haven't done another TESS. This is the first of its kind.
The time has come for this diverse team to put years of planning into practice as they begin the countdown to T0.
We've had a period of hard work that lasted for years, and when we finally get to the point of launch, it's very exciting. This is where the fun begins after we've gotten through all the early legwork and the planning, that we are actually going to now prepare a spacecraft for launch.
Building on the groundbreaking discoveries of the Kepler mission, TESS has scientists across the world excited about its possibilities.
TESS is probably one of the most interesting spacecrafts that I've ever worked on in my career, because of the science it's bringing back down to Earth. It's taking science fiction to science fact.
TESS will use the transit method to hunt for the telltale signs of planets orbiting other stars. In the transit method, the spacecraft watches the sky, and when a planet passes in front of a star, the star's light briefly dims. But Kepler only looked at one portion of the sky. TESS is taking this search to a whole new level.
What TESS is going to do is look around the entire sky around us to find stars nearby, much closer, 10 times closer than Kepler.
The really exciting part about this is it's the first all-sky survey of this type, using the transiting method to look for Earth-sized and super-Earth planets.
I think the real interest by the public in exoplanets is that everyone has a dream that there's an Earth analog out there, another planet that has the ability to have an atmosphere and water and sustain life on it. That, of course, is the ultimate sort of goal of exoplanet science.
When all the pre-launch tests, inspections, cleaning, and checkouts are done, it's time for TESS to join up with its launch vehicle, the SpaceX Falcon 9 rocket. This is a critical process, and it begins with encapsulation. This is the Falcon 9 payload fairing. Its smooth aerodynamic profile will give TESS a safe ride through the extreme heat and pressure of the climb to space. The vehicle systems engineer in NASA's Launch Services program plays a critical role in bringing the spacecraft and rocket together.
We have our hands in just about everything. We have to know enough about each system to know how they all interact together, and we have to know how the vehicle operates as a whole. So that's how critical the vehicle system engineer is in this whole process. We've been working very closely with SpaceX from the start, even when during their design phase and going through the whole certification process, the vehicle system engineer was integral in that role to understand what's going on with the SpaceX launch vehicle and how the NASA team can supplement a lot of what's going on.
The fairing is in one piece as it arrives at the door to the high bay. Inside, the test spacecraft is ready and waiting for encapsulation.
What's exciting about encapsulation is it's one of the last few things we do to prepare the spacecraft to get ready to go on the launch vehicle. It's exciting because you know we're going to be launching in a few days, which is the most exciting part of working this mission for the past couple of years.
TESS has to be ready for prime time when it gets into orbit, which means the last of its covers used during processing have to come off. Once TESS is inside the fairing, it won't be seen again on Earth. The payload fairing has been opened into two halves, and they're positioned on either side of TESS. The spacecraft is surrounded. Slowly and carefully, the fairings are moved into position until TESS is locked inside.
The encapsulated station has just been completed. Right now they're getting ready to lift the spacecraft, the encapsulated spacecraft, onto the trailer, which they'll then transport to the launch site. And from there, they'll mate the encapsulated spacecraft to the launch vehicle, and at that point, that's the last major thing before we get ready to launch. And that is exciting.
A specialized transporter rolls into the processing facility's high bay. It's here to take the payload fairing and its precious cargo to be attached to the Falcon 9 rocket. Getting TESS to this point was no small feat. It took several teams working closely together to ensure every system and every piece of hardware are ready for this mission. With the crane doing the heavy lifting, the fairing rises off the floor. It's guided toward the transporter, with team members helping every inch of the way. The fairing must be attached securely to the transporter for the final miles of its journey on Earth. There is no margin for error. The Falcon 9 rocket is waiting.
The Falcon 9 for the test mission is a new launch vehicle. We are planning to recover the first stage from the test mission on the drone ship, Of Course I Still Love You. If successful, this will be the 24th successful booster landing for SpaceX. By recovering first stages, not only do we understand more about our launch vehicle, it also enables us to reuse and refly that hardware, which is a key part of the SpaceX mission.
The fully assembled Falcon 9 rocket, with TESS on board, rolls out of the hangar at Space Launch Complex 40 at Cape Canaveral Air Force Station. Its final stop, the launch pad.
The SpaceX team is really proud to be part of such a cool mission, the TESS mission. The TESS satellite is looking for planets outside of our solar system in our galaxy, which aligns very well with the SpaceX vision to make life multiplanetary. To prepare for the rocket to be vertical on the pad today, the engineering team in the hangar did those final last checks. We mated the fairing to the rocket, and once the launch vehicle was finally checked out, the rocket rolled out of the hangar late last night and went vertical early this morning.
TESS is healthy. The Falcon 9 rocket stands ready. It's time for the final countdown.
So launch day is a pretty incredible day. Those last few minutes, you're just holding your breath. You find yourself holding your breath until, you get that T0 count. I lead a team of LSP engineers to successfully launch our spacecraft into orbit.
The SpaceX team has partnered with the NASA Launch Services Program, NASA Goddard, Orbital ATK, and MIT to enable that planet-finding mission.
We go on console about maybe 3.5 to 4 hours prior to launch. We do our voice checks to make sure we can activate and we have all the voice channels that we need to listen. We're listening to at any one point in time, maybe 6, 7 voice channels at the same time, so you're kind of training your ears to listen for your call sign. The team has a great responsibility to be able to look at all this data and say, yes, we are go for launch.
LD, go for launch. Falcon 9 is in startup. Falcon 9 is configured for flight.
3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying test.
Status check to proceed with terminal count.
There is a moment at the start of every mission when everything comes together. A moment when years of preparation and planning are put to the test.
Clear to proceed.
There are no second chances.
You have permission to launch.
Success or failure is just a heartbeat away.
Rocket report range status. Range green.
A spacecraft and its rocket on the pad, fully fueled and ready to launch.
Status check. Go Atlas. Go send.
In that moment, a controlled explosion is released with such intense power it can propel a spacecraft off the Earth and into space for the benefit of all. We call this moment T0. This is its story.
That's an insight.
NASA is about to do something we've never done before. Nestled along the mountains on California's central coast is a little talked about space launch center known as Vandenberg Air Force Base. From here, history is about to be made.
This is the first time we've had an interplanetary launch from Vandenberg Air Force Base in California. The cool thing about this launch is that we've got such a capable rocket, the Atlas V, we don't have to launch from Florida.
InSight is going to be the first time we've had a spacecraft leave Earth's orbit launching from California. We've actually done studies for it even up to decades ago, but it just comes down to whether or not the mission had extra propellant left over and whether there was an operational reason to switch from an East Coast launch to a West Coast. This is just the first time all of it came together.
What we're going to do is we're going to unload the spacecraft really carefully, and then we're going to drive it a couple of miles to the Astrotech facility where they have a clean room all set up for us. Got about 2 months here. All we got to do is clean it up, test it out, put the fuel in the tanks, and bolt it on the rocket, and off we go to Mars.
InSight is NASA's next groundbreaking mission, literally designed to break ground on Mars. Using probes and seismometers, InSight will listen for Mars quakes and measure how much heat the planet's interior gives off. If we're going to truly understand how rocky planets like Mars and Earth were created, we need to look inside.
It's unlike other missions that we've done to Mars. We have a number of orbiters, a number of landers that we've successfully explored this amazing planet. But this actually is the first mission where we're really looking on the inside, the inner space of Mars.
Sending a science mission to the Red Planet is never easy. Landing a probe on the surface is even harder. To accomplish this, InSight will have to shed its many components in a matter of minutes, bit by bit, like peeling an orange, until only the lander is left.
So the crew stage itself is the critical component that actually gets us to Mars. There's an aeroshell that absorbs the heat as we re-enter the atmosphere. That aeroshell enables us to go through the atmosphere of Mars successfully without getting the inside, the lander itself, too hot. We deploy a parachute. That parachute does two things. It really ensures the stability of the aeroshell as it's starting to get closer to the surface. It also slows down the spacecraft further until finally we drop out of the combination backshell and parachute, and then we do a propulsive descent down to the surface.
We know water exists on Mars, and where there's water, there could be signs of life. But we must ensure any organisms we discover weren't simply stowaways from Earth. This is where the Planetary Protection Team comes into play.
Planetary protection is what we do to responsibly explore other planets and moons in our solar system. In order to do that, we need to make sure that we send a clean spacecraft there. We would hate to get to another planet or moon and think we discovered life, but it was actually something that we brought with us. So we collect our samples on InSight, any part of InSight that's going to land on the surface of Mars. We bring it back to our lab and we process it using a NASA procedure. If we run into a situation where we take a sample and it comes back as having a higher number of bacteria than what we want, then we make sure that the engineers go back and clean those surfaces with the whole idea that we don't want to cloud our ability to potentially find life on another planet or moon.
Lockheed Martin Space of Denver, Colorado, built InSight with an extremely efficient design, streamlining what needs to be done at the launch site. They shipped the spacecraft to Vandenberg with no assembly required. Simply check it out, fuel it, test it, encapsulate it, and it's ready for launch.
The processing for our spacecraft has been very smooth. A lot of the processing had to do with fueling the spacecraft, removing some remove before flight items. Everything else was pretty much already installed on the spacecraft in Denver, Colorado before it was shipped here. And that's called a ship and shoot, which means there's not too much to do except for to fuel the vehicle and do some last-minute power-on checkouts of the onboard computers and subsystems.
These preparations are crucial. Everything must be working perfectly before InSight leaves Earth. This effort is designed to ensure a safe arrival and landing following the 6-month trip from Earth to Mars. In the meantime, United Launch Alliance, or ULA, is busy at their launch pad, Slick 3, assembling the world's most successful rocket, the Atlas V.
Well, I mean, we're building a rocket. What's not exciting about that? And really excited to be able to launch the first planetary mission from the West Coast.
First, ULA stacks their Atlas V booster onto the launch platform. Atlas V is powered by the mighty RD-180 rocket engine. The RD-180 is a powerhouse, burning highly refined kerosene known as RP-1 and liquid oxygen for thrust. For this mission, the RD-180 has more than enough power to get InSight off of Earth and heading towards Mars. When the booster's fuel is spent, the Centaur second stage kicks in and finishes the job. Centaur won't actually hit Mars. It will fly just past it. Final course corrections will be done by InSight itself to enter the Martian atmosphere and land on the surface. Once fueling and testing is complete, the team from United Launch Alliance will encapsulate InSight inside its payload fairing, the shell that keeps InSight clean and safe during its dangerous ascent through Earth's atmosphere.
We're at the phase of the mission where we're encapsulating with the launch vehicle, and the ULA team with their fairings now come in and they take the two halves of the fairings and they make a clamshell around the spacecraft to help protect it for the environments that we see during launch. And we do that because as we leave the Earth's atmosphere, the air and the molecules in the atmosphere would tear up our spacecraft otherwise, and the fairing is there to protect us.
With InSight encapsulated in its fairing, it's time to move the payload out to Slick 3. But this California coastline comes with its own set of challenges. The surrounding marine layer can swallow up a launch pad, reducing visibility to under a couple hundred feet.
So right now, it's on the transport vehicle and it's ready to roll. And we'll be rolling out around 2 a.m. At that point, we'll have a convoy that drives very slowly from the payload processing facility out to the Slick 3 Atlas V facility. And once it arrives, we'll hoist the encapsulated spacecraft up to the top of the mobile service tower and place it on the launch vehicle.
This morning when it was sitting on the truck and they put the crane on it, they started to lift it up. That's the last time this spacecraft's ever going to feel the ground of Earth. I'm just kind of jumping out of my skin. This is so exciting. We're getting so close to launch, and it's been a long, long road for me. This has been a challenging program. I mean, we've had a lot of technical issues to overcome. We actually had to stand down back in 2015, but since then we've gotten it all together, and things have been going so smoothly the last year. We really feel really confident about this launch now. We got it on top of the rocket. We're going to blast it off in just a few days, and when it gets to Mars and lands, finally it will have solid ground under its feet again and get to work on probing the depths of Mars.
But InSight won't be traveling alone. Hitching a ride to the Red Planet are a pair of CubeSats, twin satellites called Marco A and Marco B.
So Marco is a dual payload riding as a secondary mission on its way to Mars.
So Marco is a pair of CubeSats, and CubeSats are really small spacecraft. They're essentially the size of a large cereal box, so about this big.
It's going to be relaying telemetry from the entry, descent, and landing of InSight back to Earth in near real time. After InSight is deployed on orbit and is heading to Mars, Centaur, which is behind me, ejects Marco A into orbit, and it'll slowly rotate itself so that Marco B ejects 180 degrees on the other side of the vehicle.
But Mako is a technology demonstration mission. It's actually one of the smallest spacecraft we've ever launched to interplanetary space. It's the first interplanetary CubeSat. So in of itself, it has all of these technology that we've never tested in deep space before. So if Mako works this time, one of the cool things that we could do is actually replicate that system and fly it with other missions in the future. And whether you're going to Mars or Venus or maybe even further away to an asteroid, you could think of it as bring your own telecom relay.
So everything went well today with the lift of the spacecraft and mate onto the rocket. It started off very foggy and windy, and right now it's a beautiful day, just typical California weather. And now we're ready to go to Mars.
But just as twilight falls across the base, the fog returns, cloaking the coast with a bone-chilling mist that will last until daybreak.
As we get closer to T0 liftoff time, a number of activities have to happen. There's a mobile service tower around the Atlas V rocket, and the InSight spacecraft is on top of the rocket, enclosed in the payload fairing. So we're going to back that mobile service tower away from the rocket to leave it exposed just beside the umbilical tower.
Stand engineer, proceed with MST roll to park position. Roger. MST bores shall be closed in park position. Roger.
The final launch pad preparation is underway. Once the mobile service tower is rolled back, InSight and Atlas V are just hours away from T0. Basking in the searchlights of the West Coast facility, they are presented with the glamour of a Hollywood premiere, fitting treatment for such an historical mission.
So there's a lot of excitement within the NASA launch team about the InSight mission. First time we're going to launch from the California coast, going to Mars. And what is really exciting to the team is this is the culmination of a lot of work. The teams have been working on this mission for over 5 years, and today is the day that they will see all of their hard work rewarded.
Status check to proceed with terminal count. Atlas systems. Propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur systems. Propulsion. Go. Pneumatics. Go. LH2.
Go.
Facility. Go. Range coordinator.
Clear to proceed.
Launch director.
LC, you have permission to launch. Go Atlas.
Go Centaur. Go InSight. Proceeding with the count.
We're at T-minus 8, 7, 6, 5, 4, 3, 2, 0. And liftoff of the Atlas V, launching the first interplanetary mission from the West Coast, and NASA's InSight, the first outer space robotic explorer to study the interior of Mars.
Seconds after liftoff, the rocket punches through the marine layer, lighting the night sky for miles, visible all the way down to Los Angeles. An infrared camera showing the long tail of the exhaust plume captures some of the ascent, as well as an onboard ascent camera.
And we're nearing booster engine cutoff, or BECO.
Back to 4.6 Gs in preparation for BECO. Boost phase cooldown has completed. And we have BECO. Shutdown looks good. Stage separation. We have box and fuel pre-start. G&2 purge firing. The RCS is underway. We have ignition and full thrust. And we have indication of payload fairing jettison. Looks like a good step.
And the payload fairing that was encapsulating the InSight spacecraft has been jettisoned. The RL-10C engine, the second stage of the Centaur, continues to burn.
An hour and 28 minutes into the mission, the InSight spacecraft and the Marco twins are deployed from the Centaur upper stage, beginning the long voyage to Mars, where InSight will go to work shedding light on secrets hidden in the depths of the Red Planet.
Hey there, I'm NASA astronaut Ricky Arnold. Welcome aboard the International Space Station. Today we're going to talk about the Space Station truss. The truss segment is just about 100 meters from side to side.
A truss is a segment or part of the whole integrated truss structure. The trusses are used to support the 16 solar array panels, which provide energy for us, and radiators which get rid of excess heat that builds up inside the space station. The design of the truss involves triangles and beams, which can be seen on Earth in structures like bridges. Why triangles? Well, this is because of their unique geometric properties, their methods of transferring loads, and their spatial openness. Triangles are more rigid than rectangular shapes because they have fewer joints. The larger number of joints in a shape, the more prone that shape is to being impacted by shear forces.
What I'd like to talk a little bit about today is some of the forces that can act upon the truss. Well, the first force I want to talk about is compression force. And compression force is just like it sounds, two things coming together. So if we apply a compression force to the truss, what do you think is going to happen? Well, let me go ahead and do it. And you can see right here where the truss would bend. What do you think the opposite force of compression is? Yeah, it's going to be pulling apart. We call that a tension force. And a tension force is what's going to help maybe even rigidize the truss segment, but it also could potentially pull it apart. I'm not going to pull apart this tape measure because we probably need it later for some work we have to do.
Now, if you look carefully, this next force I want to talk about
is basically kind of like a twisting force, and we call it torsion. And even when I just let go of the tape measure, you can see it will actually start to happen a little bit. You can start to see, because the center of mass is actually right here, where most of the tape measure is located. And when I let it go, the tape measure itself starts to twist just a little bit. Finally, the fourth force
that can act along a truss segment
is that can occur at a single point where two opposing forces work on a single point along the truss, just like they can upon the Earth's surface. Think about some earthquakes. You can have a plate that is, or along a fault line where one side of the fault line is moving upward or being forced upward while the other side is moving downward. And that force in one point in opposite directions is called a shear force. And we can also have that happen on the truss segment. Something like this.
One thing to think about, where do these forces come from?
One force, even though we're up here largely out of the Earth's atmosphere, we do still have drag with the Earth's atmosphere, which can impart loads on or impart a force on the truss segment. Another, I already hinted at earlier, is crew working inside. We're up here, we're exercising, we're moving really heavy pieces of equipment around. So we have an amazing engineering team on the ground, and we have specific disciplines that their job is to monitor all the forces imparted upon the International Space Station. They keep track of all those various forces I talked about and where they could be coming from, the atmosphere, visiting vehicles, or even things that the crew are doing inside the space station. And to make sure that those forces aren't significant enough to cause any damage to this wonderful laboratory and living space we have up here in low Earth orbit. Thanks so much for joining me today. We'll see you next time. So long.
Wherever, however, whenever. We're here, there. We're everywhere. NASA Space Communications and Navigation. Exploration enabled.
Mission Control Human Spaceflight is made possible through the generous support of Alabama Bicentennial Commission, the Daniel Foundation of Alabama, Wells Fargo, the Malone Family Foundation, the Robert R. Meyer Foundation. Mission Control is a production of the IQ Learning Network, a division of Alabama Public Television.
You're looking good here. Roger.
Hi, I'm Dorian.
Carmen here.
This is Luke, standing by.
Here's Chandel. And I'm Kaylee.
We're interrupting your regularly scheduled programming for a very important reason. As members of the STEM Brigade, our mission is clear. Learn science, earn badges, and help others to learn too along the way. Right now, we're working on earning our cadet rank in space exploration, and our squad has a very important mission.
To learn all about the history and the science behind human spaceflight.
And as we sprint through this learning marathon, we'll try and earn 6 different merit badges: the space race, rocket boosters, shuttle, life systems, future exploration, and space computer controls. We'll be reviewing the badges we earn throughout the program, so pay attention and follow along, and you too can be honorary virtual members of the STEM Brigade.
We're ready to blast off. Mission Control, do you copy?
Since the dawn of humankind, the stars have been there waiting for us. But for the majority of human existence, leaving Earth was nothing more than the desire of an overactive imagination. If only they'd known, the stars have always been reachable. They were just waiting on us to find the right path.
Last century, following the birth of the airplane, scientists like Robert H. Goddard, perhaps the first great rocket scientist, started getting close. Rocket technology advanced quickly, especially during the Second World War, when rocket technology was used, regrettably, as a new kind of weapon. But from the dust of that terrible war came something better: the space race.
The space race was between 2 of the most powerful countries to emerge from the rubble of World War II, the Soviet Union and the United States. The space race ultimately amounted to a series of one-ups, as the Soviets and the Americans raced to see who could accomplish what amazing feat first.
The Soviets struck first, putting the first satellite in space, the first human, the first spacewalk. But the Americans were right behind them, step for step, thanks to early space programs like Mercury, which, among its many accomplishments, sent American John Glenn orbiting around the world. The 2 powers were both on a chase for the same finish line: who would be the first to get to the moon?
We choose to go to the moon in this decade and do the other thing, not because they are easy, but because they are hard.
On July 20th, 1969, the Americans did the impossible.
That's one small step for man, one giant leap for mankind.
Neil Armstrong, along with Buzz Aldrin, became the first human beings to ever walk on the moon as part of the Apollo 11 mission. It was a day that changed the world. 2 men walked on the moon that day, but the support of thousands of men and women back on Earth put them there, and they all deserve credit for this landmark accomplishment of the human spirit. When astronauts say Houston into their radio, they're referring to Mission Control at Johnson Space Center in Houston, Texas. Mission Control has been the center of communication between Earth and human spaceflight from the early days of Gemini and Apollo to communication with the International Space Station today. I'm joined today by legendary flight director Gene Kranz, who was flight director of the Apollo 11 mission that first landed on the moon, and Apollo 13, where an explosion on board the spacecraft put Mission Control to the ultimate test. Thank you so much for being here with us today.
It's a pleasure to be here, and thank you very much for the opportunity.
What is the role of Mission Control?
Mission Control is the center where you pull all the people together, where you've got communications to the launch site, you've got communications to the tracking station. So it's basically the overall hub for communications. In addition to that, the controllers here are prepared to take any actions necessary for crew safety and mission success.
Could you tell me a little bit about your job as a flight director?
As flight director, I have the ultimate responsibility for performance of this room here. During the course of the mission, I am the final person to make decisions. There is no higher authority than me. And as mission time approaches, I look at the decisions I got to make and I see if I got a set of notes to fit that, and I write it down as sort of a timeline. Because the one thing I have to do in this room is to manage the clock. So it's up to me to know how to use every second that we've got in the decision process. Most of our decisions are hours. Frequently I'll get one that's down in the minutes. Ones that we do in seconds, I have to know instantly and tell the guy what I want done.
July 20th, 1969, moon landing. As the world watched, Houston waited for the call. What was the feeling like in this room?
That moment, that time in history, we knew that we had 2 minutes, 120 seconds of fuel in that tank at a 30% moderate throttle setting. So I had one controller in this room who had a stopwatch. He was counting out seconds of fuel remaining. Now, at the time he's doing this, the crew is trying to go around and find their landing site. As he got down close to the surface, the dust on the surface was moving with him. So it was really hard to figure out, where can I land, and where's the right place to land, etc. And we kept calling out 60 seconds of fuel remaining.
60 seconds.
And about the time we said 30 seconds, we saw the crew going through engine shutdown.
30 seconds. Forward. Okay, engine stop.
And that's when we heard the words, Houston, Tranquility Base here, the Eagle has landed.
Tranquility Base here, the Eagle has landed.
And boy, all through this thing, I had a hold of one of these handles because in those last seconds, it was totally up to the crew. My job was over. I got him down close. He had to land. But I was holding on to that guy, and I don't think I took a breath. And that was true of everybody in this room.
Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot. Thank you.
Okay, Apollo 13, the infamous. Houston, we've had a problem. What was going on in your head at that moment?
You have to think your way through problems. So as soon as I heard that call,
Okay, Houston, we've had a problem here.
Earlier in my shift, I had had 3 minor electrical problems. And my immediate thought is, it's a minor electrical problem. We'll sort it out. We'll put the crew to sleep, and then we'll work the problem.
Stand by, 13. We're looking at it.
Then about a couple minutes later, one of my controllers said there was a pretty big bang associated with that. The crew reported a bang, and I said, okay, something I don't understand is happening right here. I better proceed more carefully. And then about 10 minutes later, Jim Lovell's looking outside the hatch window, and he sees a jet plume going out there. And he says, Houston, I think we're venting our oxygen.
We are venting something out into space.
Roger, we copy your venting. And that was when I went into survival mode. Say, okay, I'll flight controller, settle down, quit your guessing, let's start working this problem. And that was really the key to getting this room now focused on the problem at hand. We had to make several tough decisions. We had to make the decision, how are we going to come home? Because we're right in the area where the gravity of the moon is balanced to the gravity in Earth. So we're right in between those two. And if I use my big engine, I can be home in a day and a half. If I go around the moon, that's my other option. It's going to take 4 to 5 days to get back home. So which way am I going to come home? I don't know what happened to that spacecraft, so I better be careful. So I'm going to go around the moon.
Here in Mission Control, we're now looking towards an alternate mission. Swinging around the moon and using the lunar module power systems.
And if I go around the moon, I got a 2-day spacecraft. It's going to take 4 days to 5 days to get back home. So now I got to figure out how to take that 2-day spacecraft, water, oxygen, electrical power, and stretch it out.
And we have a procedure for getting power from the LEM. We'd like you to copy down.
Because the key thing is, once the crew's up in space, you don't want to make a mistake because you're too conservative. You got to wait until you got enough data to make the right decision.
Another cheer in the control room as we head splashdown.
What advice do you have for a young person who's interested in a career in mission control?
Dream, aim high, never surrender. Dream is your goal. What do you think you're best at? And start going after that goal. And what you have to do is you have to have that goal, that dream, so strong that you'll pick up and carry on. It's what I call tenacity. staying tough, working tough, being tough when it relates to going after your goal. So dream, aim high, never surrender.
That's great advice. Well, thank you so much for talking with me today. It was really nice meeting you.
Will you give me 5?
Yes.
Okay. Thank you. I enjoyed it too.
Dream, aim high, never surrender. That's exactly what the Apollo astronauts did. And so did the many men and women who built the incredible machine that got us to the moon, the mighty Saturn V rocket.
Among its many contributions, Huntsville is where the Saturn V was dreamt up and designed by German rocket scientist Wernher von Braun. It's also where the Saturn V's mighty F1 engines were initially tested, and continues to be a major force in the exploration of space to this day. During my visit to the U.S. Space and Rocket Center, I headed out to Rocket Park to learn more. I'm joined now by Ed Stewart, head archivist at the U.S. Space and Rocket Center, to talk about rocket development in Huntsville. Thanks for being with me today.
My pleasure.
So can you tell me a little bit about the early days of rocket design in the U.S.?
So a lot of American rocket technology is really based on or evolved out of the V2s that were developed in Germany during World War II. The V2 was a liquid-propelled rocket that really was a terrifying invention, and the masterminds of the V2 program was a gentleman named Wernher von Braun, who actually came over to the United States after the end of World War II and became the head of the guided missile development program for the U.S. Army. And then eventually NASA was formed in 1958. He started working on civilian space exploration-based projects. And so von Braun and most of his team transferred over to Marshall Space Flight Center when it was opened in 1960. And that's kind of where you see the beginning of the development of these big space exploring rockets. If you look, for instance, at the Saturn I behind us, the tanks, the skinny tanks that are kind of clustered together around the outside of the first stage, are all stretched out Redstone rocket propellant tanks. And so they took those kind of pre-existing elements, combined them together to produce a 1.5 million pound capable first stage. And that is the first sort of heavy lift or really big rocket developed for the United States. And it was also the first vehicle developed specifically for space exploration as far as like kind of a ground up design.
Building off the successes of the Saturn I, Dr. von Braun's team went to work building the biggest, most powerful rocket the world had ever seen to take us all the way to the moon, the Saturn V. The Saturn V was comprised of 3 stages. The first had 5 massive F1 engines that generated over 7.5 million pounds of thrust at sea level. The second stage, designed to push the rocket through the upper atmosphere, had 5 smaller but even more efficient J2 engines, creating 1.1 million pounds of thrust. Finally, the third stage's single J2 put the Saturn in a temporary parking orbit before firing up again for something called translunar injection, the astronauts' trip to the moon, at more than 24,000 miles an hour. While on the way, the crew unpacked the Apollo command and lunar modules through a delicate series of docking maneuvers to prepare for lunar orbit and landing, and finally jettisoned the last stage of the mighty Saturn rocket.
Looking good. Over.
While the Saturn V was a beast of a machine, you might be surprised to learn that today, there's thousands times more computer memory in the smartphone in your pocket than the Saturn V had in its entire enormous structure. But that's not to suggest the Saturn V was dumb. It was anything but, especially for 1960s computer technology. While still at the U.S. Space and Rocket Center, I discovered all about how it worked with the help of docent and former Apollo computer programmer, Luke Talley. So can you tell me a little bit about how the computers on the Saturn V worked?
In the 1960s, what we could put together with a digital machine really couldn't do all the job we needed to guide a missile of the Saturn V. So what we have is a combination of a digital computer and an analog computer. So this is a 26-bit machine, and each of these blocks now has 4,000 words of memory. All right? So there's 16,000 and another 16,000. So when the rocket's flying, both of these are executing the same flight program. And they're comparing the outputs to make sure they're getting the same results. During the flights, we only had a few miscompares ever. Even though it looks kind of old and antique-y like, it worked quite well. So the redundancy is strictly for reliability. Now in the logic itself, we have these circuit boards Each circuit board has 35 chips on one side, 35 on the other. Give you a feel for yesterday and today. The processor that we built up here with this technology, we would execute about 8,000 calculations a second while it's flying, okay? Your cell phone's doing probably 2.5 million or so calculations a second. So, in order to make this thing fly, you have to do navigation, guidance, and control. The digital computer could do these timed functions, and it did navigation and guidance, but the control function was actually transferred over to this thing, looked like a barrel over here, an analog computer. The analog computer, it flows in, you're multiplying or dividing or whatever you're doing, comparing the data as it comes through, and it just keeps flowing, all right? And it goes right on out, and in real time. Whereas the digital computer, it'll get an interrupt, and it'll go do something, and then it'll go back to doing what it was doing previously. Okay, the computer itself does not have an operating system. So we have a series of signals coming in. When the signal pops up, we go do something. The next signal pops up, we go do something else, all right? And then we also have timed functions, in other words, there's a clock. When this clock comes up, that says to start navigation, guidance, and control. Start it, navigation, guidance, control. So we have clock signals and we have interrupts from the rocket itself.
Thanks for meeting me today, and thanks for telling me all about computers.
You're welcome.
All aircraft rely on a force called thrust to work, which is generally created through applying Newton's third law of motion. For every action, there is an equal and opposite reaction. What does that mean? A good example is rowing a canoe. To move the canoe forward, you push back against the water. This action, pushing back, creates the opposite reaction of moving the canoe forward. In a propulsion system for a rocket, Newton's third law is applied by exploding fuel and a source of oxygen, or oxidizer, in a combustion chamber, which, as every action creates an equal and opposite reaction, this combustion creates a reaction of exhaust, which works as a thrusting force on the system. It's amazing it works. It's more amazing we figured it out. But perhaps the most amazing part of it all? Leaving the Earth was always physically possible, even when humankind believed it was just a fantasy. We just needed the right technology to take advantage of the physics that were already a part of our world. Who knows what other seemingly impossible tasks humankind will make possible in the future?
Speaking of rocket engines, meet the RS-25, formerly the main engine of NASA's space shuttle, and, with some amazing new upgrades, rocket engine of the future, primed to give the Saturn V's F1s a run for their money. These super RS-25 engines will power NASA's Space Launch System, the vehicle that will one day take us back to the moon and even beyond to other planets like Mars. I headed down to NASA's Stennis Space Center in Mississippi to get a first-hand look.
So this is an RS-25 flight engine.
So when was this originally designed, and how has it been updated since then?
It actually flew during this space shuttle program on several space shuttle missions. And so what we're doing now with this engine is we're actually repurposing it from the space shuttle program and actually taking it to making it a little bit smarter and a lot more powerful for the Space Launch System.
How exactly does a rocket engine work?
So really, what's best for us to do, let's just go upstairs, we'll get real close to parts of the engine. I can point out and talk about how we use liquid hydrogen, liquid oxygen to produce the thrust that we need on these engines. So these areas here, this thing is a high pressure pump. And so there's one just like it on the other side of the engine. This pump is pumping liquid oxygen. On the other side of the engine, the pump is pumping liquid hydrogen. So liquid hydrogen is our fuel, liquid oxygen is our oxidizer. Liquid hydrogen is the second coldest element on Earth. It's minus 423 degrees Fahrenheit. And then liquid oxygen on this side of what we're talking about, it's around minus 300 degrees Fahrenheit. So normally when we think about liquid hydrogen and liquid oxygen coming together, we think about water. And we say, okay, we have hydrogen and oxygen and it comes together and we make water. So how do we make rocket fuel out of water is really the cool question, right? So what we do is we actually take these two elements and we put them under extreme pressure, somewhere between 9,000 and 11,000 pounds of pressure inside the engine. When they come together at that high pressure, they actually hit each other and explode. And that explosion is what we're controlling in the main combustion chamber that comes out of the nozzle. And that explosion coming out of the nozzle is the thrust of this engine, and it's what's making that thrust. So coming out of the nozzle at the bottom is 6,000 degrees Fahrenheit. So you think about instantaneously it goes from these cold elements to plus 6,000 degrees, and that's what's making this, how this engine works as far as producing thrust.
Awesome. Thank you so much for your time. It's so awesome. Very interesting. I learned so much today.
Looking good. Over.
All right, let's check in and see what badges we've earned. So for now, we've only got the space race and rocket boosters. 2 down, 4 to go. After reaching the moon, which many consider to be the end of the space race, NASA's human spaceflight program began to change directions and focus on humans staying in space as long as possible.
Following the Skylab program of the 1970s, NASA began its longest-running program to date, the Space Shuttle program. The Space Shuttle was a bold new reimagining of manned space exploration.
Low Earth orbit, an orbit around Earth some 1,200 miles above the planet's surface, was now the goal. And instead of rockets and capsules that were one and done, now reusable winged orbiters would be used.
First launched in 1981, NASA's fleet was comprised of 5 orbiters. All in all, America's space fleet flew 133 successful voyages beyond the Earth, leading to countless scientific advancements.
Without the shuttle, we'd also be without one of the most important scientific devices of the 20th century, the Hubble Space Telescope, a window to the cosmos that's given humankind some incredible first-time peeks into some of the universe's most amazing sights. While at Kennedy, I had an amazing opportunity to learn more about the shuttle program firsthand from one of the brave astronauts who flew as part of the program. I'm joined now by astronaut Charlie Walker, who actually served as a payload specialist on this shuttle right here behind me, the Space Shuttle Atlantis. So Charlie, tell me a little bit about your experience on this shuttle. Were there any moments that really stood out to you?
Well, launch is always a very memorable experience. Atlantis, during the entire flight, had virtually no electrical or mechanical problems, which was a joy for the crew because we could spend more time getting the useful things done and looking out the window.
So what were some of the most innovative things on the space shuttle?
Innovative. Wings to start with. The earliest manned or piloted spacecraft was a capsule. So wings was a very innovative approach to space travel, not only launching to space, but also returning to Earth. And the wings were only useful on the return to Earth. Another innovation was this Canadian-provided robotic arm. It was an international project, very useful, including on my flight on Atlantis, in which 2 of our crew members did a unique spacewalk to demonstrate construction in space.
So what would you say the training was like to become an astronaut?
To work inside a spacecraft in orbit takes certain necessary skills and personal characteristics. For instance, you had to go through a screening process before you even went into training for the managers to determine that you weren't claustrophobic. You can't be afraid of small spaces in a spacecraft because you can't open the door and get out. And the training then included a lot of course, systems training. Now, I didn't need to learn every system in there. The mission specialists knew how to operate every orbital system with a spacecraft while it's in orbit. The pilots fly it up and fly it back home, and they didn't teach me to do that. That was fine. I was a payload specialist. And then, of course, I had to be very trained up on my particular research, as well as learning to work with my fellow crew members. That took well over a year.
What lessons did we learn from the shuttle program that we're applying to the future of spaceflight?
The Space Shuttle was the first to utilize in that capacity solid propellant first stage booster rockets. We learned lots of lessons from using those booster rockets to launch shuttles into space, and solid rocket boosters are planned and are in development and testing right now for use in the next big NASA launch vehicle, the Space Launch System. And the engines on the Space Shuttle, they're being modified for use on that next big launch system as well. But also learning to train efficiently and effectively crews to work together, that was an important lesson that's being used in the future. The overall efficient technology that was used to control, to do life support on board Space Shuttle. So all of those things, those are what comes immediately to mind as lessons learned from Space Shuttle for future space activities.
Well, thank you so much for taking the time to talk to me today.
My pleasure.
Thanks to the shuttle program, NASA was able to set its sights, with the help of the rest of the world's space community, on an even greater goal: the world's first long-term home in outer space, the International Space Station. NASA, along with Russia, Japan, the European Space Agency, and Canada, slowly constructed the International Space Station for nearly a decade and a half, from 1998 to 2011, the same year NASA finally ended the shuttle program.
The ISS is a major achievement of human ingenuity and science, and as of today has housed more than 236 people from 18 countries. Truly a space station serving all of humankind.
Thanks to the countless experiments that can only be studied in low Earth orbit, amazing advancements have been made. But none of those experiments could ever have gotten off the ground without the help of an amazing support team in the Rocket City.
We're standing outside the Payload Operations Integration Center at the Marshall Space Flight Center. This is the primary Space Station Science Command Post, and it is here that all of the International Space Station science experiments are coordinated. I'm joined now by Payload Operations Director Christy Robertson. Thank you so much for joining us today.
Thank you. It's good to be here.
So why is this called the Payload Operations Integration Center? What exactly is a payload?
So a payload is the experiment itself. So each experiment that a scientist launches to station is called a payload.
What happens on a typical day in the Payload Operations Integration Center?
7 days a week, 24 hours a day. A typical day begins with a crew wake. Throughout the day, our job here at the POIC is to interface with the crew for their science experiments to ensure that those experiments are executed and be kind of the liaison between them and the payload developer that actually developed the science experiment.
So what do you guys do to help the astronauts in space doing these experiments?
When they have questions or issues, anomalies, they'll call down to POIC, and then we work to get them an answer and a resolution so that they can proceed through their experiment.
What sorts of scientific fields are researched up there?
So we have everything from combustion to rodent research. We also have various life sciences, human research sciences that are done. So many of the astronauts participate in what we call human research experiments, which are those things that evaluate essentially the toll that space takes on a human body.
How does the payload operation team prepare for a scientific expedition?
So we start about a year and a half out preparing for each expedition. And part of what we do is actually some on-hands training. So we have a center downstairs that I can take you and show you, and we can kind of see some of the on-hands training that we get.
Okay, cool.
One of the things we have for our controllers here to be able to utilize when they're developing procedures as well as getting ready for operations are our hands-on environment. This is the lab that we're currently in. It is a true to life-size mock-up of the lab that is on space stations, the U.S. laboratory. So one of the racks that we have there is this one, which is the MSG, which is a microgravity science glove box. So as you can see, the work volume will extend. That just allows the crew members more functionality. So if you want to, you can go ahead and stick your hands in there, see what it would feel like to have a glove on, and see what adjustments you can make. Create a pressure right here for you. So you should feel, see these other gloves kind of fill up around you.
Thank you so much for teaching me all this stuff. I really enjoyed it.
Thank you, and thank you for your time.
Providing for the day-to-day needs and resources of the men and women living and working on the ISS presents constant technical challenges, like recycling precious onboard resources with its water recovery system. The ISS's water recovery system provides clean water to the astronauts by recycling and purifying water waste on board. It does this with the help of the Water Processor Assembly and something called the UPA, or, well, the Urine Processor Assembly, because it recycles, urine. On the ISS, the #1 priority of a #1 is to recycle it. Urine is turned to water with the help of a low-pressure vacuum distillation process. Distillation is the process of heating a mixture of liquids until they become a gas, then condensing the gas back into separate liquids, which successfully removes the clean water from the urine. The water is then moved into the WPA's purification system. The ISS maintains extremely strict purity standards before any recycled water can be consumed by the crew, especially recycled urine.
I am here with Jennifer Pruitt, who is the project manager for the International Space Station Urine Processing Assembly. Why do we recycle urine and sweat for astronauts in space?
When we go somewhere where there isn't water available, like in space, we need to have those systems. It's crucial for humans to survive. It's very expensive to ship up all the water that we need, so what we have to do is recycle it, which is a much more cost-effective way of giving the astronauts water.
What percentage of the water on the ISS is recycled?
Of all the water that's on Space Station, we have a couple different sources. We have our urine, and that's where a lot of the water comes out of our bodies. There's also some that comes out in our breath and in our sweat when we work out. So if we take all of that together, overall we recycle about 92% of the water, maybe a little bit higher, and we're trying to get as close as we can to that 100%. We have developed our hardware here that we now use on the space station. So I'm going to show you our urine processor that we have right here. This is the same as what is on ISS now with a few tweaks, but we have these clear containers that we use on the ground only. The ones on station are big metal tanks. In space, people would pee, it would fill up, and when it got to a certain point, that would start the process. So it runs in a batch. We have a couple pumps that move the fluid through. These two here, one moves all of our fluid, and it's a peristaltic pump. So it's kind of like your esophagus where it pushes everything through, trying to not use gravity, so it's just that push. We have a purge pump, which is reducing the pressure in the system so that we don't have to boil the water at high a temperature. So to try to save power, we instead bring the pressure down. So we're lowering the pressure so we can boil the water at a lower temperature as well. And we do that in this guy here. This is the distillation assembly where we actually boil the water. He's kind of like a washing machine. He's a big drum. The urine goes in, it's boiled, and the steam comes out, and then they're separated from that point on. So the good clean water is what goes on to the water processing, the next cycle, and all of the brine will come back to the beginning, and that will be concentrated until we get enough water out, and then that brine is what's thrown away at the end.
Thank you so much for showing me all of this stuff and explaining to me all these awesome processes.
You are so welcome, and if you ever want to come back and help donate to our Mars mission, you are more than welcome.
While the ISS is an unprecedented, literally out-of-this-world creation, it sometimes requires maintenance and repairs. When something needs to be altered or fixed by an astronaut on the outside of the station, they perform what is known as an extravehicular activity, or EVA, and a very special tool is required.
A spacesuit. Spacesuits are more than just an astronaut's Sunday best. They're highly engineered life support systems in their own right, allowing astronauts to survive and work in the cold vacuum of space. While in Huntsville, I was able to make a stop at the U.S. Space and Rocket Center to learn more about them. Hello, I'm here with Joseph Vick, who is the manager of museum education here at the U.S. Space and Rocket Center in Huntsville. What can you tell me about the history of spacesuits?
Spacesuits originated here on Earth for exploration of the Earth. When we had the need to go and dive, so think of really old school diving suit. Post that, we went from exploring the oceans to exploring the skies. So as astronauts, we begin to explore past our atmospheres. We need even more protection from those lack of pressures. The first of those were used during our Mercury mission, so it was the first manned mission. The suit they had was a very early elementary spacesuit. The second manned mission of NASA was the Gemini suit. They needed to develop a new suit so that they could exit out of the capsule. The first American to do that was Ed White. And then for Apollo, they needed a very much substantial suit that would enable them to not only get out of their vehicle, but walk on a surface that was foreign to us.
What it would be like to go into space without a spacesuit. So I need your help. If you could put a little bit of pressure on top.
That'll provide our earth pressure, which is 14.7 pounds per square inch. That's what helps us maintain our shape and function, just like AstroDuck here. I'm going to remove the pressure from this chamber. So it's just as if we're going to have AstroDuck in outer space. So as I remove the pressure, the air pressure within, notice what's happening to our AstroDuck. There's no more pressure to keep AstroDuck as he was shaped here on Earth. So he would expand and expand until eventually pop. So from AstroDuck's perspective, you need a spacesuit. Spacesuits have multi-layers. So each layer has its own importance for protection of the astronaut. So notice the first on the outside piece, it's mostly for protection from flying debris when you're in space. Micrometeorite garment. So if anything were to hit this, it would bounce off and not cause any harm to the astronaut. You have layers, multiple layers of a mylar-like material that provides a thermal protection. Other layers are what are called pressure bladders, which allow the pressure inside of the suit to maintain that pressure. And then you have at the very closest to the skin this ventilation garment, which is the movement of the water over the pipe so that water would flow over the astronaut's skin and body, creating a cooling sensation for the astronaut.
Thank you for all this knowledge. Next time I see you, I'll have my own personal spacesuit.
Oh, great, and I'll catch you on Mars.
Looking good. Over.
The place where all of NASA's iconic launches began is Kennedy Space Center in Cape Canaveral, Florida, America's spaceport. I was lucky enough to get special access to the newly renovated Launch Pad 39B, where Apollo and shuttle missions were once launched, and where they'll soon be joined by the Space Launch System. I'm here with Tim McDaniel, who is the Launch Pad 39 facility manager. So Tim, can you talk us through getting ready for a launch? What kind of things happen on the pad?
They have to have the electricity hooked up to it, they have to have water hooked up to it, and just like your car, it has to have fuel. On each side of the launch pad, there's liquid hydrogen on one side and there's liquid oxygen on the other side. They bring the fuels together and they fill the rocket. Then once it's fueled, they do all their preparations and getting ready for it. They do all their checkouts, they do all the electrical checkouts, the man checkouts, the systems checkouts. This water tower here, it has several thousand gallons of water in that tank. This tank actually drops every bit of water out of that tank in 1 minute. It flows from that tower and it goes up through the mobile launcher, and it has some big heads that spray water in the direction of the flames where it comes out the bottom of the rocket. And that helps for sound suppression, because as you can imagine, it'd be very, very loud.
What modifications are currently being made to the launch pad for SLS?
They redone the flame trench. They put all new bricks in the flame trench. They also, currently, they're underway, they're making a new liquid hydrogen tank. This liquid hydrogen tank will be the largest in the world. It will be approximately 3 times the size of the current one we have.
Well, thank you so much for meeting with me today.
Thank you.
Time for another badge review. We're adding shuttle and life systems to our collection. Home stretch now, guys. Just 2 more to go. And to keep us moving, let's kick it back to Kaylee and Chandel, who are learning about the future of the United States manned space exploration program.
Ever since the shuttle program ended in 2011, NASA has had no fleet to send astronauts to the International Space Station. While private companies like SpaceX, Boeing, and Northrop Grumman have learned to launch satellites and ISS supplies at launch sites around the country, and NASA has launched rovers like Curiosity to Mars, the agency has relied on the Russian space program and its Soyuz rockets to deliver astronauts to the space station.
But NASA won't be without a space vehicle for much longer. The Space Launch System, NASA's super heavy-lift expendable launch vehicle that's ushering in a new direction for NASA's space fleet in the tradition of the Saturn V, will be the most powerful rocket in existence, with thrust capacities even greater than its moon-delivering ancestor, and with crew on board the Orion capsule up top, NASA will once again be able to send astronauts distances beyond low Earth orbit.
I'm here with Scott Wilson, NASA Orion Productions Operation Manager, and Jules Schneider, Lockheed Martin Orion Productions Operation Manager. Thank you so much for joining with me today.
Well, thank you very much for having us.
Thank you.
Can you give me a brief history of the Orion program?
After the shuttle program, we were looking to decide where do we go next, right? So for many years, we've gone to what we call low Earth orbit, which is about 250 miles above the planet. And that's where the ISS is. And we really wanted to begin exploring deep space, which is getting us back to the moon and Mars and beyond. So we did a lot of studies trying to figure out what would our spacecraft look like, and eventually that led to Orion, and that's what we're building today.
And why did we go with the capsule design again?
Well, in the early studies, we looked at should it have wings like a shuttle, should it be a capsule, or variants of those. And the winged idea is really good for shuttle when you go to low Earth orbit and you're returning to the planet. You use those wings in the last parts of re-entry when you're back in the atmosphere. But from a deep space exploration, it's a lot of weight that you take that you don't really use for your whole mission. Another piece was safety driven. So a capsule, by its design, if you lose the ability to control the spaceship, it's still going to land. It lands like a badminton birdie. It might not land where you want it to, but it lands and the crew is safe. And so it has some safety aspects to it that's important to us. So those are the two reasons it looks like it does today.
Jules, can you describe some of the big advances that set Orion apart from its predecessors?
So let's go all the way back to the Apollo program, because that was the last capsule program we had. As you can imagine, from the 1960s to now, advances in just technology on many different fronts, from computers or computing capabilities and speeds, to materials, to advanced manufacturing processes like 3D printing. So almost in every category that it takes to design and build a spacecraft like Orion, there have been huge advances.
You'll notice the solar arrays here, right? So Shuttle and Apollo used commodities on board to generate electricity, and that meant you could only generate it for a limited amount of time until you run out of those commodities. With the solar arrays now, we can generate electricity indefinitely when you're in space. That's kind of one simple example.
What are the biggest challenges of a long space trip, and how is Orion meeting them?
If you're in low Earth orbit at the space station, for instance, you can return home in 90 minutes or so. You may not come down exactly where you want to, but you can get home pretty quickly. If you're going to the moon, it could be days until you return, and if you're going to Mars, it could be years. So the further you move away from the planet, the more redundancy and things you build into your spacecraft.
Jules, what are the launch plans for Orion and SLS? When will we be aiming for Mars?
Well, the next orbital test flight is called Exploration Mission 1. We actually are building the Orion for Exploration Mission 1 right now. It's almost finished. And the plan for it is to launch late next year. Maybe early the following year. Beyond that, we have Exploration Mission 2, which we're also building here at the Kennedy Space Center as we speak. I believe that's in the 2022-23 time frame, and that'll be the first crewed mission, so we will have people, astronauts, on board EM2. And then Mars is probably the mid-2030s. And prior to Mars, NASA's plans are to put the Gateway, which is a spacecraft orbiting the moon. And so before we go to Mars, our plan will be to go to the moon multiple times and then use that as a launching pad for a Mars mission.
Wow, well, thank you both very much for meeting with me today.
No, thank you very much for your time. I appreciate it.
It's nice talking to you.
Very nice.
While Kaylee was learning about the mission of the Orion program at Kennedy, Chandel was at Johnson Space Center in Houston to learn even more about the Orion capsule.
We are in Building 9 at Johnson Space Center. Building 9 is home to NASA astronaut training and space vehicle mock-up facilities. Behind me is a full-scale mock-up of the Orion Crew Exploration Vehicle, and I'm joined here by Orion engineer Najoud Moranci. Thank you for being here with us today.
You're welcome. Thanks for coming.
So I understand that the Orion will sit on top of the SLS rocket. What can you tell me about its design?
So one of the key parts of the design of Orion, we can abort at any time during ascent, and once we get out in space, Orion can always turn around and come home as well. So that's a really fundamental part of our design, was making sure the crew is safe throughout the whole mission.
And how do you keep the astronauts safe in here?
So there's a lot of ways we do it. So first off, there's redundancy. So everything has a backup to it. There's multiple tanks of water, there's extra computers. So no matter what happens, we can always actually come home on the backup system that's on board. One of the fundamental parts of spaceflight is keeping the crew safe by having redundancy and then having lots of our contingencies planned out ahead of time to be able to respond to those emergencies.
What will it be like for astronauts to live in Orion while in space?
So it's kind of like a camping trip. They'll be inside, we can have 4 of them in there, and they'll have to bring all of their food and clothing, and they've got a shower and waste management system. It's actually in the floor in there, and they bring sleeping bags. So they'll be doing experiments throughout the day, they'll be monitoring the ship's progress, but then they have to do lots of exercise so we can keep their musculoskeletal system from degrading. They'll be eating meals, they'll be having leisure time.
And what are your responsibilities as an Orion engineer?
So I'm actually the mission analysis lead for the program, and my team are actually designing the missions to the moon and home again. So we have to make sure that when we're done building Orion, we can actually accomplish the missions, and the mission designs are something Orion can fly.
Can we take a closer look?
You bet. Let's go inside.
Awesome.
So inside here, this is the Orion medium fidelity mock-up, and this is here to train the astronauts as well as allow the engineers to figure out what the design looks like on the inside so we can make sure everything's going in and will fit when the space vehicle actually flies.
Well, I see the controls in there, so could you tell me how they control this vehicle?
So the crew will actually fly it, but most of the vehicle flight is automated. So we'll have software that's on board controlling it. There's thrusters and engines that are in the service module that would be beneath where we are right now, and that actually flies the spaceship with the ground control monitoring and then the astronauts providing oversight over what's going on.
Thank you so much for talking with me today.
You're welcome. Thanks for coming.
I really enjoyed it.
In order for the SLS to make it to Mars and beyond, we're going to need a lot of power. The RS-25 engines are more than up to the task. But before the engines are ready to be used in any real-life situations, they have to be tested rigorously and for years to ensure that they'll perform as required. To learn more about this all-important testing process, I got an opportunity to speak to one of the engineers working tirelessly to get these engines ready for launch.
We are standing near test stands at Stennis Space Center in Hancock County, Mississippi. I'm now joined by Tommy Carroll, a NASA engineer. So why don't we test the physical engine instead of just using a computer?
We use computer modeling for a lot of different things. We use it in design, we use it to check out clearances of hardware. We also use them to model what should be happening inside of the engine. And when we run that engine, the physical engine, and actually see it, we're baselining our models, but we're also looking at some of the variables that we're going to see, and that's why we test.
What is the engine test today going to tell us about?
We're going to be looking at a green run controller. That means a brand new controller, the computer that tells the engine what it needs to do.
So what's the next step from here, and how many more steps are there going to be until the engine's ready for launch?
So this engine that we're testing today is a development engine, and that just means that we use it for testing parts, not for testing the whole rocket engine. But the very next engine that we're going to test is a flight engine that will fly in space. So we'll take that engine after we test it, we'll ship it from here to another facility called the Michoud Assembly Facility. We'll install it on the rocket along with 3 other engines, so have a total of 4 rocket engines on that. We'll take that, that's called the stage, we'll bring that here, we'll mount it on that test stand, and from there we'll test it again. And once we've done that test, we'll put it on a barge again called the Pegasus, and we'll ship that barge from here down to Florida. And they'll put the whole rocket together there and then roll it out to the launch pad.
Awesome, great information. I can't wait to see this test.
It's going to be good.
Oh yeah.
Yeah.
To operate engines like the RS-25, you need a lot of fuel and a pretty big gas tank.
We're at the liquid hydrogen test stand at NASA's Marshall Space Flight Center with NASA's structural engineers Robert Bobo and Sam Stevens. Thank you for talking to me, guys.
It's a pleasure to be here. Thank you.
Robert, can you give me an overview of the systems and the components of the SLS?
Sure, and I'll set it with reference to the test article that's behind us here. The test article that you see behind us is the liquid hydrogen tank for our new SLS launch vehicle. The hydrogen tank is our fuel tank, if you will, for the entire vehicle. The liquid engines on this vehicle run on liquid hydrogen and liquid oxygen. Those are the propellants that we use to produce the thrust. In addition to that, we have a solid rocket booster attached to each side of this liquid hydrogen tank for added thrust to get through the Earth's atmosphere. As we go up the stack, if you will, there's an inner tank that sits on top of this. Above the inner tank is where the LOX tank, or the liquid oxygen tank, rides. Then we adapt to our second stage. Then we adapt to the Orion, which includes a service module, a crew module, and a launch abort system.
Sam, what are structural tests and why do you do them?
Well, the structural tests are very important to us. You've got these engines underneath and beside that are pulling, winds, pushing, all sorts of different forces that it has to be able to withstand. So we do structural testing. We put all these forces into the rocket to make sure that it can withstand those and the vehicle is safe to fly.
I know that this rocket is designed to take us back to the moon. What are the similarities between the SLS and the Saturn V?
Some of the primary similarities are the fact that we use liquid propellants through the rocket engines to generate the thrust to get to the moon and complete the mission. We also have to do it in stages. One stage or one set of engines doesn't get us all the way there. And a little difference with SLS is we have the solid strap to each side for the first phase of the mission.
So why does America need this rocket to go to the moon?
There are other nations, other private companies who are building rockets, but none of them have the payload capacity that we need to launch an Orion carrying multiple astronauts or very large payloads. We need an SLS with all of its launch capability to get all those things to the moon. Once we get to the moon, we can learn how to work with these large components, and from there, we can eventually move on to Mars.
I know that you guys said that the rocket was going to be big, but how much bigger will it be compared to what's behind us right now?
So what you're looking at behind me, the test article here is about 150 feet tall. The Space Launch System itself, add another 100 feet to that, about 320 feet tall.
Wow. Well, thank you guys for talking to me today. I really appreciated it.
Thank you. It's been a pleasure.
If you're going to get something the size of NASA's Future Space Launch System, or SLS, off the ground, you need more than just brawn. You need brains. Computer brains, the best science has to offer. The SLS's computers work using the same basic principles as the computer or smartphone you interact with in your daily life. In order to function, computers need programming. Programming is built by humans by writing lines of computer code, a language spoken by computers which is then input directly into the computer. With this code, computers can be programmed to do actions automatically, like turn on and off certain circuits or valves on a rocket at specific times. This allows human controllers the ability to manage hundreds of delicate operations on the SLS that would be impossible without a computer. The Space Launch System has both brawn and brains, and as NASA's future vehicle for sending humans into space and beyond, it'll be one of the smartest rockets ever when it takes flight.
I really wanted to see how engineers are testing the computer hardware that's responsible for operating SLS launch systems.
And now we're here at the SLS Systems Integration Lab. Here, engineers install different components into this system unit mock-up to try to see how different things work together. I am here with Hannah Hopkins, SLS software engineer, and Alex Matris, aerospace engineer. Can you explain to me the systems on this SLS?
Well, there's a lot of avionics systems on board, and avionics are just the computers which operate all of the systems that fly the rocket. One of the systems is the flight computers. It's what's doing all the controls, it's the autopilot system, and it's checking all of the sensors and everything else to make sure that everything's still working well for flight.
There's 3 flight computers, and they're basically the brain of the operations. And if one of them fails, it's okay. They vote it off the island and we keep going. But if 2 of them fails, things get a little risky. So we definitely need these. These are crucial to flight.
There's other instruments such as a redundant inertial navigation unit, which is a fancy term, but all it's doing is just figuring out where we are when we're in space. There's other systems for like hydraulics and steering the vehicle so that you can steer it to get it to wherever you need it to go to.
We also have the engine controller over here. The engine controller basically controls the mixture ratio between the liquid oxygen and the liquid hydrogen tanks, and so it controls the thrust of where it goes. And it also takes all of the sensors from the engines, and it can look at, is this engine failing us, or is this engine okay? Is it doing what it's supposed to do? So you can kind of think of the systems of the SLS as kind of the central nervous system of the rocket, especially the avionics components in here.
How do you test SLS systems and software in here?
We test all of the hardware and software in here with a simulation called Artemis. And so basically what we do is we write code to simulate all of the different models on SLS and all of the different components. Something cool with that we can do is we can say, what if one of the engines fail? Or what if all the engines fail? Or what if the flight computer quits on us or something like that? And we can see how the rocket is going to react so we can better prepare prepared how to handle that on launch day. In fact, we've actually run about 15,000 simulations in here, and so we've launched the rocket 15,000 times.
We present the flight computer any number of scenarios to make sure that it can detect all the kinds of different faults and still keep flying safely. You can't do all of these with a real test flight.
Yeah, and so that's one of the big differences between now and the Apollo days, is that they didn't have that software to be able to test it as much as we have.
What are some of the things that you've learned from the testing that you've done here?
Well, our job is to bring a lot of different pieces together all in one place. There's a lot of different people making a lot of different parts of this vehicle. So we'll find issues where two things may not talk together the way we thought they would. We can figure that out, fix it, and test the solution to it right here in our lab, and then go make that happen in the real hardware.
Thank you guys so much for telling me about all the awesome stuff you have going on here.
Yeah, of course. No problem. It was our pleasure.
Over.
Is that it? I think we got them all. Let's check. And that's future exploration and space computer controls. We did it. Great work, team.
Yes! But we really couldn't have done it without your help.
That's right. Every single one of you viewers out there should now consider yourselves members of the STEM Brigade, just like us.
Exactly. Together, we all learned about the science and history behind human spaceflight.
And the endless possibilities in the future of our travels away from the big blue marble we call Earth.
Thanks for joining us on our out-of-this-world journey. And now...
STEM Brigade, over and out.
What's up for January? New year, new moon, midnight meteors, and Mars rises. January begins with a new moon on the 2nd, and that means the first week of the month is ideal for stargazing because the few days before and after the new moon are the darkest. Head outside around 8 or 9 p.m. all week and look southward to be dazzled by all the bright stars of the winter circle, along with the Pleiades and Orion. The quadrantid meteor shower peaks on the night of January 2nd and the morning of the 3rd. This tends to be one of the better meteor showers of the year and often produces a number of bright meteors called fireballs. This year, the peak coincides with the new moon, making for great viewing conditions provided the skies are clear. You should be able to see a few meteors on the couple of nights before and after as well. For the best quadrantid meteor viewing, find a dark location away from bright city lights, point your feet roughly toward the northeast, and look up. The meteors appear to radiate from the constellation Boötes, which includes the bright star Arcturus, but they can appear anywhere in the sky. Generally, the best viewing will be after midnight, once Boötes rises above your local horizon. The source of the quadrantids is thought to be the asteroid 2003 EH1, which might actually be an extinct comet. So start off your new year by catching a few shooting stars after midnight on January 3rd. Finally, a couple of highlights at dusk and dawn. On January 5th, look to the southwest after sunset to find the crescent moon in a close pairing with brilliant Jupiter. The two will be only about 4 degrees apart, which should make them appear together through most binoculars. Then at the end of the month, on January 29th, if you happen to be up early, you can catch sight of the moon near the red planet. Joining the pair in the southeastern sky will be Venus. Having left the evening skies last month, Venus is now rising before the sun as the morning star. Now, Mars is slowly returning to view after passing behind the sun over the past few months. In fact, NASA stops communicating with our spacecraft at Mars for about 2 weeks every 2 years when the planet is directly opposite the sun. That event, called Solar Conjunction, took place back in October. Mars will continue to brighten and climb higher over the next few months, where it'll have super close conjunctions with Saturn and Jupiter, which we'll tell you about in future videos, so stay tuned. Here are the phases of the Moon for January. Stay up to date with all of NASA's missions to explore the solar system and beyond at nasa.gov. I'm Preston Dykes from NASA's Jet Propulsion Laboratory, and that's what's up for this month.
The Rescue Coordination Center started receiving distress signals.
The bridge was starting to fill up with water. The ship was sinking and got them out on top of the rescue boat.
Winds up to 60, 70 knots.
We started to separate one by one.
Wave height 50 to 60 feet.
Finally I was alone and no rescue boat or nothing. The rescue boat drifted away.
It's freezing out there.
All I had to do was just wait and hope some kind of miracle would happen.
There is almost no chance to survive in conditions like that.
AIS, the automatic identification system. All ships out on the open oceans are obliged to transmit their position and their identity and their direction of speed, heading and speed, etc. It's kind of like air traffic control for the sea.
It's very useful to help provide assistance to ships in distress.
First of all, to see, do we have assets in the area that could help somebody in distress. In the days before AIS, we didn't even know if there were any vessels in a particular area where we have an incident.
They were more or less invisible to the Coastal Traffic Administration.
But as of today, if we have an incident out in open water, we have the chance to see what vessels are in the area and could contact them directly to route them to the position or the distress, and in that way, in a more effective way, rescue more people within a shorter time frame than we ever have before.
AIS receiving stations along the coast, they can only look a certain distance out into the sea.
Ships that go out beyond 75 kilometers outside the coast were over the horizon and invisible to us. But if you think about these signals going straight, they go maybe several hundred kilometers out into space. And you know what circles around the Earth about 400 kilometers above us? The International Space Station.
The European Space Agency contacted the Norwegian Defence Research Establishment and gave them the opportunity to mount an AIS receiver on board the space station to test out this technology from space. All our calculations indicated that this should work, but we really did not know before we switched on the receiver on the space station. 1st of June 2010, the system was turned on.
The switch was flipped and the light came on and we were actually able to get the first data in. Yes, the instrument works.
We all got very excited.
And suddenly we could see a whole world full of ship data. It was I would say, a quantum leap really in our ability to look at global ship traffic.
It's like a blind man starting to see.
Yeah, it was a huge relief and great satisfaction to see.
So this brought a whole new dimension to the monitoring of ship traffic on the open oceans.
Nobody knew how many ships really are out there at any given time, and suddenly we had, if not the complete picture, then almost a complete picture.
On a typical day, the space station is observing about 30,000 ships out on the open ocean.
I was kind of overwhelmed, I guess, by the response this got. The space station really is an excellent lab for testing this type of technology.
This project demonstrates that the International Space Station is not just for science and astronauts, but it really benefits the whole mankind with down-to-earth applications.
Based on the AIS, we had another vessels in the area that we contacted who continued to the area, and they searched together with the helicopters. Nobody expected to find anybody surviving in that conditions. They actually spotted one man in the sea.
After floating in the North Atlantic Ocean for 4 hours, I was finally rescued.
Thanks to AIS data and AIS data from the space station, this lone survivor was rescued. An absolutely happy ending for him.
And luckily for technology that made something that was basically impossible to survive possible.
What happens if you wake up in the morning and you understand the state of the world as it is right now?
What could that data enable? How could people make smarter decisions? How could, for example, a farmer get better yield on his or her crops? How could somebody help disaster response? How can we use satellites to help humanity? That in many ways was the underlying thesis of doing Planet Labs, was to get data into the hands of people that could enable us to make smarter responses to that.
Planet Labs set out with the mission to photograph the entire Earth every day. And they thought, how are we going to do this? They said, let's build our own satellite.
Commercial imaging satellites, they're very large. They are very expensive. We took a different approach.
By making them really small, we can launch lots of them, and by launching lots of them, we can cover this, to get to this mission of imaging the whole Earth every day.
If we can do that, then we can literally change the way that we see the world.
And they called it the Dove. It's about the size of a loaf of bread.
Our doves are basically mainly a big camera with a telescope looking down to take pictures of the Earth. We initially developed the first Dove satellite in our garage. So we kept on iterating the Dove design, we made it better and better, and eventually we put our first one into space. We had no idea what the quality would be like.
I mean, we didn't know if it was going to work.
But we got an image down and it was so beautiful that we knew at that point we could make this technology work.
Wow, we can really do this, and we can achieve this mission, which is something that is really needed for us to understand global change.
So we had done a couple of demonstration satellites, but the next steps we wanted to do was to scale it up to test the first fleets of satellites.
But what made that possible was actually access to space.
So here's the problem, that in order to take pictures of the entire Earth every day, you're going to need more than 1 or 2 satellites. You're going to need a whole lot of satellites, and you're going to need to be able to deploy them really fast. And really, there's only one obvious choice on how to deploy that, and that's the International Space Station.
There was no other platform in the world in order to get access to space of that fashion in that time period than the International Space Station.
NanoRacks is our key partner with NASA.
At NanoRacks, we understood Planet Labs' vision, and we knew that we could help. We worked together to figure out what was going to be the best way to get as many satellites as possible, and we basically developed a new platform. It goes out of the GIM airlock. It's picked up by a robotic arm, pointed out into space, and it fires these little satellites off of the space station.
They were able to secure 28 of our satellites to be launched from the International Space Station, and that was known as Flock 1, our first constellation.
This opened up the whole world to satellite developers, people that could put things into orbit fast.
We now deploy these on a regular basis from the International Space Station. And now today, we're able to operate the largest fleet of Earth imaging satellites in human history.
And none of that would have been possible without the International Space Station.
The International Space Station does enable young, small companies like ourselves to get going in space.
The ISS provides a lot of opportunities for commercial companies to test and find where the market in space is going to be.
And so what we're seeing today is a proliferation of new ideas and new concepts. It's almost like it's a renaissance of what's happening in space. Buckle up and strap down, because this is going to be a rocket for all of us in the global community to be part of.
The first pictures now coming in from Puerto Rico after taking a direct hit. Hurricane Maria slamming into the island. One official saying the island is destroyed.
Hours with winds and rain, and didn't stop.
Power lines are down. Streets are impassable. Many roads are flooded.
High winds uprooting trees, overturning cars, and turning buildings into piles of twisted metal.
It is something that will change Puerto Rico forever.
We had no water, no food, no gasoline, no communication at all.
Not knowing where my next meal will come from, it hasn't been easy.
After Hurricane Maria, everything was gray, all the plants were dead. Hurricane Maria took the color away from us.
I am sure that these children will not be the same. They will not be the same. They are still struggling and trying to recover from this.
My name is Joe Acaba. I'm a NASA astronaut of Puerto Rican descent. I was about a week into my mission on the International Space Station. Hurricane Maria was forming up, and from there, if you looked out the window, Maria took up a big chunk of what we could see. It was going to cover the entire island. After the hurricane, their power grid was pretty much taken out. You just couldn't see the island anymore. The hurricane, I think, had a huge impact on, the island as a whole, but especially the kids.
Joe Acaba was our hero, and we need something positive. The students need something positive.
We wanted to pull through, forget all that happened, and lift up our spirits and lift off the island.
So I knew I couldn't do much from up on the International Space Station, but I did want to connect with the students to show them that there is hope and that there are people out there that care about them.
NASA has the STEM station, which allows the students and teachers to talk to the astronaut in the space station.
It's making that connection so that maybe, they become more interested and we can inspire them more to study the STEM fields.
So we were able to establish and coordinate with NASA one of these video conferences. Thousands of students from different parts of the island watching the video conference with the space station, talking to Joe.
This is Joe aboard the International Space Station. I have you loud and clear.
How do you compare?
What is the most impressive view?
How did Puerto Rico look?
Are astronauts allowed to visit? How often?
What is the minimum number of?
It was awesome because, as soon as it came up, you could hear people clapping, people were excited. So even though I couldn't see them, I could feel them, and that was pretty neat.
It was amazing. He called from the International Space Station to see how Puerto Rico was doing, and that means a lot for us, a lot.
In May of 2018, I was able to go back to the island, my first time since the hurricane. It was a great opportunity to get out and kind of come full circle with those students, to go and see them in person and, kind of reiterate how important they are, and just to give them a little bit more hope, because there's still a long way to go on the island.
He's a hero for us. Kids love him, and everybody loves him here. Joe Acaba is the role model that we need at this time.
I want to be like him. I want to go far, and I want to be an example for little kids when I'm older.
Not only is the International Space Station a great tool for scientific research and exploration, but for students from Puerto Rico in particular, I think that having that video conference with them, it did provide some hope. It did provide some inspiration. And so it's just one of the benefits that we get from the International Space Station.
In order to support International Space Station, we're constantly having to build new hardware to send to space, but as well, we need to make training hardware on the ground. So we ask ourselves, what if we got high school students to build us some training hardware and get them out of the textbook, get them some hands-on lessons to work with, and by doing that, we'll be inspiring the next generation of students. So that's when we decided to create Hunch. Hunch goes to the local high schools, partners with the high schools, and gives these students opportunities to design, build hardware that will fly in space or be used for training hardware on the ground. Students did the design and engineering, the CAD drafting, the 3D print prototyping, the machining, the procurement of the hardware. All this done by high school students to get this article to fly in space. From the quality perspective, the students have exceeded all of our expectations. The hardware we're getting in is top notch.
This program actually helps them focus into the engineering and the STEM fields.
I've been teaching for 23 years. I've never seen anything that even remotely compares to having the type of impact on students that Hunch has had. Absolutely phenomenal.
Working with the Hunch program, we fabricated training hardware for the ISS.
I created and designed interactive simulations.
We're making a Mexican paella and hopefully gets chosen to go to the International Space Station.
From the Hunch program, I've learned how to use AutoCAD.
We learned a lot of teamwork.
I've definitely gained some communication skills.
We're learning more about food science, technology, but everything basically doing this.
It gives them a confidence that I don't think they would have had to that level before this.
Maybe I would actually be able to be an engineer. So it was never something that I'd thought that much about. And then I was working on this stuff that went to space, and I couldn't think of anything more exciting. And I still can't.
It's a pretty cool thing to be able to tell other people or family when you go visit that I work with NASA programs.
I mean, I told everybody, like literally everybody.
We have an opportunity here for them that is unbelievable.
It's kind of like getting a master's at age 16.
They truly have moved on to a level they wouldn't have approached or wouldn't reach, I believe, without this program and without the International Space Station.
Before the Hunch program, I really was just a C student with no direction in my life. And since then, I've been on the Dean's List for the past 4 years and will be transferring to pursue mechanical engineering.
It really helped me find my passion for aerospace. The Hunch program gave me my career.
The impact on their lives has been amazing. They're more successful, they're more driven, they're more determined. They know they can achieve. And that's all, I think, through this program, through the Hunch program and interaction with the International Space Station.
Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration. Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything we can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
And the observation of an occultation is one of the more challenging missions that Sophia can do.
Right now, we are looking at the dawn of a new era of aviation.
Most early inventors thought that flight control can be achieved by a pilot simply shifting his weight back and forth. The Wrights, on the other hand, knew that controlling the plane would be the key to successful flight.
Release brakes, throttle to afterburner. Watch exhaust temperature. Watch nozzle position. Check engine pressure ratio now. And all this time, steer down the runway. First nose wheel steer, then rudder. Lift nose wheel at just the proper speed to fly off in the least ground roll. Today, man copes with a highly complex environment with physical abilities no better than he has ever had. Greater demands on the air crew call for ever closer relationships between man and machine.
Until now, all flyers have used the force of their muscles, multiplied by gears and motors, to adjust wing and tail surfaces.
Your landing gear and flaps are operated hydraulically.
It's about 45 pounds of force to get that stick to move. It's a very athletic endeavor.
An advanced flight control system called the Digital Fly-by-Wire System has been installed by the Flight Research Center in a modified F-8 jet aircraft.
The pilot of this experimental aircraft need only indicate the desired flight path to a computer, which then